Hey folks, I welcome you all to Scalar Academy's YouTube channel. So, if you want to be a good programmer, then you need to have a good mathematical aptitude. Or, in other words, you need to have mathematical way of thinking to solve the coding problems which you face. So, understanding the importance of this, we have brought you this tutorial on mathematics for programming. Now, before we start off, I'd like to request you guys to subscribe to our channel and also hit the bell icon so that you do not miss out on our upcoming videos. So, on that note, let's get started.
Hello, so we are back with a live class. Today's topic is factorization. These classes are for people who want to become better programmers, right? Better at DSN algorithms. So please make sure that you subscribe to the channel and press the bell icon to get notifications, right, about any new videos. As always, there will also be a practice set available to you. This practice set will have a few problems so that you can apply whatever you learn in today's class, right? Actually practicing the problems will help solidify the concepts. All right. So we are going to cover factorization today. Now, factorization is a topic of mathematics. All right. And as computer programmers, you will need to have a decent understanding of mathematics. In fact, in all sciences, and computer science is a science, right? The stronger you are at maths, the easier your life will be. Now, programmers, you don't have to be very good at mathematics, but there are certain areas that you need to focus on to be a good programmer. Now, these topics are like discrete math, probability, statistics, combinatorics, linear algebra, modular arithmetic, number theory, graph theory, right? So it is still a very large section of topics that you will need to be a very good programmer. So we're going to start with that. And today's topic is from number theory, and the topic is factorization. All right. So let us begin. All right. Cool. So before we begin, let us start with a question directly, right? Let us say that you have been given a number n, all right? And this is an integer. This is an integer. In fact, this is a positive integer, right? Your task is to find all the factors of this number, right? So for example, let us suppose that you have a number like 16, perhaps, right? So can someone tell me all the factors of 60? What all numbers is 60 divisible by? So when we're talking about factors, we are talking about the positive numbers, right? The positive integers that divide 60, right? And do not leave a remainder. So what numbers are those? So firstly, we have 1, right? Then does 2 divide 60? Yes, it does. So we have 2. Similarly, 3 divides 60. 4 also divides 60. 5 does. 6 does. 7 does not really divide 60, right? Now 8 also does not divide 60. Neither does 9. 10 does. Right? 10 definitely divides 60. After that, what numbers we have? So we have 12, right? Then we have 15. Then we have 20, right? What more? We have 30 and 60, right? So these are all the different factors of 60, right? Cool. Now, before we dive further into this problem, let us try to draw some observations. Right? Let us try to draw some observations and see if there is some pattern to what the factors of a particular number are, right? So first of all, you will notice that 1 and the number itself, they are always factors of this number. Yes, do you agree? Well, 1 divides every single number, and if you have a number, let us say n, then that number will divide itself, right? So that has to be a factor. What else do we notice over here? Is there any other pattern that we notice over here? Yes? So we notice one more thing. So the first thing is that 1 and n are divisors of n. The second thing that we notice is that factors come in pairs. Factors come in pairs. What do I mean by that? I mean that given any factor, there is a corresponding factor, right? So if I pair 1 with 60, then I will get 60, right? 1 times 60 equals to 60. Similarly, if I pair 2 with 30, then I once again get 60. So 2 times 30 is 60. Similarly, 3 times 20 is 60. 4 times 15 is 60. 5 times 12 is 60. 6 times 10 is 60, right? And then if I continue from here on, you will see that I will just repeat these things, right? So I will just repeat these things. I will say 10 times 6 is 60, right? So 10 and 6 have been repeated. Similarly, I will next say 12 times 5 is 60. So after all this, the numbers are being repeated. Is that clear? The factors will always come in pairs, right? That is the main observation that we draw from. All right. Now, given that we have these observations, could we write a program? Could we write a function, let us say find factors, right? That takes an integer n, and let's suppose prints out all the factors of it. So let us in fact call this, instead of find n, let us call this print factors. This function accepts an n, and it is supposed to print out all the different factors of n. Right. So what approach do we see over here? So one way to do this would be the naive way, right? The very, very simple way. The first way would be to go through all the numbers. Go through all the possible devices. Right? So to go through all the possible devices, we will need a few more observations, right? Let us quickly see what those observations are. So the first observation was that 1 and n are devices of n. There is one hidden observation over here, right? Let me mark this as the third observation. And that observation is there are no devices that are less than 1, and there are no devices that are greater than n. Right? So the devices, so 1 is the smallest divisor and n is the largest divisor. Yes? Does that make sense? So when I am trying to find the divisors of a particular number, I only have to go from 1 all the way till n, right? Because I cannot have divisors that are greater than n. Does that make sense? Is that part clear? Right? Perfect. So how do we write this program then? This is a very simple for loop. So we will say for I goes from 1, right, all the way till n, and we'll increment I. So we'll go through all the different numbers. What we will do inside this? We will check if n mod I equals to 0. Right? So everyone is familiar with this mod operation, right? This is the remainder operation. This says that when we divide n by I, then what is the remainder? Is that remainder 0? If that remainder is 0, then I must be a factor, right? I must be a factor. Then what do? We simply print I, right? So this is our code for factorization, right? Cool. Now this is the first approach. This is very naive. We can do much better than this. But why is this naive? So let us analyze the time complexity of this particular program. So how much time does this take? If I have a number n, then what is the time complexity of this particular program? Well, this is a simple for loop, right? We are going from 1 all the way till n. So this is linear. In fact, this takes order of n time, right? Cool. Can we do better? Well, certainly we can. So the first thing that you will notice over here is that whenever you're looking at these numbers, we know that the largest factor is the number itself, right? The largest factor is the number itself. But what is the second largest factor? How big can the second largest factor be? So I know that the largest factor is n itself, right? What about the second largest factor? Second largest, that must be less than or equal to n by 2, right? That factor must be less than or equal to n by 2. Why? Because if it is greater than n by 2, then its corresponding pair, right? Divisors always come in pair, right? Factors always come in pair. Its corresponding pair will not be an integer. Right? 2 is the smallest integer that might divide this number apart from 1. Right? So we know that the second largest has to be less than or equal to n by 2. So one thing that we can do over here right away is, instead of having this loop from 1 till n, right? Instead of having this loop from 1 till n, we can modify this. Right? We can modify this. So let me just modify this over here. I will say I is less than or equal to n by 2. Right? And notice that this is integer division over here. Integer division. Right? So in this loop, I will print all these divisors, but now I do not print n, right? I have missed n now. So I will have to add another statement over here, which will simply say print n. Is that clear? Because now our loop is going from 1 all the way to n by 2. So I will not print out n in this loop. I'll have to print it separately. Yes? So how much time did we save just now? We made a program twice as fast. Right? That's very nice, right? We certainly made a program twice as fast. Asymptotically, it is still linear. Right? It is still order of n time, but practically it is twice as fast. Right? Perfect. All right. So can we extend this? Can we extend this observation further? What about the third largest factor? What about the third largest factor? How large can that be? Well, if the number is divisible by 3, then the third largest factor can be up till n by 3, right? Does that make sense? So third largest factor has to be at max. It has to be less than or equal to n by 3. Similarly, the fourth largest factor has to be less than or equal to n by 4, right? And so on. So we see this pattern over here. Is that clear? Cool. Now the question is, we could use this particular observation to reduce our time complexity by half. How do we utilize all these observations? How do we really utilize all these observations? So to do this, let us make one more observation. Right? Let us actually go back to this observation that we had previously. Let us look at this thing once again. Okay. So let us say that instead of going from 1 all the way till 60, right? Instead of going from 1 all the way till 60, we only go till this midway point. Right? You clearly see that there is this midway point over here. After this midway point, so this is the midpoint. After this midpoint, the numbers will repeat. Yes, 6 into 10 repeats as 10 into 6. 5 into 12 will be repeated as 12 into 5, and so on. Right? So we only need to go till this particular point. We only need to consider this half. We do not need to consider the other half. All right. So if we are considering this half, then we have to go from 1 all the way till what number? We have to go from 1 all the way till this number. How do we find what this number is? How do we find what this number is? So basically, we are looking for a number I, right? We are looking for a number I such that I times something else. First of all, this should be equal to n, right? Because they are numbers, they are factors, right? So I times something should be equal to n. Secondly, I am looking for a number such that I is less than or equal to this something, right? Because so basically, I'm going till 6 because the pair of 6 or the number which is paired with 6 is greater than 6, right? 10 is greater than 6. If I go any higher, then the numbers will swap. 10 will now become, the first number will become greater than 6 now, right? So we are looking for a number over here that follows this property. Okay, so if this is x, then what can I say from here? I can say that x equals to n divided by I. Right? So I can put the value of x over here. I will get I is less than or equal to n divided by I. What can I get from this? I can move this I to the left hand side. Right? So I will get I squared is less than or equal to n. And what does this tell me? This tells me that these numbers, they must be less than or equal to. So I must be less than or equal to square root of n. Is this part clear? Is this derivation clear? This is very simple. A lot of you might already know this, but it is important from where this is derived. Right? This square root sign, this is not magic. All right. So once again, We are saying that we are looking for a number I, we are looking for a factor I, such that its paired factor, when we multiply them, we get n, right? They are factors. Now we are also saying that, okay, we are going to make sure that this factor must be less than equal to its pair. Right? This factor must be less than equal to its pair, because if it is greater than its pair, then we are just repeating ourselves, right? Because 2 times 3 is the same as 3 times 2. So we only need to make sure that this number is smaller than this number. Otherwise, we will be repeating ourselves. So we put this in the equation. We say I is less than equal to n by I, which means that I square is less than equal to n, which means that I is less than equal to square root of n. So what did we get from here? So now we can improve our program. We can now say that we have a for loop for I equals to 1, I less than square root of n, right? Square root of n and I plus plus. I less than equal to square root of n and I plus plus. Right? Now I will check if in fact n is divisible by I. So what should I print over here? If n is divisible by I should print I, right? I should print I. But is that all? Is that all? No, because I also have to print the other pair, right? Remember, we are only going to half the pairs down. So we also have to print the other pair. So I will also print n divided by I, right? N divided by I, right? And that will complete the list of factors. Is this part clear? Yes. Perfect. Right? Now, first of all, there is a mistake in this program. There is a mistake in this program, a very subtle mistake. Can someone point that out? Yes. Exactly. So over here, let me just point it out. So over here, Lucky says that, hey, this is the mistake, right? What happens when I is actually equal to n by I? Which means that when n is a perfect square, you will be printing this number 2 times, right? That is not very good. You will be printing this 2 times. That is not very good. So how can we fix this? Right. So first of all, is everyone clear? If n is 9, n equals to 9, what we will see? We will see I equals to 1. We will print 1, 9. Right? I equals to 2. We will not print anything. I equals to 3. We will print 3, 3. Right? So we see that we printed 3 2 times. That is not a good thing to do. Right? So we need to resolve this. And we see that this only occurs when n is a perfect square. Right? Otherwise, this issue cannot occur. Right? So how do we resolve this? We simply say that I goes till less than square root of n. Right? I goes till less than square root of n. And after this, we will specially check. After this loop is over, we will check. So after this loop, what will be the value of I? It will be exactly square root of n, if it exists. Right? So we will say if n mod I equals to 0, then print it just once. Right? Print it just once because it is a square root. So just print I. Right? Notice that we are not printing the pair over here. Is that clear? Cool. So this will give us the correct answer. Now the question is, how much time did we save? What is the time complexity? Of this particular code? Yes. So who can tell me that? Well, this is very simple, right? Just like the previous case, we have a simple for loop. And this for loop now goes from 1 all the way till square root of n. So the time complexity is supposed to be order of square root of n. Right? Simple. Is that clear? There is one more thing over here, that if you were actually using a function to calculate the square root of n, you would not do this again and again. Right? You will actually say sqrt or square root equals to, you will calculate the square root of n outside. And then you will just use that variable. Right? So that whenever you hit this condition, you don't have to calculate it again and again and again. Okay? So this will give us the correct code. And the complexity will be order of square root of n. Now that is a huge improvement. Right? That is a huge improvement, going from order of n to order of square root n. This is huge. This is massive. Imagine that you had a number which was, let's say, 100 trillion. Right? 100 trillion. 100 trillion is how much? 100 trillion is how much? It is 10 to the power 14, right? If you were to check this number, if you were to check a number of this order of magnitude on your computer, it will take a lot of time, right? How much time will it take? It will take around 10 to the power 5 seconds, right? Or you can say it will take around 30 hours. It will take around 30 hours of time. Whereas with this particular algorithm, how much time will it take? It will take just 10 to the power 7 operations. So this is 10 to the power 7, square root of 10 to the power 14 is 10 to the power 7. So it will just take how much time? It will take 0.01 seconds. Right? That is amazing. We went from a program that took 30 hours to a program that ran in 1/100th of a second. All right? Cool. So this is how we would factorize a particular number. Okay. So I hope this is clear to everyone. Now let us move on to a question, right? To a question, related question. Okay. Suppose that we have 100 doors, right? And all these doors are closed. All are closed. So we have basically door number 1 over here, door 2, door 3, door 4, all the way till 98, 99, 100. Right? We have all these different doors, and initially all of them are closed. So let me say that these are closed. Okay. Now we are going to play a game. We are going to play a game. This game will have 100 steps because we have 100 doors. We will have 100 steps. So the first step, what will we do? We will toggle all the doors. Right? So you understand what toggle means, right? Toggle means that if it is open, you close it. On the other hand, if it is closed, you open it. Toggle basically means to flip it. Right? Cool. So we will say that in the first step, we will toggle all the doors. In the second step, we will toggle all the doors, all the even doors. Basically, we will toggle every second door. Every second door. Right? In the third step, we will toggle every third door. And so on and so forth. It will continue like this forever. In the 100th step, we will toggle. So there will be just 100, right? We will toggle the 100th door. Right? So this is what we are going to do. Is this part clear? So first of all, what happens after the first step? Initially, all of them are closed. After the first step, all of them will be open. Right? Then what will happen? After the second step, we will toggle this every second door once again. So this door will become closed. 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 Right? In the third step, we will once again toggle every third door. So this third door will become closed. There was a sixth door over here. Right? It was initially closed. So we will open it up. Right? And so on and so forth. Does that make sense? So we are doing this thing. That is the game we are playing. The question is that after we are done with this game, after 100 steps, which doors remain open? All right. Is the question clear? Yes, after the third step, we will toggle every fourth. So in the fourth step, we will toggle every fourth door. In the ith step, we will toggle every ith door. Right? And the question is, after all these 100 steps, which doors will remain open? Okay. All right. So, I mean, this 100 is a very, very large number, right? So let us actually reduce the problem. So whenever you have a difficult problem, you try to check that problem on smaller numbers, right? So let us say that we only have 10 doors. Okay, we only have 10 doors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Initially, all of them are closed. Okay. What happens after the first step? So this is the 0th step. This is step 0. Step 1, step 2, step 3, step 4, 5, 6, 7, 8, 9, 10. Right? What happens after the first step? After the first step, every door is open. Right? After the second step, what happens? After the second step, what happens? So after the second step, 1 is open, 2 is closed, 3 is open, 4 is closed, 5 is open, 6 is closed, right? 7, 9, these are closed now. What happens in the third step? In the third step, 1, we do not change it. 2, we do not change it. 3 was open, right? 3 was open, so we will close it. 4, we do not touch it. 5, we do not touch it. 6 was closed, so we will open it. 7, we do not touch. 7 remains as it is. 8, we do not touch. 9 was open, so we will close it. 10, we do not touch. Yes? Okay, we move on. So in the fourth step, we will keep 1. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this, and we will not touch this. And so on and so forth. So can someone see what is happening over here? Can someone see what is happening over here? Basically, what happens in the ith step? What happens in the ith step? Exactly. So Srinivas has the right idea over here. Srinivas says that in the ith step, all the doors that are divisible by I, get toggled. Right? That is the problem over here. Now the question is, let us suppose that I am talking about the nth door. Right? Let us suppose that I am talking about the nth door. For which all numbers, for which all steps will toggle this door? Will toggle this door. Right? So is the question clear? If in the ith step, I toggle every ith door, then given a door number, right? Given that I am saying that, okay, let's talk about the 20th door, right? Let's talk about the 20th door. Then in which all steps will this 20th door be toggled? In which all steps will this 20th door be toggled? All the factors of n. Exactly. Right? All the factors of n. Yes. So basically 20th door will be toggled in the first step, in the second step, fourth step, fifth step, 10th and 20th step. Is that clear? Yes, because these are all the factors of 20. Cool. So how many times will this door be toggled? How many times will this door be toggled? Well, we see, we already know that factors come in pairs. Right? Which means that if there is a step number 1 on which this is toggled, there is also a step number 20 on which there is toggle. Right? Similarly, for step number 2, we have step number 10. For step number 4, we have step number 5. Right? So we know that the nth door will be always toggled, an even number of times. Right? Because why is this true? Because the factors will come in pairs. Right? So every door is going to be toggled an even number of times. Is that correct? Well, not so fast. Is there any particular number which has an odd number of factors? Right? What happens? So you have this pairs coming up. Right? You have these pairs coming up. What if there is a middle value? What if n is a perfect square? In that case, this value root n, it doesn't have a pair. Right? Root n is going to pair with itself. So it will not have a pair. So basically, if the nth door, so if n is a perfect square, right? If n is perfect square, then nth door will be toggled an odd number of times. Right? In all other cases, it will be toggled an even number of times. Is that clear? Yes. All right. Cool. So what happens if you toggle a door even number of times? Initially, it was closed. Then it became open. Then it became closed. Then it became open. If we do this an even number of times, what will the end state be? It will be closed. Right? Because we started with closed, we toggled it even number of times. So eventually it will be closed. On the other hand, when n is a perfect square, we will toggle it odd number of times. So what will be the final state? We started with closed, we move to open, we move to close. Since we will do this odd number of times, the final state will be open. Right? So which all doors will be open? Now we know the answer. Which all doors will be open? All the doors whose numbers are perfect squares. Perfect squares, right? And all the doors from 1 to 100, which all doors are those? Which all doors are those? So that is 1. Then 4, 9, 16, 25, 36. Then what do we have? 49, 64, 81, and 100. Right? Exactly 10 doors will remain open, and all these are the doors that will remain open. Is that clear? No. If n is prime, the answer will be even. So Vishwajit has a question over here. Vishwajit says that if n is prime, then how many factors does it have? Well, for any prime number, it has two factors, right? 1 and n itself. So for prime numbers, it will be even, not odd. Only for perfect squares. Only for perfect squares will we have odd number of factors. Odd number of factors. All right? Cool. Okay. So what did we learn from this particular problem? This was not a very difficult problem, right? This also does not involve a lot of programming. We did not do anything fancy. We did not do any fancy maths over here. All we did was we sat down, we made some observations, right? We made some observations. We looked at the problem, we tried it with a smaller number. Instead of going to directly 100, we tried it with a smaller number. So that is something that you have to keep in mind, right? Whenever you're facing a problem, whenever you're facing an algorithmic problem or any problem in life, please, your first step should not be to come up with a solution. That is a very, very wrong way of doing things. The first step should be to make observations. Make observations. Right? Once you do this, only then you will be able to find a solution. Find a solution. If you do not make observations, you will never be able to find a solution. All right? So please do not skip this step. Okay. Cool. So that was a nice little exercise. Let us go back to what we were doing earlier, right? So first of all, what we did was we found all the factors. Found all the factors of n, right? That is the first thing that we did. Now, while we were doing this, we kept talking about something, right? We kept talking about prime numbers. So first of all, can someone quickly tell me what a prime number is? So what is the definition of a prime number? What is the definition of a prime number? A prime number, so first of all, it has to be a positive and it has to be an integer. Right? It has to be a positive integer. Secondly, it must have exactly 2 divisors. Right? It must have exactly 2 divisors. There is a lot of people think that this is the definition of prime numbers, right? A lot of people think that a prime number is a number which is divisible by 1 and itself. Right? By 1 and itself. If this was the definition of prime numbers, then 1 would be a prime number. Right? Then 1 would be a prime number because, hey, 1 is divisible by 1 and 1 is divisible by itself. But 1 is not a prime number. All right? Is that clear? So this is not the correct definition. This is very close, but this is not the correct definition. The correct definition is that it must have exactly 2 divisors. Exactly 2 distinct divisors. Right? So can someone very quickly tell me what the prime numbers are? A few prime numbers from the start. So is 0 prime? Is 0 prime? No, it is not. Is 1 prime? No, it is not. Is 2 prime? Yes, 2 is prime. 2 is the smallest prime number. Then 3 is prime. 4 is not prime. 5 is prime. 6 is not prime. 7 is prime. 8 is not prime. 9 is not prime. 10 is not prime. 11 is prime, and so on. Right? How many prime numbers are there? How many prime numbers are there? 100, 200, 500, 1000, million, billion. How many prime numbers are there? There are infinitely many prime numbers. Infinitely many prime numbers, right? Everyone knows this? Cool. There's a very simple proof for this as well. All right. Okay. So now that we know the definition of a prime number, some people are saying 4 prime numbers are there. That's nice. Suppose now that we know the definition of prime numbers, can we write a program? Can we check if a number is prime? Right? So we know that the definition of prime number is a number which has exactly two divisors and it is a positive integer. So given a number, can we check if it is prime? So is prime, right? It is going to return a boolean and it is going to take an integer. Yes. So how can we write this program? So very simple, right? Very simple. We can say that count is 0, right? We can write a loop for I equals to 1, I less than equal to n, I plus plus, right? And we can check if n mod I equals to 0, then we will do count plus plus, right? And finally we will return what? If the count is exactly equal to 2, then it is prime, otherwise it is not prime. Yes? Right? Cool. What is the time complexity of this program? What is the time complexity of this program? This program runs in order of n time. We already know that we can optimize this a lot. Right? We already know that we can So Suraj says why boolean? So this is prime will return true or false, right? It will return true or false. True if the number is prime, false if it is not. Right? Which is why we are returning a boolean. TechGeos is asking, sir, just confirming, is this code Java, right? So this might not exactly be Java. For example, in Java, you will have to put a semicolon over here, right? I'm not sure if you write bool or boolean in Java. I kind of forgot, but the rest of it pretty much looks like Java, right? Pretty much looks like Java if we add these semicolons. This will also work in C++, almost exactly the same way, right? However, when we are doing these classes, we will not be following any particular programming language. If you have any questions of a particular programming language, that let's say if you want to ask, okay, so how will I do this in Rust, or how will I do this in Haskell, or how will I do this in, let's say, Python, right? So you feel free to ask that. Okay, feel free to ask that. I will be able to give you an answer for most common programming languages. However, we will not be focusing on the programming language in this particular class, right? We will be focusing on the pseudocode. We will be focusing on the intuition. Okay, cool. Okay, all right. So we see that this is linear in time, but we already know that we can improve this a lot, right? So how can we improve this? Instead of going from 1 to n, so if 1 is a factor, right? If n is a factor, right? And prime numbers have exactly 2 factors. What does this mean? What does this mean? This means that if n is prime, if n is in fact prime, then it must not have any factor, between 2 all the way till n minus 1. Yes? Is that clear? It must not have any factor between 2 all the way till n minus 1. In fact, it must not have any factor between 2 all the way till n by 2. In fact, we can even generalize this and we can say that a prime number does not have any factors between 2 all the way till square root of n, right? Because we see that the factors will come in pairs. Right? The factors will come in pairs. Is that clear? So we can improve this code a lot. We can say boolean is prime, right? We have an integer n, and we will say, so now we don't need that count anymore, right? Because we are just checking if there is a prime factor or not, if there's a factor or not. So we can say for I goes from 2 all the way till square root of n, I plus plus, right? If there is any factor, if n mod I equals to 0, if we did find a factor, then what can we say? If we did find a factor, then what can we say? Hey, we found a factor, so it must not be prime. If you found a factor between 2 and square root of n, it cannot be prime. So we'll just return false. Return false over here. Right? And after this loop is done, we will return true. Because if we did not find any factors except for 1 and n, then the number must be prime. Is this clear? And the time complexity of this code is The time complexity of this code is order of square root of n, right? Perfect. So we know that we can check if a number is prime in order of n time as well. Now, one question, it's not, I mean, we are not going to teach that today in the class, but one very common question is this the fastest we can do? Is this the fastest we can do? And the answer is no. The answer is no. In fact, primality testing, this is in P, right? This is in P. P stands for the polynomial time algorithms, right? I'm not sure if you have heard of P versus NP, right? But primality testing is in P. That means that we can check for primality in log n time, right? In order of log n time. All right, we will not be going over this particular algorithm today. So there are several algorithms. One of the most famous ones is the AKS primality test, right? Okay, but primality can be checked in order of log n. It is in P, right? And no, this is different from Sieve of Eratosthenes. Right? This is different from the Sieve algorithm. This is a different thing. Okay. Cool. So if someone asks you how much time does it take to check if a number is prime, the answer is log n. Right? You can test primality in polynomial time. Okay. Cool. Vikas says, what if n equals to 5? So Vikas has a question over here. Let us look at this code and see what happens when n equals to 5. Does this code work correctly? Right. So let us try that. So what happens? So first of all, we will say I equals to 2. Right. So we will first come over here. We will check I equals to 2. Then we will move on to the condition. We will move on to this condition. Right. That is how a for loop works. We initialize, we check the condition, we go inside the block, we increment, and we check the condition again. Right? So we will check this condition. Well, what is the square root of 5? The square root of 5 is? Well, the square root of 5 is 2 point something, right? Let us suppose that we are doing integer things over here. So we will say that, okay, this is 2 is less than equal to 2.5, right? Less than equal to 2 point something. So we will go inside. Right? We will go inside. We will check. Is n divisible by 2? Is 5 divisible by 2? No, it is not. Right? So we will continue the loop. We will increment I. I will now become 3. Now once again we will check, is 3 less than equal to square root of n? No, 3 is not less than equal to square root of n, right? 3 is greater than square root of n. So we will exit this loop and we will return true. So we will say that yes, 5 is prime, which is correct. Okay. Okay, so there's another question. Santosh says that, okay, what if 2? What if we check with n equals to 2? Right? What happens when n equals to 2? Won't this program return false? Let us see. Right? So when n equals to 2, we start. Right? We start with I equals to 2. Right? Then we move on to the condition. We check if 2 is less than equal to square root of 2. Is this true? Is 2 less than equal to square root of 2? No, it is not true. Right? This is not true. So it will directly come outside the loop. Okay, it will directly jump outside the loop. It will not go in the loop. And we will return true. So even for true, we will return true. Is that clear, Santosh? Yes. But this program is not 100% correct. This program is not 100% correct. Can you tell me one value for which this program will fail? Exactly. So Ayush has the right idea over here. What if n equals to 1? Or what if n equals to 0? Or what if n equals to minus 100? Right? For all the numbers that are less than 2, we will never go inside this loop. So we will automatically return true. Right? So we need to improve on this program. We need to add a check over here. Right? So let me just insert some space. So we will very quickly, let me just clear up the mess. This was square root of n. So we will add a check over here. We will check if n is less than or equal to 1, then we simply return false. Right? We simply return false. Right? Is this clear? No, this is not a base case. Base case happens when you are in a recursion. Right? Base case, we talk about base cases when we are in a recursion. This is a edge case. This is a boundary condition. Okay? Sujit, it's almost the same, but it is better if we follow the correct nomenclature. Okay? Base case is when we talk about recursion. Currently, we're talking about edge cases or boundary condition. All right. Yes, we can also say that this is less than 2. Right? We can, instead of saying less than equal to 1, we can also say less than 2. That is perfectly fine. All right. Okay. Let us continue. So now we know how to check if a number is prime. Now a very common question comes up. Let me just check how we are doing on time. All right. So a very common question comes up now, which is called if you had to find all the primes till n. Right? So I give you a very, very large number n, let us say 1 million. Right? And I ask you, find out all the primes till 1 million. Right? How will we do that? Is the question clear? We have to find all the primes till 1 million or some number n. So one way of doing that is to very simply go through all the numbers and check if they are prime. Right? So we can simply do for I equals to 1, I less than equal to n, I plus plus, right? And we will say if is prime. If is prime of I, right? So this is prime is the function that we have coded earlier. If this is prime is the function that we have coded earlier, we will simply print I. Simple enough? Yes. How much time will this algorithm take? How much time will this algorithm take? Well, this is prime function. This takes order of square root of I. Right? This takes order of square root of I. And we are doing this thing n times. Right? We are doing this thing n times. So how much time does it take? It definitely takes, it is bounded by, it is upper bounded by, so the time complexity of this program is upper bounded by order of n times square root of n. Right? N times square root of n. It is a little lesser than that, but as importantly, this is what the type bound is. Okay? Cool. Can we do better? Now the question is, can we do better? This was the simple approach. We had the program, we had this function is prime that we have already coded, right? And we simply say, okay, let us go through all the numbers and let us check them. So this will take this much time. The question is, can we do better? All right? Cool. So the answer to this is yes, right? In general, yes. There is something called sieve algorithms. Sieve algorithms. All right? And there's a lot of different sieve algorithms. So one of the most famous that you will come across is the sieve of Eratosthenes, right? The sieve of Eratosthenes. And this is how you pronounce the name. You say Eratosthenes. Okay? Eratosthenes. So this sieve algorithm can achieve much better time complexity. All right? Now, let us continue this particular thing in tomorrow's class. All right? We are going to keep the today's class simple enough because you will have a lot of practice problems that you can go and try it. We will talk about this sieve algorithm tomorrow. And this is a very elegant algorithm. This is a very nice algorithm. It is also very simple to code. Right? So it only has like 5 to 6 lines of code. And that gives you a very powerful algorithm that checks, that finds all the numbers, all the prime numbers up to a given number. All right? Cool. So one thing that Ankush is pointing out over here, or not this, where did that comment go? Interesting. That comment just vanished. Yes. So Ankush is pointing out over here that in this particular program that you wrote, right? In this particular program that you wrote this loop as I equals to 2 all the way till square root of n. We can rewrite this in this manner as well, right? So I'm just pointing it out over here, as Ankush said, that these two loops are equivalent. I equals to 2, I is less than equal to square root of n, right? I plus plus. This loop is the exact same as this loop for I equals to 2. I times I is less than equal to n, I plus plus. Okay, so instead of calculating the square root of n and then comparing it with I, we square I and then we compare it with n. Right? It will work exactly the same. And this is one more way that you can do it. If you were to do it this way, then you will have to pre-calculate the square root of n. Right? You will say square root of n equals to, you will use some sort of a math library. You will say math.square root of n and things like that. So if you do not want to do that, you can simply use I into I is less than equal to n. All right? Bridge says, but don't we have to check for overflow? Well, not really, Bridge, because I into I will not overflow, right? If I into I overflows, then N itself should overflow. Does that make sense? We are not really considering the overflow case over here. We're talking about not too big numbers. Okay, we are talking about numbers that will fit in the integers. Now, if n fits in your memory, if n fits in let's say a 64-bit integer, then I into I will also fit in 64-bit integer. All right. Srinivas says, sir, how to deal with very, very big numbers? Well, Srinivas, there are a lot of different ways that you can tackle big numbers. One very common approach is to use a big integer library, right? Big integer library, right? But usually this is not a very good approach, right? First of all, the question is, why would you need to deal with big numbers, right? If you are implementing, let us suppose, some sort of an RSA algorithm, and you want to check if a number is prime or not, then you might have other ways of generating large prime numbers. Right? In practice, we don't really have to deal with we don't have to check very large prime numbers with something like a sieve. Right? With something like a sieve, we don't do that. Okay. So let us end the class. Once again, please subscribe to the channel, hit the bell icon so that you can be notified of the videos. And in the next class itself, we will be going over prime numbers once again, and we will be going over a lot of different things. So we have to cover GCD, so greatest common divisor, Euclid's algorithm for that. We have to cover model arithmetic and a lot of different topics. All right, so please make sure that you subscribe to the channel, hit the bell icon, and please go and practice the problems.
Hello everyone. So in the last class, Pragya has taught you about how to check whether a number is prime or not. Okay, so is everyone clear with that? If given a number n, can you all check whether the number is prime or not? Now, once you know that whether a number is prime or not, now let's try to modify the problem a bit. Okay, so instead of getting a direct problem of checking whether a given number is prime or not, let's say that you have to print first n prime numbers. Okay, given a number n, you have to print the first n prime numbers. Or another question could be that you have to print all the prime numbers less than n. Another question would be that you have to print all the prime numbers in the range from L to R. Okay, so these are the three types of questions which we are going to solve optimally in today's class. Okay, now if you all remember, if when you have to check whether a given number is prime or not, what is the time complexity of that operation? You are going to run a loop that starts from 2, goes till square root n, right? And with every number in this range, you try to divide n, and you see whether n is divisible by that number or not. If n is divisible by none of the numbers, then you can say that n is prime. So the time complexity of this operation is order square root n, right? Now, if you have to check, if you have to print the first n prime numbers, what will be the time complexity of this approach? If you have to print first n prime numbers, you will be checking for all the possible numbers, right? You will run a loop for all numbers from 1 to n, and then you will run another loop. Maybe you will have to increase the size of the first loop because first n prime numbers might exceed n as well, right? So the time complexity of this is going to be n root n, right? For each and every number, you will be checking, you will be running a square root n check, right? Similarly, if you have to print all the prime numbers which are less than n, again, the same time complexity will be there, n root n. If you have to print all the prime numbers in the range from L to R, then again, size of range multiplied by square root n. So all these types of questions can be solved in this time complexity n into square root n using a very easy check prime algorithm that we have learned in the previous class. Okay, can we do it optimally? Can we do something to make all these problems easy for the computer? Now, there is a very, very well researched algorithm, with very famous algorithm, which many of you are already writing in the comment. It's called the Sieve's algorithm, right? So in today's class, we are going to learn about the Sieve's algorithm. Okay. Do you guys understand what is a sieve? What is the literal meaning of a sieve? If you just translate sieve in Hindi, what is that? It is nothing but a channi, right? This is chai sante hai ghar pe. So it has a net, very fine net, and a handle. Right? This is a sieve, right? And printing all the prime numbers using a sieve is going to be exactly same as how you filter your tea. Okay, we'll see how. So जब चाय छानते हैं तब क्या होता है? You have a utensil, right? In this utensil you have the cooked chai, right? And then you pour it on the sieves, and after this you have your tea mug, right? So At this point, this complete mixture is called chai, right? At this point, you say that everything which is there in the utensil is my chai. But when it is filtered, then whatever is in your teacup is called chai, right? तो पहले तो जो उसमें था पूरे को हमने बोल दिया कि यार ये चाय है, चाय बन गई है, इसको छान लेते हैं. जब छन के आई तो फिर हमने बोला यार चाय तो ये है, ये जो इसमें रह गया है ये चाय नहीं है, ये चाय पत्ती है, अदरक है, जो भी है, चाय नहीं है, है ना? So sieves is going to function in an exact same way. We have to figure out what are the prime numbers. We'll say that all the numbers are prime, right? So we'll take all the numbers and we'll say that all of them are prime. Then we will pass them through a sieves. After passing them through the sieves, we will see that only the actual prime numbers are remaining. All the composite numbers will be filtered out by the sieves. Okay. Let us see how it is going to work. So first of all, let us write down all the numbers on which we'll be running the sieves. Okay. So we have all these numbers. Initially, just like the T, I'm saying that all of them are prime. Okay, all the numbers are prime. Now for 1, we are very sure that 1 is not a prime, right? Is everyone clear with this thing that 1 is not a prime, right? Why is 1 not a prime? Because a prime number has to have exactly 2 divisors. 1 has got only exactly 1 divisor, so 1 is not a prime, so we can directly remove 1. Okay. Now whatever is the first number which is present in this in the list of all these numbers, which is available in the list, we'll say that this number is a prime number. Okay. So what is the first available number here? The first available number is 2. So I'm saying that 2 is a prime number. So we'll filter out 2. 2 comes out of the seeds. Okay. So we have poured all the numbers here till 40, and now 2 has fallen. 2 has been successfully, he has crossed the seeds. Okay. 1 has stuck here. Now, if 2 is a prime number, can I say that all the multiples of 2 will never be a prime number, right? Because all the multiples of 2 will definitely have 1 as a divisor, themselves as the divisor, and also 2 as a divisor. So they are not satisfying the criteria of being a prime number. Does this thing make sense to everyone? Does this thing sounds obvious to everyone? That any multiple of 2 can never be a prime number, right? So if any multiple of 2 can never be a prime number, so what can we do? Filter them out, cut them. So I will just cut all the multiples of 2 which are present in this list. So 4 is gone, 6 is gone, 8 is gone, 10 is gone, right? So all these multiples are removed from this list. These all have been filtered out and thrown away. What is the next available number which is there in the seeds? What is the next number that I can see? The next number is 3. So I can say that, okay, 3 is also a prime number. Let's add 3 as well. Okay. Once I am declaring that 3 is a prime number, can I say that any multiple of 3 does not stand a chance for being a prime number? Any multiple of 3 is always and always going to be a composite number, right? So let us filter them out. Let us remove them from the list. So let us remove all the multiples of 3. 6 has already been removed. Then we remove 9. 12 has already been removed. We remove 15. 18 is already gone, right? And then 21. 24 is gone. 27. And then 33. 36 is already gone. Then 39. Okay. Now, which number is the next available number in this list? The next available number is 5, right? So I can say that 5 is also a prime number. Okay. So out of all these numbers, we have till now filtered out 3 numbers which are prime numbers, right? So now 5 has come. So any multiple of 5 will never be a prime number. So all the multiples of 5 will also be removed. So currently I can see that all the multiples of 5 have already been removed. 10 is gone, 15 is gone, 20 is already gone, 25 is remaining. So we'll remove 25 as well, and then 35. Okay. Then what is the next available number in this list? The next available number here is 7. So 7 becomes the next prime number. Okay. And all the multiples of 7 will also be removed. So now 14 is gone, 21 is gone, 28 is gone. All the multiples of 7 have already been removed. Okay. What is the next available number that we have? Now we have 11. So 11 becomes the next prime number. And all the multiples of 11 again have already been removed. Then we have 13. Then we have 17. Then we have 19. Then we have 23. Then we have 29. Then we have 31, 37. And that's it. So now you can see that we have got all the prime numbers in the range from 1 to 40. These are all the prime numbers in the range. All the prime numbers which are less than 40 are now with us. Is the idea of the algorithm make sense to everyone? Is the idea clear? How the algo is going to work? Initially, we said that all the numbers are prime numbers, assume that all of them are prime numbers, pass them through the sieves. What does the sieve do for us? The sieves algorithm takes the first available number and declares it a prime number. So we declared that 2 is a prime number. Since 2 is prime number, none of its multiple can be a prime number. Cut them out, remove them. Then take whichever is the next available number, call it a prime number, remove all the multiples of this number as well. Okay. Now let's try to see how can we write the code for this. Okay, the code is going to be very, very small, very, very easy, right? So what we are doing here is initially what we are doing is we said that let us first take all the numbers. So if let's say we have to print all the prime numbers in the range n, so then we take an array prime of size n plus 1, because if n is 40, array indices are going to start from 0. So I also need 40 as an index. So I will take the size as n plus 1. Okay, and I will say that all of them are prime. Okay, so this primary, what does it hold? This primary, for every index, it holds true or false based on whether the number is prime or not, right? So currently I'm saying that if this is my array, okay, currently I'm saying that all of them are prime. So have true for each and every index. Okay, then what we will do is we'll first declare some of the already known values, right? So we know that 0 is not a prime, so we can say that prime of 0 is false. So this will be turned false, and we also know that prime of 1 is also not a prime, right? So 1 will also be converted to false. Now starting from 2 to n, we have to check each and every number whether they are prime or not. So how did we do this in this algorithm? We selected whichever is the first true value. Basically, the first available means the first true value, which is currently declared as a prime number, right? So we'll run a loop which will start from 2, and this loop will go till till n, and we'll be incrementing the value of I one by one. And then we have to check whether this value has been removed or not. So if it has not been removed, then we will always be having a true value. Okay, so we'll just check if this number at index I, if it is true, if this number is currently a prime or not. What is the first available prime number that we have here, right? If it is a prime number, this means that none of its multiple can be a prime number. So for all its multiple, make them false. So if 2 is true, 4, 6, 8, 10, all these numbers should be turned to false. So I will just run a loop. Let's take a different variable. So now what we have to do for I, we have to make 2i, 3i, 4i, all these numbers as false, right? So we'll quickly run a loop starting from 2, and we'll see till where we have to run this loop, and then do this. We'll say prime of I into j, right? So I is already there. This is our j, right? This has to be false. So we till what value we have to increase j? We don't know, right? We don't know that. So we actually don't know till when we should be incrementing j. But what we know is that this product, this 3i, 4i, or ji, this can never be greater than the maximum value that we have. So this product can never be greater than n. This always has to be less than or equal to n, right? So here what we'll have is j into I is less than or equal to n. Okay, because if you see in this list, when you select I is equal to 2, then from where to where your j ranges, j starts from 2. So if j is equal to 2, you cut 4, then j becomes 3, you cut 6, j becomes 4, you cut 8, and you will go till 40, right? So j becomes 20. You don't want to increase j such that you are trying to cut a number which is greater than 40. So always we are keeping I into j less than or equal to n. Okay, cool. Now let us see. Let us try to quickly see what happens when we are actually cutting the numbers, right? So when my I takes a value 11, okay, when I'm taking a value 11, in this case, when we selected 11, what was the first number that we tried to cut? The first number that we tried to cut was 11 into 2, which is 22, right? So if I is 11, we are going to check it for value of j is equal to 2, right? Which will give us 22. Then we will try to cut 33. Then we will try to cut 44. Then we will try to cut 55 and so on. Then j will become 11 and we'll cut 121 and so on, right? Now I have a question. When I'm trying to cut all these numbers for the value of I equals to 11, can I say that 22, 33, 44, 55, all these numbers would have already been cut? Because before I takes the value 11, I will also take the value 2. When I takes the value 2, 22 would have been cut by that, right? So you must have observed in this case also that when we reach to 11, all the multiples of 11 were already cut, right? When we reach to 5, what was the first number that we cut? 10 was already gone using 2. 15 was already gone using 3. 20 was already gone using 2. What was the first number that we cut using 5? It was 25. If I start from 11, then we can see that none of the multiple of 11 is available here, which has not been cut. All the numbers have been already cut, right? Why that happened? Because before taking a value 11, I must have taken all the values which are less than 11. So all those values have already been cut. So 22 has been cut by 2, 33 has been cut by 3, 44 has already been cut by 2, 55 has been cut by 5, and so on, right? So what should be the first value from where we should be starting the second loop? From where we should start the second loop? This has to start from j is equal to I, right? Because when we were trying to cut the numbers from 5, we saw that the first number that we are cutting is 25. Similarly, for 11, the first number which will be available there is going to be 121. All the other numbers must have been cut by the smaller values of I. So we don't need to start from 2, we can start j from I, okay? Now, if we are starting j from I, what is the maximum value that I can take? Do we need to run the first loop till n? Okay, let us try to analyze the second loop, and that will give you the answer whether we should be running the first loop till n or not. Should it go till n by 2? So what is the maximum value that we have to cut? The maximum value that we have to cut is here 40, right? Okay. And whenever you are starting to cut, you are always starting from the I value, which means that the first value that you are cutting is I square, right? For 2, you are cutting, the first value that is being cut is 4, right? For 3, the first value that you are cutting is 9. For 5, the first value that you are cutting is 25. For 6, the first value that you will be cutting is, for 6, you will anyhow won't cut any value. For 7, what will be the first value that you will be cutting? For 7, the first value should be 49. 7 into 7 is 49. Is 49 in this range? No, 49 is out of this range. So what should be the maximum value? The maximum value till which we can go is I square. So I can never go beyond square root n, right? Because the first number that you are cutting here, like this number, which is the last number, would have been cut when I becomes square root n, right? So this n can be turned to square root n. Right, so either you can say I is less than equal to square root n, but if you are using this function square root n, this is an expensive operation of finding a square root of a number is actually an expensive operation. It will take at least log n time. So what you can do is you can replace this by I into I less than equal to n. So now you are doing the checking order 1 operation. This is going to take log n time, at least if you are printing the integer part, right, using binary search. Okay. So now let us come to the time complexity. Okay. This loop, the first loop is running from 2 to square root of n. Let us actually remove all the optimizations that we have done. We'll try to calculate a very relaxed upper bound. Okay. So tell me one thing. When the value of I is equal to 2, how many times does the inner loop run? If let us say that this starts from 2, if we are considering the previous loop, the totally unoptimized loop, which was starting from 2 and going till n, and this loop is also going till n, we are considering the most unoptimized version. Now tell me, if value of I is equal to 2, how many times are we going to run this loop? This loop will start from 2, go till n by 2, right? We'll be cutting exactly n by 2 numbers For I is equal to 3, how many times is the inner loop going to run? The inner loop is going to run for n by 3 times. For I equals to 4, how many times is the inner loop going to run? For I equals to 4, is it going to run for n by 4 times? For I equals to 4. So see what happens is when I takes a value 2, we cut 4. We say that now 4 is not a prime because 4 is a multiple of 2. And before running this loop, we are always checking whether I is prime or not. Is 4 a prime? No, 4 is not a prime. So this loop, the inner loop is going to run how many times? Exactly 0 times. This if case is going to fail for 4, right? For 5, it is going to run for n by 5 times. For 6, this is going to run for, again, 0 times. 6 is not a prime. For 7, this is going to run for n by 7 times, right? So can you see a pattern here? If we have to add all these time complexities, what will we get? We'll be getting n by 2 plus n by 3 plus n by 5 plus n by 7 and so on. What are these? If you take n common from here, you get 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus 1 by 11 plus 1 by 13 and so on. What are all these? These are nothing but sum of reciprocals of prime numbers, right? First n prime numbers basically, correct? So I can say this is equal to I equals to 1 to n 1 by p. All the prime numbers, the first n prime numbers, or maybe all the prime numbers which are less than n, right? All the prime numbers which are less than n. This is the time complexity. Now, if you are really good at mathematics, you will be able to you will be knowing that this whole sum can be approximated to log of n. Okay, so this is the overall time complexity of Sieve's algorithm. Okay, so if you are really good or if you are interested in mathematics, you can read about the Merton's theorem, which proves this thing. Okay, that sum of reciprocal of first n prime numbers is same as log of n. So the overall time complexity can be approximated as order of n into log of n. Okay. Okay, I will quickly brief over the time complexity part once again. Okay, so if we are just checking for every value of I, how many times is the inner loop going to run? Okay, so I said that if I is equal to 2, how many times is the inner loop going to run? Inner loop is going to start from 2. We are assuming the most unoptimized version. We are removing all the optimizations that we had done. So inner loop will start from 2 and it will run for n by 2 times, right? If you are starting from 2 and you have to go till 40, you will be running 20 times, right? You will cut 20 numbers in this loop. Similarly, for I equals to 3, you will be running the inner loop for n by 3 times. For I equals to 4, now this is a very important thing that before running the inner loop, you always check whether this number is prime or not. 4 is not a prime. So for 4, the inner loop will never run. For I equals to 5, the loop runs for n by 2, n by 5. Then for 6, again, since 6 is composite, loop does not run. Then for I equals to 7, loop runs for n by 7 and so on. So if you add all of them, right, because when you have to calculate the time complexity, you will be adding how many times the inner loop is running in total, right? And that will be the overall time complexity. So if you add all of them, you get this series. Here, if you take n common, then you get something which is nothing but the sum of reciprocal of all the prime numbers. And if you apply Merton's theorem, if you are aware about the Merton's theorem, you will be knowing that sum of reciprocal of all the prime numbers can be approximated as log of n. So that is why the time complexity of Sieve's algorithm is order of n log of n. Okay. Now this is the most relaxed time complexity that we have achieved because we removed all the optimizations, right? The optimization that says that the first loop should run only till square root of time. This loop should start from I. We have removed all of them and then we have calculated. So whatever, if you do any optimization here, your algo is definitely going to be better than this time complexity. Okay. The question is, will this work for a range whose first element is not a prime number? This is only going to work if you are starting it from 2. If you are starting from any random number, this algorithm is never going to work, right? Because you have to make sure that all the composite numbers are cut. So if let's say if you are trying to find the numbers in the range from 40 to 100, right? So you have these numbers, and now if you start cutting the numbers from from 40, you're trying to cut the multiples of 40. This is not what Sieves is suggesting. Sieves is saying, give me the first prime number. What is the first prime number? First prime number is 2. Cut all the multiples of the first prime number, not the first prime number in this range, the first prime number overall, right? So you will always be starting, or this algorithm will only work if you are starting cutting the numbers from 2. However, if you have to find the numbers in a range, what you can do is you can pre-compute all the prime numbers. So what you can do is, if you have what would be the maximum value of range, then starting from 2 to that range, you can pre-compute all the prime numbers. Okay. Once you have all the prime numbers in this range, now what you can do is you can this array is going to be a sorted array, so you can apply binary search and you can find all the positions of the lth prime number and rth prime number and print all the values. Okay. Cool. Is the Sieves algorithm clear to everyone, including the idea, the intuition, and the code? Is everything clear to everyone? Great. Now what we'll do is we'll try to see a problem. Okay. So we still have 30 minutes. So we'll try to solve a very, very good problem, which is a very commonly asked problem and a very generic problem. Okay. The problem says that given a number, return the prime factorization of this number. What is prime factorization? So is everyone here clear with the thing that any composite number can be written as the multiple of all prime numbers? Not all prime numbers, but multiple of prime numbers. Is everyone clear with this thing? So if I give you n is equal to 24, what would be the prime factorization of 24? 24 can be written as 2 into 2 into 2 into 3. Basically 8 3s are 24, right? So 8 is nothing but 2 raised to power 3. So 24 can be written as this. So the prime factorization of 24 would be 2, 2, 2, and 3. This is what you have to return. Okay, is the problem clear to everyone? If the value of n, let's say, is 10, you will be returning 2 into 5. Okay. If the value of n, let's say, is 42, then we have 2, 3, and 7. Okay. Is the problem clear to everyone? Given a number n, you have to return the prime factorization of n. Prime factorization means you have to represent that number in terms of only prime numbers, and that is possible for each and every number, right? Because any number either will be a prime number or a composite number. If it is a composite number, you can further divide it into prime numbers, right? For example, if n is 24, you can write it as 2 to 2 into 3. There can be many ways. Can there be many ways? Varun, just try to think and figure out. Can there be many ways? If you are breaking down the number into prime numbers, not composite number, none of the numbers in the returned array should be a composite number. Okay, what can be? What is the first thing that comes to the mind? So if, let's say, I'm given 24 and I have to, so we must have done this in schools, right? We all have done the prime factorization of the number in school in the elementary mathematics, right? This was, I think, in 6th class maybe or 5th class when we learned about the prime numbers, right? So how did we used to do it at that time? So if I'm given 24, what will I try to do? I will pick what is the smallest number with which I can divide it, right? So the smallest number that I can figure out is 2. So I will try to divide 24 with 2. I get 12, okay? And this 2 gets added to my answer. Now I have got 12, and I know that again I have to do the exact same thing. Find the smallest number with which I can divide this, and that number obviously should be greater than 1, right? So again, here also the smallest number that I can think of is 2. So I divide it with 2, I get 6. Again, I can divide it with 2, so I get 3. Now 3, the smallest number that can divide 3, bigger than 1 is 3, so I get finally 1. All these numbers are definitely going to be a prime number because we are always selecting the smallest number, right? If that smallest number is not a prime number, then there must be a number which is smaller than this that can divide this number. Does this make sense to everyone? What I'm trying to say is, if there is a number x, which is the smallest number, which is dividing 24, and x is not a prime number. If it is not a prime number, then it must be a composite number, and then it can be broken down into 2 prime numbers at least, right? So 24 will also be divisible by these two. So that means x was not the smallest number that can divide it. There are smaller number than x which can divide 24. So using this proof by contradiction, I can always say that the smallest number which is able to divide any number is going to be a prime number. Okay. Now, how to code this thing? I'm just going to code the same approach that we used in our 5th, 6th class mathematics, right? So to do this, first we can initialize an answer array or maybe a prime factor array. And what we are going to do is, so here in this case, I just used my mind and saw that this is divisible by 2. But for computer, we'll have to check with every number starting from 2, right? What is the first number that divides 24? And then keep dividing it by that number till it is divisible, right? So I will start from 2 and I will say that this has to go till somewhere and then I plus plus. And then I will say while this is divisible, if it is not divisible, then it will not go inside the loop. But if it is divisible, first of all, add this I to the answer. So we'll do prime fact dot add I. Okay, add this to the answer and then divide n. So n will become n by I. Okay. So what we are doing in this case is n is initially 24, right? We are starting from I, and we are and the first value of I is 2. So we are checking if it is divisible. If it is divisible, then keep dividing it till it is divisible. So we divide it, make it 12, n becomes 12. Then the loop still checks that this is still divisible by 2. So keep dividing it, and also keep adding it to the answer. So the answer will have 2, then in the next step again 2, and then again 2. Then you have 3. So this will break out because now n mod 3 is not divisible. Sorry, n mod 2 is not divisible. N has now become 3, right? 3 mod 2 is not equal to 0. So we'll increment the value of I. So I now becomes 3. So then we'll check n mod 3 is now divisible. So we'll add 3 to this and we'll divide n further. So now n becomes 1. Okay. So the question is, till when this loop should run? What should be the breaking condition here? What can be the maximum number that I can take? The maximum number that I can take is, we may use set instead of array. No, you cannot take set, because set will guarantee that the occurrence of every number will be limited to exactly once, whereas we need 3 2s. If you are taking a set, you will have exactly 1 2, right? So set is not useful in this case. We'll have to take a list, array list, or array which supports multiple occurrences of same character, right? Okay, so what should be the maximum value that I can take? The maximum value that I can take obviously is going to be square root of n, right? So the I that we are going to increment is going to be till square root of n. Okay. Now this code is going to print all the prime factors for us. I can see that there are 2 mistakes in this code, 2 very big mistakes. Can you guys quickly figure out them? This code has 2 blunders, and one of them is the most commonly done mistake while writing a code. Even when people write the most simplest of the codes, they make this type of mistakes. Can you quickly figure that out? It doesn't work for 0 and 1. Yes, so this is guaranteed in the input that n will always be greater than 1, because even the person who is asking the question knows that 0 and 1 will not be are not eligible for this question. Okay, right. So I can see that one of the mistake has been pointed out. The other mistake no one is able to guess. Let us see what we are doing. Let us quickly reiterate over the code. We are saying that I is starting from 2. I should go. What is the maximum limit that I is taking? It is taking square root of n. So here, instead of this, I would be writing what? Actually square root of n, or maybe to keep it optimized, let us have I into I less than equal to n, right? This is the more optimized version of the same thing. Okay. So what we are doing here is we are initializing I. We are checking that I should not go more than square root of n. And inside this loop, what we are doing is we are changing the value of n, correct? N is changed inside this loop. N is also there in the breaking condition. So initially we started this loop with an assumption that n is going to be 24. So the maximum value that I can take is going to be root 24. In the next iteration, you changed n to 12. So this loop here, now this condition is not going to hold true because n has been changed. This is the most common mistake that I have seen students doing while writing most easiest of the codes. If you are changing a value inside the loop, you should never be taking it in the breaking condition. So always do one thing, assign some variable this value and then use it here. Okay. Otherwise, you will see your code behaving in very unexpected way and you will not be able to realize what is going wrong there. Okay. So assign the value and then keep it inside the loop. This is one mistake. What is the other mistake? The other mistake most of you have already pointed out, which is if the number is already prime, right? If the number is already prime, or maybe number is having the number is having a prime factor which is greater than square root of n, right? If a number is having a prime factor which is greater than square root of n, for example, let us talk about 404. Okay, so for 404, how will this loop run? We'll start from 2. We check that 404 is divisible by 2. We divide it. Okay. Then we again check that this is again divisible by 2. We divide it. Now this is not. So we have added 2 and 2 in the array. Now this is not divisible by 2. Then this is not divisible by 3. And what would be the maximum value of that I will be taking in case of 404? The maximum value that I can take is going to be 20, right? Because the square of 21 is going to be greater than 404, right? So the maximum value of I is going to be 20, but we can see that for all these values of I, the prime factorization of 404 is not complete, right? So what we can say in this case, right? Because this is not complete. 101 would also have been there, correct? So this is another mistake in this code. How to fix that mistake? Can I say that even after removing all the possible prime factors from that number, if I have got a number which is greater than 1, that number must be a prime number? Can I say this? So to actually fix this code, can I just add another if condition? It says that if this number is still not reduced to 1, that means that this number has to be a prime number. So directly add this remaining number as well. So what we'll do here is if n greater than 1, then prime factor dot add n. We'll add this line here itself after the for loop completes. So if this number is not been reduced to 1, we will add 101 as well, and we will get the correct answer. Does this make sense to everyone? So this is about prime factorization. What is going to be the time complexity here? What is the time complexity of this code? So calculating the time complexity is pretty easy here, right? The first loop runs for how many times? The first loop runs for root n time. Okay. Then the second loop runs for, the second loop is going to run for how many times? We are dividing the number n by I every time in every iteration. So how many times the second loop is going to run? The second loop is going to run for log n time. So what should be the time complexity? Is it going to be root n into log n? Is the time complexity going to be root n into log n? No, right? This is wrong. This is not going to be root n multiplied by log n. Okay, why? We can quickly see that this loop runs for root n times, and here we are dividing the number by I every time. In the worst case, the value of I is going to be 2. So in the worst case, if you are dividing n by I, how many times can you divide it? If given a number, how many times can you divide that by 2? This is given by log, right? This is given by log of 16. Log, whatever is the value of log of 16, you can divide 16 that many times by 2, right? But this is incorrect. Why? So let us try to analyze what is going on here. So if we have a value, let's take 16 itself. Okay, so in the first iteration, when the value of I is equal to 2, we check that this is divisible and we divide it. So we get 8. Then again we divide it by 2, we get 4. Again we divide it by 2, we get 2. Again we divide it by 2, we get 1. Okay. Now after we have divided completely with 2, for the next value of I, which is equal to 3, how many times is the inner loop going to run? For 3, how many times is the inner loop going to run? 0 times, right? Inner loop is not going to run because this has already been reduced to 1. Okay. If this has already been reduced to 1, now this inner loop will never run again. If this inner loop is not going to run again, for 3, number of iterations are going to be 0. For 4, the number of iterations are going to be 0, right? So what is the total number of times, including all i's, the inner loop is running? For all the i's, the inner loop is going to run for log n time. This is not for each and every I. This is for all the i's combined. For 2, it runs for log base 2n. Then for 3, it runs for log base 3n if n is there, right? So if let us talk about any other number. So if I talk about 24, 2 can reduce it to 12, then 2 can reduce it to 6, then 2 can reduce it to 3. Now 3 is not going to have log base 3 24, these many steps, because 3 is going to reduce this number, which has already been reduced by 2, right? So the total number of steps, including all the i's combined, is going to be log of n. So this is going to be log of n plus square root of n, which is nothing but square root of n. So the time complexity of this algorithm is going to be exactly square root of n, not root n log n. Okay. Guys, in mathematics, there are multiple topics which are very, very important for programming point of view, or both the interview point of view as well, right? So there is modular arithmetic that you must learn, and you must solve multiple problems on this. Okay. Then there is GCD, the LCM and HCF problems. Okay, GCD is also very, very important concept. Okay. Then of course you definitely have the prime numbers, and in the prime numbers you can also optimize this approach that we have discussed, right? You can optimize this approach using a concept called the smallest prime factor of a number, which is called the SPF, which we haven't discussed in the class, but this is also a very important concept. Okay, so after the class, please go through this, what is SPF and how you can actually optimize this algorithm using the smallest prime factor. Okay. And then in the modular arithmetics, there is also Fermat theorem, which is very important. So just Google all these concepts and go through all of them. Try to solve problem based on all of them. Okay, they all are very, very important. They will help you in problem solving as well as in interviews. Okay, cool. So this is it for today's class. If you liked the video, if you understood everything, please like, please share it with your friends. Please tell us in comment which all topics you would want us to discuss next. Okay. Tomorrow's class is going to be on bit manipulation. So if possible, before joining the class, if you can go through how numbers are represented or what are the basic bit operations, then the class will go very smoothly, right? So next class is going to be on bit manipulation. So just read about some bitwise operators like OR, AND, XOR, left shift, right shift, etc. Just read about them. And if you found this video useful, you can just like it and share it with your friends. Okay.
Hey guys, I'm Bhavya. In this video, I will discuss the day 1 problems of code drift on 2 pointers. So let's look at the very easy problem, the first problem. Given an integer array A consisting of distinct elements, you are asked to create a lexicographically largest array S equal to X plus reverse Y, such that it satisfies the following conditions. Length of S is less than equal to length of A, and X is the prefix array of A, and Y is the suffix array of A. X or Y can be empty as well. Length of A is less than equal to 10 to the power 5 and A is less than equal to 10 to the power 9. So for the first case, 4, 1, 3, 2, we can choose X as 4 and Y as 1, 3, 2. Now reverse Y will be 2, 3, 1. So X plus reverse Y will be 4, 2, 3, 1. Similarly, in the second case, 10, 20, 30, 40, we can choose X as an empty array and Y as 10, 20, 30, 40, which is a suffix. So X plus reverse Y will be 40, 30, 20, 10, which is the lexicographically maximum array. So let's look at the solution approach. Now let's actually take an example. So we have 5, 3, 2, 1, 4. So this is our array. So first thing to observe is, since we want the lexicographically largest array, and we will place some prefix and reverse of some suffix. So if we consider reverse of some suffix, the first element will be 4 in that, right? The first element will be 4 in that. Now we want the bigger elements to appear in the initial positions. So we can actually take the elements greedily. So if our element is greater than or equal to 4, we will keep taking the elements. Since the array only has distinct elements, we don't have to actually care about equal. So if our elements is greater than 4, we will keep taking the prefix. So we'll take 5. Now 3 is actually lesser. So it will be better to place the reverse of a suffix, because if we place a reverse of a suffix, we will get 4 here. And if we keep taking the prefix, we will get 3 here. So it will be better to choose 5 as x, and we can choose y as some suffix. No matter what suffix we choose, we will get 4 here, which will be better than choosing x as 5, 3, right? So that actually gives us a greedy algorithm that we will keep taking the first elements if it is greater than the last element. So for example, the last element is 4. Now 5 is greater than 4, so we'll take it. But now 3 is not greater than 4. So now we will take a suffix and reverse it. So it will have 4. Now is it beneficial to take 1? So we can also take 1 as well. So instead of saying that we are reversing the suffix, we can say that we are taking elements from last. Now as you can see that 5, 4, 1 will be lexicographically greater than 5, 4. So it will be better to take 1 as well. So 5, 4, 1, and similarly we can take 2 as well. So 5, 4, 1, 2, and 3. So from this you can observe that our algorithm is, as long as the prefix contains element greater than the last element, we will keep taking it, and finally we will take the remaining elements in reverse order. So let's actually see one more example. So let's say in that case our array was 3, 5, 4, 1, 2, right? Now 3 is greater than 2, so we'll take 3. Again 5 is greater than 2, so we'll take 5. Again 4 is greater than 2, so we'll take 4. But now 1 is not greater than 2, so we'll now take the suffix, and so we are left with only 2 elements, so we'll place them in reverse order, that is 2, 1. So this is the lexicographically largest array which we can get. So we can just keep one pointer and keep checking if it is less than the last element. So let's actually look at the implementation. So we initialize n as the size of the array. Now left pointer is 0, that means it points to the leftmost element. So we'll keep taking elements from the left as long as it is greater than the last element. So answer is the answer, which is the lexicographically largest array. Now while L is less than n, if AL is less than AN minus 1, that is our left element is smaller, so we'll break because we are done taking all the greater elements. Otherwise we'll just take AL, since AL is greater than AN minus 1, and after taking AL we will increment our left pointer. Finally we'll just take all the elements from n minus 1 to L and append it to our answer, and we will return our answer. So what will the time complexity? So since we are taking each element at most once, so time complexity will be O of n, because our left pointer can be n in the worst case, so which will be O of n. So let's move to the next problem, medium problem. Rishabh and Ojas are on a mission. There is a bomb which they want to defuse, but the problem is they have to solve a task first, which is very difficult for them. As you are their friend, they ask you to solve the problem for them. Given an integer array A containing n integers, you need to find the number of scalar subarrays in A. A subarray is called scalar subarray if there are exactly B elements in the subarray which occur at least 2 times. So we need to find the number of subarrays which contain exactly B elements which occur at least 2 times. So n is less than equal to n to the power 5, AI is less than equal to 1000, and B is less than equal to n. So for the first case, 1, 2, 3, 1, 2, 3, there are only 2 scalar subarrays, A 0 to 4, 1, 2, 3, 1, 2. So 1 and 2 have occurrence greater than 2, greater than or equal to 2 rather. So there are exactly 2 elements which have occurrence, which have at least 2 occurrence. Similarly, A 1 to 5 will have 2, 3, 1, 2, 3. So 2 and 3 have at least occurrence 2. So there are exactly 2 elements which have at least 2 occurrences. So let's look at the solution approach using the same example. So we'll take the same example, 1, 2, 3, 1, 2, 3. So we have 1, 2, 3, 1, 2, 3. This is our array. And B is 2. That is, we want exactly 2 occurrence. So the first thing to observe is, we can actually get rid of this exact thing. Let's say FB finds the number of subarrays which have at most B occurrences of elements which occur at least twice. So now our answer will be F of B minus F of B minus 1. So here there are at most B elements. Here there are at most B minus 1 elements. So their difference will contain the subarrays which contain exactly B elements which occur at least twice. So now that we have changed our question, so now our question is, we need to find the number of subarrays which contain at most B occurrences of elements which occur at least twice. So that might sound confusing. So actually let's look at some example. So now we need to find F of B minus F of A and F of B minus F of B minus 1. So we need to find F of 2 minus F of 1. So let's actually call the elements whose frequency is at least 2 special elements. So now this will contain subarrays which have at most 2 special elements. This will contain subarrays which have at most 1 special element. So we will use a technique called 2 pointers. Now the idea this technique can be used is because for each left pointer L, we'll find the rightmost pointer such that the subarray L to R contains at most B special elements, right? Because if the subarray L to R contains at most B special elements, the subarray L to R minus 1 will definitely contain at most B special elements, since we have actually reduced one element. So if the subarray L to R is a valid subarray, the subarray L to all the subarrays from L to X says that X is between L to R will be special. Now one more thing is, if L to R contains at most B special elements, then the subarray L plus 1 to R will also contain at most B special elements, because we have actually removed some element. So it will definitely decrease some frequency. So we won't have more elements which occur at least twice. So that actually gives us idea for 2 pointers. So as we increase our left pointer, our right pointer will definitely not decrease. So it is non-decreasing. Right pointer is non-decreasing. It can increase, but it won't decrease. So now let's actually look at this idea on this example. So we need to find F of 2 and then F of 1. So let's first find F of 2. That is, there will be at most 2 special elements, and special elements are elements whose frequency is at most 2. So let's actually consider 0 indexed array. So we have 1, 1, 2, 3, 1, 2, 3. Currently, the left pointer is at 1, and let's say right pointer is -1, and it is 0 index. So we have 0, 1, 2, 3, 4, 5. So right pointer is initially previous. So this is L and this is R. Now we are actually checking if we can take R plus 1th element or not. Let's actually keep a variable occurrence, which is initially 0, which keeps the count of number of special elements. And let's actually store the frequencies of elements as well. So F will store the frequencies of elements as well. So currently we only have 3 elements. So let's say it will store the frequencies of 1, 2, and 3. Now first we'll check if we can actually take R plus 1th element or not. So if by taking R plus 1th element, the number of occurrences of special elements exceeds 2, because we are actually finding f of 2 now. So it should not exceed 2. So since the number of occurrences of special elements is 0, we can actually take the R plus 1th element. So we'll increment our R right pointer. So now right pointer points here. Also will increase the frequency of 1 as 1. Now OCC will still be 0 because there are 0 elements whose frequency is at least 2. As soon as the frequency of any element becomes equal to 2, we will increment occurrence by 1. Now we want to check if we can take the next element, which is 2. So since the frequency of 2 is currently 0, we can actually take 2 because taking 2 won't change the value of occurrence, and we want that the value of occurrence should not exceed 2 because 2 is the maximum limit because we are finding f of 2. So we can actually take f of 2 as well. So we'll increment our right pointer now, and also we will increment the frequency of 2 as well because currently now the frequency of 2 is 1. Now similarly we can again increment our right pointer since element 3 has frequency 0. So this will be now 1. Now again we can increment our right pointer because it increases the frequency of 1 to 2. So now the frequency of 1 is 2 and the number of occurrences will be 1 because there is at least one element whose frequency is at least 2. So there is one special element. Now again we can increment our right pointer because it will make the frequency of 2 and increment the number of occurrences to 2. So we can have actually 2 special elements. So it is fine to increment the right pointer. So now the frequency of 2 will be 2 and the number of occurrences will be 2. But now notice that we cannot increment our right pointer further because if we increment our right pointer further, the frequency of 3 will be 2 and the number of occurrences will be 3 now. And we know that the number of occurrences cannot exceed 2. So this is the maximum right value which we can get. So now one thing you can notice is the subarray 0 to 4 is good. That is, it satisfies the condition that there are at most be occurrences. So if the subarray 0 to 4 is good, any subarray from let's say 0 to 0, 0 to 1, 0 to 2, 0 to 3 and 0 to 4, all of them will be good. So we will add 4 minus 0 plus 1, that is 5 to our answer. We need to find f of 2, so currently f of 2 is 5. Now we will, since we have processed this current L, we will increment our L. So now we've incremented our L and now we need to remove the contribution of this one. So we'll reduce the frequency of 1, and since the frequency of 1 is 1 now, so the number of special elements will also decrease. So now let's see if we can increment our right pointer. So if we increment our right pointer, the frequency of 3 will become 2 and the number of occurrences will be 2 now, which is fine because the number of occurrences can be at most 2. So we can actually move our right pointer here. So now the occurrences of 3 will be 2 and this will be 2 as well. So after processing this, we will add 5 minus 1 plus 1, that is 5 to our answer. So answer will be 10 now. Now we will increment our left pointer and then decrease the frequency of 2. So the frequency of 2 will be 1 now. Also this will decrease the occurrence value to 1. Now notice that we cannot actually increment our right pointer because it will take us to outside of this array. So we'll just simply add 5 minus 2 plus 1, that is 4 to our answer. So answer will be 14 now. And now let's increment our left pointer. So that this decreases the frequency of 3 to 1 as well. So now the number of occurrences will be 0. Occurrences of special elements, that is elements whose frequency is at least 2. Again we will add 5 minus 3 plus 1, that is 3 to our answer. So answer will be 17 now. Since we cannot increment our right pointer, so we are done. And now we'll increment our left pointer. Again, we cannot increment our right pointer, so we'll add 5 minus 4 plus 1, that is 2 to our answer. So answer will be 19. And then increment our left pointer. Now similarly, we'll simply add 5 minus 5 plus 1, that is 1 to our answer. So answer will be 20. And we have completely processed the array. So f of 2 will return 20. That is, there are 20 subarrays which have at most 2 special elements. That is, elements whose frequency is at least 2. So now we will find f of 1 and subtract them, which will be our answer. So let's find f of 1. So we will again set r as minus 1 and the frequencies of all the elements will be 0 initially. 0, 0, 0 and answer is also 0. So currently left pointer is at 1 and right pointer is at minus 1. So we can actually take r plus 1 value, that is 0th value, because that will increase the frequency of 1 to 1 but won't change the occurrences and won't exceed it than 1, right? So this will be 1, the frequency of 1 will be 1 and occurrence will be 0. Again, can we further increase our right pointer? We can actually. So we'll increment our right pointer and increment the frequency of 2 as 1. Similarly, then this will not change the occurrence. Similarly, we'll move to the next pointer and increment the frequency of 3 as 1. And this won't change the occurrences. Now we will increment our right pointer and change the frequency of 1 as 2. And this will actually change occurrence to 1. But now we cannot actually increment our right pointer since it will increase the frequency of 2 to 2 and increment the number of occurrences to 2. And we can have at most 1 occurrences of special elements. So the rightmost pointer for 0 is 3. So we'll simply add 3 minus 0 plus 1, that is 4 to our answer. Now we will increment our left pointer and decrease the frequency of 1 as 1 and change this occurrence to 0, because now we have 0 elements whose frequency is greater than or equal to 2. Now can we increment our right pointer? We actually can. So we'll increment our right pointer and change the frequency of 2 to 2. And this will increment occurrence to 1. Can we further increase our right pointer? We cannot actually, because the frequency of 3 is 1 currently. And if we increment our right pointer, frequency of 3 will become 2, and this will increment the number of occurrences to 2. So we will simply add 4 minus 1 plus 1, that is 4 to our answer. So answer becomes 8. And we will increment our left pointer. So after incrementing our left pointer, we will decrease the frequency of 2. So the frequency of 2 will become 1, and this will decrease the number of occurrences to 0. So now can we actually increment our right pointer? We actually can. So we'll increment our right pointer, which will increase the frequency of 3 to 2. And this will increment the number of occurrences to 1. But now, since we are at the last element, we cannot increment our right pointer further. So we'll simply add 5 minus 2 plus 1, that is 4 to our answers. So this will be 12. Now we will increment our left pointer, and this will actually decrease the frequency of 3 to 1 and decrease the occurrence to 0. Because we have 0 occurrences of elements whose frequency is at least 2. So now we cannot increment our right pointer. So we'll simply add 5 minus 3 plus 1, that is 3 to our answer. So this will be 15. So we'll increment our left pointer and decrease the frequency of 1. So which will be 0 now. Now we will simply add 5 minus 4 plus 1, that is 2 to our answer. So this will be 17. And then we will increment our left pointer and decrease the frequency of 2 to 0. So again, we will simply add 5 minus 5 plus 1, that is 1 to our answer, which will make the answer as 18. So now we are done. So f of 2 is 20 and f of 1 is 18. So our answer will be 20 minus 18, that is 2. So simply return 2 as our answer. So let's actually look at how to implement this. Good thing about 2 pointers is that you can actually use the same implementation for almost all 2 pointers problem. You can actually kind of follow standard template for solving these problems. So we know that answer is f of b minus f of b minus 1. So we simply need to find f of b. So let's find f of b. So we initialize n as the size of the array. Answer is 0. So count occurrence actually stores the frequency of all the elements. Now occurrence is the count of special elements, that is elements whose frequency is at least 2. We initialize r as minus 1. Now our left pointer will go from 0 to n. So I actually denotes the movement of left pointer. Now while r plus 1 is less than n, that is r plus 1th element exists in the array. It is not outside the array. Now we need to check if we can actually take the r plus 1th element or not. So when can't we take the r plus 1th element? When it increases the number of occurrences more than b, right? So when will the number of occurrences will be more than b? If the frequency of the element which we are taking is equal to 1. So if we take the element, the frequency will be equal to 2. So this will change the number, this occurrence value. This will increment the occurrences value by 1. So if our current occurrence value is b, it will be b plus 1 now if we take this element. So this is a case where we cannot actually take the r plus 1th element and we will break it. Otherwise, we will increment r and increment the frequency of ar. If the frequency is equal to 2, we increment the occurrences, because now we have one more special element. And we simply add r minus I plus 1 to our answer. Now after processing it, we increment our left pointer. So we decrement the frequency of the ith element. And if this frequency actually becomes equal to 1, that is it was 2, now it is 1. So this actually decreases the number of elements whose frequency is at least 2. So now we will decrement our occurrence variable and we will simply return the answer. So I hope this was clear to you. Thank you for watching this video. In this video, I will discuss the easy problem and the hard problem of code drift 2 pointers. So let's look at the easy problem. You are given an integer array containing n integers. You can remove at most one subarray from it such that the remaining elements must occur at most 2 times. Find the minimum size of this subarray you need to remove such that the remaining elements must occur for at most 2 times. So n is less than equal to 10 to the power 5 and ai is less than equal to 10 to the power 9. So for example, if a is 11122, then we can remove the subarray 223 and we will get 1122. And in this array 1122, no element occurs more than 2 times. So the answer will be 2. The minimum length subarray will be 2. Obviously, an answer will exist because we can delete the entire array and get an answer. So let's look at the solution approach. Now, let's actually take the same example, 111222. So one thing you can notice is, let's first keep a variable occurrence which finds the initial number of elements whose frequency is greater than 2. So for example, in this case, there are 2 elements whose frequency is greater than 2. We can actually find those elements by, let's say, keeping a frequency array, and when the frequency becomes equal to 3. So we know that when the frequency becomes equal to 3, we can increase our count because it went from 2 to 3. So there are occurrence plus 1 elements now whose frequency is greater than 2. So if this variable occurrence is equal to 0, if this is equal to 0, it means that there are no elements such that they have a frequency which is greater than 2. Then we can simply return that the answer is 0 because we don't have to delete any subarray. Otherwise, we need to find a subarray of minimum length such that if we delete it, there is no elements whose frequency is greater than 2. So since we need to delete a subarray, let's say we will keep a frequency as well. So this is the frequency array. The frequency of 1 is 2 and the frequency of the frequency of 1 is 3 and the frequency of 2 is also 3. So since we are deleting a subarray, we know that a subarray will be of like L2R. It will have a left range and a right range. So we can actually iterate over all the possible values of L. But now we also need to find R. So how do we do that? Actually, it turns out that we can do that using 2 pointers because L2R represents the deleted range. So for example, if we found the R for a given L and we need to find the R for L plus 1, how do we find that R? That means we need to find the R dash such that if we delete L plus 1 to R dash, we get a subarray in which no element has occurrence greater than 2. So one thing you can notice is that R dash will be greater than or equal to R. That is, the right pointer will be non-decreasing. So if it is non-decreasing, then we know that our right pointer can increase at most n times, and in which case the complexity will be on. But how do we actually prove that the right pointer will definitely increase? So we know that if we delete the element L to R, no element has frequency greater than 2. Now consider L plus 1 to R. So we have added the element AL. Since we have added the element AL, if the frequency of AL becomes greater than 2, that means we need to increase our right range because we need to delete some elements until we reach AL because the frequency of AL is greater than 2 now. Otherwise, the frequency of AL is still less than 2, less than or equal to 2. That means there are no elements whose frequency is greater than 2 in L plus 1 to R. And in that case, our right end will stay same. So our right end can either increase or stay same. So that is the idea of 2 pointers. So let's actually try this in this example to understand it more clearly. So we first store the frequency of 1 and 2, which will be 3 and 3 initially. Now we assign right index as -1. So our right index is currently pointing here. And this is our current, let's say right pointer is face downwards and this is our current left pointer. Now occurrence stores the initial numbers whose frequency is greater than 2. So we'll try to include the next element R plus 1 at 0th index. That means we'll try to delete it until the occurrence becomes equal to 0. So if we delete this, R comes here and the frequency of 1 becomes 2. So since the frequency of 1 becomes 2 now, we will decrease the occurrences as 1 because there is only one element whose frequency is greater than 2. But still, we want occurrence to be 0, this variable OCC to be 0, so we'll further increase our right pointer. So we will move here and decrease the frequency of 1 as 1. Now notice that the frequency of occurrence will remain 1 because it moved from 2 to 1. So if the frequency moved from 2 to 1, then it was obvious that we haven't considered its value in this occurrence variable. So again, we'll try to increment our right pointer. So this frequency becomes equal to 0, but we don't update the occurrence value. Again, we move our right pointer and decrease the frequency of 2 as 2, and this occurrence becomes equal to 0. So now, since the occurrence is equal to 0, we stop for this left pointer because for the first left pointer, we have found the right pointer such that if we delete the subarray, we get no element whose frequency is greater than 2. So for L equal to 0, we get R as 3. So we'll simply update 3 minus 0 plus 1 as one of our answers. So initially, let's say we set answer to N, which is 6 in this case. So we'll update our answer as 4. Now we will increment our left pointer. So if we increment our left pointer, that means we have added this element because we deleted the elements from 0 to 3. If we move from 0 to 3 to 1 to 3, that means we added the A0th element. So we'll increase the frequency of 1, which we added again. So the frequency of 1 becomes 1 now. Still the occurrence is 0. So we'll update our answer as 1 minus 3 minus 1 plus 1 because L is 1 and R is 3. So we'll update this as 3. Answer will be 3 now. Again, we will increment our left pointer and increase the frequency of 1 to 2. Still the variable occurrence will be 0 now because no element is frequency greater than 2. So we'll update our answer as 3 minus 2 plus 1, which will be 2. So we'll update our answer as 2. Now we move to this element. So now the frequency of 1 becomes equal to 3. And so we update our occurrence variable as 1. Now we'll increment our right pointer until the occurrence becomes equal to 0 or we reach the end of the array. So we increment our right pointer. The frequency of 2 becomes equal to 1. Again, we increment our right pointer. The frequency of 2 becomes equal to 0. And now we cannot further increase our right pointer. Now notice that the value of occurrence is not equal to 0. So we won't update our answer because we want the value of occurrence to be equal to 0. So again, we increment our left pointer and that increases the frequency of 2 to 1. Now we cannot actually increment our right pointer. So we have to check if the frequency is equal to 0, occurrence is equal to 0, and which is not the case. So we won't update our answer and increment the right pointer. So now the frequency of 2 becomes equal to 2, but still we cannot move right pointer and neither the occurrence value is 0. So we won't update our answer. So we can finally return 2 as our answer. So let's look at the code to understand it more clearly. So we initialize occurrence as 0. Occurrence stores the number of elements whose frequency is greater than 2. N is the size of the array. Count occurrence stores the frequency. So we iterate over all the elements and increment the frequency. If the frequency is equal to 3, we increment our count. Now if occurrence is equal to 0, simply return 0 because there are no elements whose frequency is greater than 2. Otherwise we set right as -1 and initialize answer as N. Now our left pointer ranges from 0 to n, so we iterate from I equal to 0 to n. Now we'll check if we can take the next element. So if r plus 1 is equal to n and the value of occurrence is still not 0, we increment r. So we decrease the frequency of AR, and if the frequency becomes equal to 2, that means it was 3 before and it becomes equal to 2. So we have decremented the number of elements whose frequency is greater than 2. So we decrement occurrence variable. If occurrence is equal to 0 after this, we'll update our answer as r minus I plus 1. Otherwise, we increment the frequency of AI. If the frequency of AI becomes equal to 3, it was 2 previously and it now became 3 after incrementing here. So we will increment the occurrence variable and so we will finally return answer. So what about the time complexity? We know that the left pointer will increment at most O(n) times. Similarly, the right pointer will also increment O(n) times. So the time complexity will be O of n. But if let's say you're also keeping a map to store frequencies, and we know that insertion and checking works in n log n in map, log n in map. So the map will cost n log n. So total time complexity will be n log n. Also, you could use, let's say, a hash map to reduce this to O(n). So let's look at the next problem, hard problem. You are given an array A of size n. A subarray AL2R contains all the elements AL, AL plus 1 and so on up till AR. A subarray AL2R is called a scalar subarray if maximum of AL2R and AL plus AR are congruent modulo B. Here max ALR is the maximum value of this subarray. So two elements A and B are congruent modulo n if their remainder with respect to n are same. So we need to find the total number of scalar subarrays. Since the answer can be large, return it modulo 10 to 9 plus 7. So for example, consider this array 8, 7 and B is 4. So we know that the subarray 8 is scalar because maximum of 8 is 8 and AL plus AR will be 16 and 8 and 16 are congruent modulo 4 because their remainders with respect to 4 are 0. So let's look at the solution approach. We will use the same, the second example to explain 4, 5, 3, 8, 8 and B is 5. So we have this array 4, 5, 3, 8, 8 and B is 5. Now the first thing to notice is we want that maximum of AL to R, this is congruent to AL plus AR mod B. Now the idea is that we can actually use divide and conquer to solve this problem because we need to find the total number of scalar subarrays. So if we have an array, we will divide it into two parts, the left part and the right part, and we will find the number of scalar subarrays in the left part, number of scalar subarrays in the right part, add them, but we also need to, this is the divide part. And that's actually easy because we can simply do it using recursion. Now the important part is conquered part. That is, we need to find the scalar subarrays of which a prefix lies in the left part and the suffix lies in the right part. That means the subarray has a prefix which is a suffix of the left part and the subarray has a suffix which is a prefix of the right part. Something like this, the shaded region. So we need to find such subarrays. And for that, we will use two pointers. So we have an array and this partition. Now we want that there is some left part and there is some right part, and we need to find the number of subarrays is that the maximum in this range is congruent to AL plus AR modulo B. Now what we will do is, we will first assume that the maximum lies in the left part and then the maximum lies in the right part. For the case where it can lie both, so we can also have duplicates. So to counter that, we will consider the first occurrence of a value as maximum. So for example, if we have 2, 1, 2, this array, then we will count this occurrence of 2 as a maximum. The first occurrence of an element we will consider the maximum. So we will first consider that the maximum lies in the left part. So if the maximum lies in the left part, let's say we are at this index L. Now the current maximum value is mx. This is the left part, and now consider the right part. So we know that we can only move up till some index r such that all the values from here to here will be less than or equal to r because we want the maximum to lie in the left part. We have less than equal to because we consider the first occurrence as maximum. So can we use two pointer to find that index? So what I mean by that is, let's actually look at this example to understand it clearly. So if we have this array 4, 5, 3, 8, 8. Now we will divide it into two parts, that is 4, 5, 3 and 8, 8. Now let's say the maximum occurs in the left part. So if the maximum occurs in the left part, what we will do is, let's say we have considered the L is this index. So if this is the L index, we'll find the rightmost element which can be the right index. So in this case, we cannot have any element here because we want 5 to be maximum. So if we take any element, 8 will become maximum and we want 5 to be maximum. So for this example, let's take a different case. So we have 4, 3, 5, 3, 6 and 4, 3, 7. So for 6, our current maximum is 6. Now we know that 4 is less than equal to 6. So we can increment our right pointer. Again, 3 is less than equal to 6. So we can increment our right pointer. But now we actually cannot take 7 since 7 is greater than 6. So for this index, we have this element which can be the rightmost index. Now if we move here, so we move to this left index. Now our current maximum is still 6. Let's say this was 8. Our current maximum is still 6. So we cannot actually further increment a right pointer because 7 is greater than 6. Again, we move to the left index and now our maximum becomes equal to 8. So now we can actually increment our right pointer since 7 is less than equal to 8. So we increment our right pointer. So for each left index, we find the maximum right index such that the maximum from L to R will be in the left part. And we know that that right index will be monotonic. So maximum actually is non-decreasing in this direction. So consider this case that if we are moving over left index and now we know the maximum value, right? Maximum value is mx and we also know AL. We also know AL. So from this equation, we can actually find AR modulo B. So we know that AR will be equal to AL minus mx mod B. So if we store the frequency of elements in the right index modulo B, we can actually find how many choices we have for AR because we know that this is our left part and this is our right part. And from here to here, this is the maximum right index that we can have. So we just need to find the frequency of AL minus mx modulo B. So we'll store the array elements modulo B here and find their frequency. So this may sound complex. So let's actually dry run this on our example to understand it more clearly. So B was 5 in our case. So we'll store the frequencies of elements modulo 5. Now this is our first divide part. Now again we will divide it into two parts, 4, 5 and 3. Now for subarrays of length 1, we can simply check if maximum will be 3 only, and we can simply check if 3 is congruent to 3 plus 3, which is 6 modulo 5, and we know that that's not congruent modulo 5 because 3 modulo 5 is 3 and 6 modulo 5 is 1. So this is not congruent modulo 5, so we'll return 0 from here. Return 0 from here. Now for 4, 5, we again divide it into two parts, 4 and 5. Now 4 plus 4 is not congruent modulo 4, so this returns 0, but this returns 1 because the maximum will be 5 and the left AL will be 5 and AR will also be 5. So 5 and 10 both have remainder 0 modulo 5. So this is a scalar subarray. Now for 4, 5, we need to consider the conquer part. So we first consider the case where the maximum lies on the left part. So we have 4 here. So current maximum value will be 4. Now we'll find if we can take the elements. So we'll consider this partition and we can take the elements from here. We know that we cannot take 5 because we want the elements, all the elements here to be less than equal to 4. In addition to that, we will also store the frequency of elements which we have taken in the right index. Currently, the frequency of all the elements will be 0. So what elements do we want in the right index? So maximum value is 4. AL is also 4. So AR will be 0 modulo 5. But the frequency of 0 is still 0. So we'll add 0 here. So this conquer part actually gives no answer. So we return 1 from here. Now this case actually gives us no answer. So we'll consider the case where the maximum lies in the right index. So if the maximum lies in the right index, we currently have maximum 5. Now what is the maximum index that we can take? So we'll move here and we can actually take this element 4. So we'll update the frequency of 4 modulo 5 as 1. So the frequency of 4 will be 1 now. So our current maximum is 5 and right element is also 5. So we want AL to be 0 modulo 5. We want AL to be 0 modulo 5. But the frequency of 0 is 0. So again, when we consider the case where the maximum lies in the right index, this also fails and we return 1 here because we have 1 as this answer in the right part. For the conquer part, we get 0 answer. So finally, we get 1 from here and 0 from here. So we return 1 here. Now consider 8, 8. Now for the 8, 8, we can divide it into two parts, 8 and 8. Now is the array of length 1 congruent? So maximum is 8 and AL plus AR will be 16. So are these congruent modulo 5? They are not because 8 modulo 5 is 3 and 15 modulo 5 is 1. So we'll return 0 here and 0 here. Now for 8, 8, we will do the conquer part. So we first assume that the maximum lies in the left part. So we have 8, 8 and a partition here. So maximum lies in the left part. So our current maximum is 8 and we will try to increment our right pointer from here as long as the values are less than equal to 8. So we know that we can actually move to this 8, right? Our right pointer can be here since this 8 is less than equal to 8. And we'll update the frequency of 3 because we are storing the frequencies modulo 5. So the frequency of 3 will be 1. Now the maximum is 8 and the left value is also 8. So AR should be 0 modulo 5, but the frequency of 0 modulo 5 is 0. And similarly, if you consider the case where right element is maximum, so right element is maximum. So now we actually cannot move our left pointer because we want the elements to be lesser than 8. Since if it is equal to 8, then this won't be maximum because we are considering the first occurrence of an element as maximum. So this also returns 0 here. Now consider the conquer part for the complete array. And this will actually give us a good understanding of how is divide and conquer working. So we have 4, 5, 3 and 8, 8. So let's say we have a partition here. Now we'll first consider the case where the maximum lies in the left part. So we start from here. Our current maximum is 3. Now we will see how much can we move our right pointer. So we cannot move our right pointer because the maximum is 3 now. And if we want the elements to be less than equal to 3. So we move left and we get 5. So maximum will be 5. But again, we cannot increment our right pointer. So we move left and maximum is still 5. So again, we cannot increment this pointer. So now we will consider the case where the maximum lies in the right part. So our current maximum is 8. Now we will try to move our left pointer. So we can move our pointer here. So we'll update the frequency of 3 modulo 5, which is 3 as 1. So we update the frequency of 3 as 1. Again, we can decrement our left pointer. So we update the frequency of 5 modulo 5, which is 0 as 1 as well. Again, we can further decrement it. So we update the frequency of 4 modulo 5, which is 4 as 1. So now for this R, we get maximum value is 8 and AR is also 8 and we need to find AL. So this is our relation modulo 5. So AR will be 0 modulo 5. AL will be 0 modulo 5. So we have actually stored the values, the frequency of values modulo 5 and the frequency of 0 is 1. So we can add 1 to our current answer. Now again we will move our pointer here. But if we move our pointer here, the maximum stays the same and we cannot further decrement this pointer because we are at the end or the left end. So again we'll find the condition of AL. Again the condition of AL is it should be 0 modulo 5. So the frequency of 0 is 1. So we'll add 2 here. So this conquer part gives us 2. So finally we will add 2 to this one and return 3 as our answer. So the basic idea is divide and conquer, and how we conquer actually can be done using 2 pointers. So let's look at the code to actually see how we can implement this and to understand the tiny implementation details. So we assign n as the size of the array. So AI is initially assigned to the array and this is actually a global array and B is also B, a global B. We also store an array ABI which will store the elements modulo B and we return scalar from 0 to n minus 1. So this is the divide and conquer part, scalar L to R. If L is equal R, what we want is the maximum will be equal to AL and elements will be AL will be also AL and AR will be also AL. So we want this to be true modulo B. So in other words, we want that AL is equal to 0 modulo B. AL is equal to 0 modulo B. So we know that we have stored AI modulo B in array ABI. So we just simply want ABL to be equal to 0. So if this is equal to 0, we return 1. So we assign mid as L plus R by 2. Now we initialize our answer as, so this is the divide part, scalar L to mid and scalar mid plus 1 to R. So we assign maximum as minus 1. Index is actually the index of the maximum value and we assign R as mid. So we first consider the case where the maximum lies in the left part. So we have L to mid and mid plus 1 to R. So we first initialize our right pointer as mid, that means to the left of this array. Now we will move from this in this direction. So we actually iterate over all the possible left indexes. So we initially assign maximum as minus 1. Now we move from mid to L. If AI is greater than maximum value, we update the maximum value and we also update the index of the maximum value. So now let's say we are at ith index. This is our left index, ith index, and we have updated our maximum value. Now we want that while the next element to be taken, so R plus 1 is actually a valid index. That is, it is less than equal to R. And the value at that index is, which is AR plus 1, this should be less than equal to MX because we want the maximum to lie in the left part. So if this is the case, we increment our right pointer and we also update the frequency of that right element. But we do not change the frequency of AR. We actually update the frequency AR modulo B because that's what we want to find for our answer. So now our maximum value is actually AB IDX. So AB IDX is actually A IDX modulo B. So this should be equal to, now our left value is AI. So we can actually write it as A modulo I plus now we have AR modulo B. So what is the remainder that we want? We want AB index minus ABI. If this is negative, we add B. So we simply want this frequency f of RAM and we add it to our answer. Now we can actually do the similar case for where the maximum lies in the right part. So if the maximum lies in the right part, we again actually set the frequencies to 0 because we want to reset it. So we again initialize maximum as minus 1 and now L will be mid plus 1. So our current L is here and now we'll iterate over this index from here to here, right index. So right index can be from mid plus 1 to R, that is I from mid plus 1 to R. If AI is greater than MX, we update our maximum value index. Now, while the next element to be taken, that is L minus 1, is greater than equal to L, that is it is a valid index and it is less than MX. Notice that we are now taking less than MX and not less than equal to MX. Since if it is equal to maximum value, then we will take the first maximum value because we are taking the first occurrence as a maximum value. Now we decrement the left index and take its contribution in our frequency. And we know that what should be our optimal value of the left index and we will simply add the frequencies of that left index module B to our answer. We again reset the frequencies to 0 and we will return the answer. So now what will be the time complexity of this solution? So we have Tn equal to twice of Tn by 2, that is the divide part. And the conquer part is actually O of n because we iterate over left indexes and our right index will definitely either stay same or increase, that is it is non-decreasing. So the total number of movements of all the left indexes and the right indexes will be of the order n. So from here we can say that the time complexity will be O of n log n and space complexity is O n because since we are only storing some arrays. So it was actually a good problem to understand divide and conquer. I hope you liked it. Thank you for watching this video.
So today we are going to study bit manipulation. Okay. Do you guys understand what is empathy? Right. Empathy is a very important quality that every one of us need to have. Right. So if you have empathy, if you know, if you are able to feel how the other person is feeling, or how if you are able to look from the other person's perspective, then you can resolve very serious issues in your relationship, right? Similarly, if you are able to see how a computer thinks, how a computer perceives number, then you will be able to solve very complex problem in a very optimal way. Okay. Now, if from our perspective, we see numbers like 4, 5, 25, 100, etc., right? We see numbers in decimal, but computer doesn't see the numbers like this. Computer sees the numbers in binary. So for computer, this is not 4, this has to be 100. For computer, this is not 5, this has to be 101. So everything for computer is binary. Okay. Now if you are able to understand how computer stores these numbers, and how computer actually performs operations on these numbers, and what are some of the basic bit operators, then you can solve very complex problems very easily. Okay. Before actually jumping onto the problems, we'll quickly revise some of the basic bitwise operators. Okay. So we'll be talking about AND, bitwise AND, we'll be talking about the bitwise OR and the bitwise XOR. Okay. How does bitwise AND function? So everyone must have studied this in the school, right? So bitwise AND, and before we see how these functions, let us define a terminology, which is a set bit and an unset bit. So any bit which is having a value 1 will be called set bit in our context, and any bit which has a value 0 will be called unset bit. Okay. So if I ask you how many set bits are there in the binary representation of 4, the answer is 1, because there is exactly one set bit. How many unset bit are there in the binary representation of 5? There is exactly one unset bit. Okay? So this is the basic, these are the basic terms which we will be using again and again. Okay. So how does the bitwise AND functions? The bitwise AND always returns a set bit if both the operands are set, right? So if you have 1 and 1, this is the only case when your bitwise AND is going to return a set bit. For all the other possible operands, you will be having a unset bit in the return. Okay, so all of these, if any of the operand is an unset bit, you get a unset bit in the answer. If both of the operands are set, then only you get a set bit in the answer. Now the OR is exactly opposite of it. So OR will give a set bit if any one of the operand is a set bit. For example, if you have 1 or 1, or if you have 1 or 0, or if you have 0 or 1, for all of these you will be getting a set bit. If both of the operands are 0, then only you will be getting a unset bit. Okay. How does XOR functions? So XOR is a very interesting operator, right? So XOR says that if both the bits are having the exact same value, if both the operands are having the same value, then it is going to return an unset bit. So if both the operands are, let's say, set bits, or if both the operands are unset, in both the cases we will be getting an unset bit. XOR only gives a set bit if the two operands are different. So if we have 1 XOR 0 or 0 XOR 1, in this case we'll be getting a set bit. Okay. These are the basic bitwise operators. Okay, now I just said that XOR is a very interesting operator. Why is it interesting? Because this property that the XOR of exact same bits is always going to be 0. This makes XOR interesting. Okay, let us try to analyze this. If I have an integer a, and if I take the XOR of this integer with 0, what is the result that I should be getting? Okay, before actually jumping to this, let us try to understand how to take how bitwise operators functions for integers, right? So let us remove this. We'll come back to this again. If I have to take let's say 4 and 5. So till now what we have seen is both the operands were single bits, right? Now we have numbers which are not binary numbers. How is it going to work? Similarly, if I have to take 4 or 5 and 4 or 5, how are all of them going to work? So to get the answer of this thing, you will first convert the number to its binary representation. So 4 can be represented as 100, 5 can be represented as 101. And now since you are taking AND will give you a set bit only if both the bits are set. For any other cases, it is going to give you a unset bit. So you will get 100. What is the decimal representation of 100? Decimal representation of 100 is 4. So 4 and 5 is nothing but 4. Okay. Similarly, if I have to calculate 4 or 5, again, I will just convert this to binary, and similarly convert 5 to binary as well, and then we do the bitwise OR. Okay, so now here we can see that this is going to be 1 because 1 or 1 is 1. 0 or 1 is also 1. So both of these two are going to return a set bit. 0 or 0 is 0. So what we do is we convert them, we convert both of the numbers in their binary representation, and then we do the bitwise, whichever operator it is it, right? So if you are taking the bitwise OR of two numbers, you will just convert them to binary representation, and then for all the corresponding bit pairs, you will be doing this operation. Okay. Similarly, if we have to, so this is going to be 5. Okay. If you have to take what is 4 XOR 5, so 4 is again 100, 5 is 101. Now this is interesting. Can you guys quickly tell me the answer? XOR gives you a set bit only if both the bits are different. So there is only one pair where both the bits are different. Here we have 0 and 0. Here we have 1 and 1, right? So this is going to be 0, 0, 1, which is nothing but 1 in decimal. Okay, cool. So this is how we will be taking the bitwise AND or XOR of integers. Okay. Now tell me one thing. If I tell you that a is an integer and you have to calculate the XOR of a with 0, what should be the answer? Should 0 be the answer? XOR of a with 0. Correct. The XOR of a with 0 is going to be exactly equal to a. Why is it going to be exactly equal to a? Let us assume that a is in binary representation. A is represented by this random binary string. Okay, and then in the second, as a second operand, we have 0. Right. So 0 is going to have zeros or unset bits in all the bit positions. Now, when you do a bitwise XOR between these two numbers, you can see that for all the digits, for all the bit places where a is having a set bit, 0 is definitely going to have a 0. So for all of them, you will definitely get a 1, right? So for all the bit position where a is having a set bit, the answer also has a set bit. And for all the bit position where a has a 0, 0 also has a 0. So both of them are same. So the answer will also be 0. So this is nothing but this is exactly same as a. So a XOR 0 is going to be equal to a. Okay. Now if I ask you that what if I take the XOR of a with a itself, what should be the answer? XOR of a with a. Again, let us try to represent a in binary form. So let us say that a is a number which can be represented by this random binary string, and the second operand is exactly the same value because the second operand is also a, right? So for any position where the first a has a set bit, the second a is also going to have a set bit. For any position where the first a has a non-set bit, the second a is also going to have a non-set bit, right? So the XOR of same bits is always going to be 0. So in all the bit positions, we'll be getting a non-set bit which is equivalent to having a 0 in decimal, right? So XOR of A with A is 0. These two are very, very important properties of XOR, which will actually allow you to solve very complex looking problems in very optimal way. Okay. Okay. Now let us see one more property of XOR. If I say that there are two integers a and b, okay, and a XOR b is equal to k, what can I say about the value of b XOR k? If a XOR b is equal to k, can I predict what is the value of b XOR k? So if a XOR b is equal to k, what if I take the XOR of a both sides? If or let's say, what if I take the XOR of b both sides? If I take the XOR of b both sides in this equation, this is going to be a XOR b is equal to k XOR b, right? Now, what can I say about this equation? A XOR b XOR b, right? So b XOR b, these two are exactly the same. So these two will cancel out each other, right? We have just seen that a XOR a is going to be 0. So similarly, b XOR b is also going to be 0. If this is 0, I will be getting a XOR 0 equals to k XOR b. What is a XOR 0? We have just seen a XOR 0 is nothing but a. So a is equal to k XOR b. So we can say that b XOR k is nothing but it is equal to a. Okay. Does this make sense to everyone? Similarly, you can take a XOR of a both side, and you can also prove that a XOR k is going to be equal to b. Now these are some of the basic bit operators and some interesting facts about them. Now there are two more bit operators which are not that basic, but they are also very interesting. Okay, so there is an operation which is represented by this sign. Okay, and this is called the left shift operator. And similarly, the counterpart of this operator is this, which is called the right shift. Okay, what do we mean by left shift? So left shift means nothing but you are shifting the bit positions. You are shifting all the values which are there in the bits towards left side. Okay, so for example, if I have 1 and I left shift 1 by 1 bit, if I have to left shift 1 by 1 bit, how will I write it? I will write it something like this. So I am left shifting 1 by 1 bit. Okay, so I'm left shifting this number by these many bits. Okay, so how is it going to work? So let us say that the computer that we are using is representing all the numbers using 5 bits. Okay, so if I left shift 1 by 1 position, what will happen is all the bits will be shifted towards the left side by 1 place. So this 1 will come here, this 0 will come here, this 0 will come here, this 0 will come here, and this 0 will be removed from this equation. So this 0 is gone, and here in this empty position a new 0 will be added. Okay, so what is the end result that we are getting? The end result is nothing but 1 0, which is nothing but equal to 2 in decimal representation. Okay, if we further left shift this by 1 position, then what will happen? If I further left shift this, I will get 0 here, this 1 moves here, this 0 moves here, this 0 moves here, this 0 is removed from this, and here we get a new 0. In the last position we'll be getting a new 0. Okay, now what is this? What is this number? This is nothing but 4 in the decimal representation. Okay, similarly, let us try to do it once again. If you again left shift this number by 0, you get 0 here, you get 0 here, you get 1 here, this 0 here, this 0 is removed, and you add a new 0 in the left corner. What is this number? This number is nothing but 8, right? So you can quickly observe that whenever you are shifting a number, you are doing a left shift on a number by 1 bit position, you are doing nothing but you are just multiplying that number by 2. So 1, initially you had 1, then you get 2, then you get 4, then you get 8, right? And in the next operation, you will be getting a 1 here and then all zeros here. This is nothing but 16, right? So whenever you are doing a left shift by 1 bit position, you are always multiplying the number by 2. Okay. Now similarly, the right shift is the counter part of this operation. So what you have to do in right shift is that you will be shifting all the bits to right side, all the bits by the specified number of positions toward right side. So for example, if you are starting from 16, okay, if you are starting from 16 and you are doing 16 right shifted by 1 bit, what will happen? All these bits will be shifted towards right by 1 bit. So 1 comes here, 0 comes here, this 0 comes here, and then this 0 comes here. This 0 is gone, and in the left end you will be appending a 0. Okay, so what is this number? This number is nothing but 8. So initially you had 16, now you have 8, right? In the next iteration, what will happen is this 1 will come here, this 0 comes here, this 0 comes here, and this 0 is removed, and again you will be inserting a new 0 in the left end. What is this? This is nothing but 4. So now you can see that you are always dividing by 2, right? So left shift is equivalent to multiplying the number by 2. Right shift is equivalent to dividing the number by 2. If let's say I do a right shift of 1 by 1 bit position, what will be the answer? Right shift of 1 by 1 bit position. So if my 1 is represented like this and I am right shifting it, so this 0 comes here, this 0 comes here, this 1 is removed, right? And this 0 comes here, okay? And in the left corner, we add a 0. So the answer that we get is 0. So even if you have a set bit here, that will be removed, okay? Cool. Now let us try to solve an easy problem, okay? What if you are given a number and you have to check whether the ith bit of that number is set or not? Given an integer, and this is going to be a positive integer, check if the ith bit of the integer is set or unset. Okay, so how can we solve this problem? If you are given a number n and you have to check whether the ith bit is set or not. What about negation? Negations, if you have a bit which is representing the negation sign, that will not be removed in a logical shift operator. So even if you are shifting a number which is negative, the result that you get is also negative. Okay. So how are we going to solve this problem? So let us say that the number that is given to us is 6. Okay, and we have to check whether the second bit is set or not. Okay. So what is 6 in binary? 6 in binary is nothing but 1 1 0. What is the second bit? Second bit is this bit, and I have to check whether this bit is set or not. How can we do it? So we have seen all the basic bit operators, right? And now there is a bit operator which is bitwise AND, which only returns a set bit if both the operands are set, right? So in my opinion, this can be a very, very good candidate to analyze whether we have a set bit at any given position or not, right? So if let us say I construct a number where we have a set bit at this position, but unset bits in all the other positions, and I take an AND of this number with the given number, okay? Can I say that if the result is non-zero, then we will always, we can say that this bit is set, or if the result is 0, we can say that this bit is non-set, right? Because if the result is non-zero, which in this case is which is the case in this question, the result will only be non-zero if this bit is set, right? Because we are making sure that in the number that we are constructing, the ith bit is set, right? And all the other bits are unset. So if we are taking an end of this number with the given number and the answer is greater than 0, then we can say that yes, the ith bit is set. Okay. If the answer is not greater than 0, in that case, what will happen? Since all the other bits of this number are unset and this position is also giving a 0 in the answer, that means that the original number had a unset bit at that position. Is this thing clear to everyone? So we just have to construct a number which has a 1 at the ith bit and all other bit positions should have a 0, right? How can we construct such a number? So we know that to construct this type of a number, we just have to shift. If I have 1 already, right? This is how we can represent 1. Now if I just left shift 1 by ith position, right? So if let's say I have to check whether the third bit position is set or not, right? So I can just do 1 left shifted by 3. So 1 left shifted by 3 is going to be 2 raised to power 3, right? Sorry, 2 raised to power 2. So we can say that right. Oh, sorry. One left shifted by we'll be doing here. 1 left shifted by 2, right? So 1 left shifted by 2 is going to be 2 raised to power 2, which is 4. And now you can take the XOR. You can take the end of this constructed number with the given number. If the result is greater than 0, then you can say that yes, the number has a set bit. So what will be final equation? You will just have to return if your number and the bitwise end with 1 left shifted by I bits. Okay, if this is greater than 0, then you return true, else you return false. Okay, this is how you can check whether the ith bit in your number is set or not. Now there can be other ways as well, because this number is nothing but 2 raised to power I, right? So you can also calculate 2 raised to power I, and then that can also be used, but this is going to be more optimized. Okay, can we use other bit operators as well? Yes, you can definitely use, but this is the easiest thing. Based on the properties of other bit operators, you can also figure out a different way to figure out the same thing. Okay, let us see another quick question. If you are given an array, find the XOR of all the numbers where ith bit is set. Now, given that you are able to find whether the ith bit of a number is set or not, can you also find the XOR of all the numbers in a given array which has the ith bit, which has a set ith bit? So you are given given an array which is an unsorted array of positive integers. Okay, you have to find the XOR of all the numbers, the collective XOR of all the numbers where the ith bit is set. Okay, so if let's say I is equal to 1, so you just have to check whether you just have to calculate the XOR of all the numbers which have a set first bit, right? So for example, 2 does not have a set first bit because 2 is 1 0. 4 also does not have. 10 also does not have. 1 has a first set bit. 3 also has a set bit. So the answer that you will be returning is going to be the answer of 1 XOR 3. Okay. Now can you guys? You just have to apply a loop, and for every number you check this thing. If this condition satisfies, then you calculate the XOR of that number in a cumulative XOR sum. Okay. Now let us see a very commonly asked problem. Okay, which is very common in interviews. The question says that you're given an array and you're also given the condition that in this array all the numbers appear even number of times except 1. Okay, so there in this given array all the numbers are occurring even number of times. They can occur 2 times, 4 times, 6 times, 8 times, and so on. But there is exactly one number which occurs odd number of times. Okay, So for example, if your array can be 2, 1, 3, 2, 1, 1, 1, 4, 4. Okay. So now in this array, you can see that 2 is occurring twice, 1 is occurring 4 times, 4 is occurring twice, but there is exactly one number 3 which is occurring once. So there is exactly one number which will occur odd number of times, and all the other numbers will occur even number of times. You have to return the number which is occurring odd number of times. XOR of all the elements. Okay, so I can see that most of you are giving the correct approach, which is XOR of all the elements, which is absolutely correct, right? So we know that A XOR A is 0. We have seen this. Now, if A XOR A is 0, what will be the value of A XOR B XOR B? This will also be 0 because B and B will also cancel out each other. A and A will cancel out each other. So this will also be 0. What will be the value of A XOR B XOR A XOR B? Again, this is also going to be 0 because when you are calculating the XOR, order does not matter, right? You can calculate the XOR in any order. You can calculate the XOR of A and B or B and A. Both of them are same thing. So this is also going to be 0. Now, if you just add a C in between, what will be the answer now? The answer now is going to be C because A and A cancels out, B and B cancels out. So only C is remaining. So if all the numbers are occurring even number of times and you take the XOR of all of them, they all will be reduced to 0. The only number which is occurring odd number of times, let us consider that also. So if let's say that there is a number x which is occurring odd number of times, right? So if this is the case, if the number is occurring 3 times, then what will happen? These two x will cancel out each other and you will be remaining with exactly one x and the XOR with 0. This is nothing but equal to x. Doesn't matter how many times the x is occurring, but if it is occurring odd number of times, all the even occurrences will cancel out each other. They all will become 0, and at the end you will be remaining with one odd x, right? So the answer is always going to be x. So if you quickly take the XOR of all these numbers, then you get the element which is occurring odd number of times. Okay, is this thing clear to everyone? If you have to just quickly write the code for this, this is going to be a single line, a single for loop code. You can just initialize an answer with 0. Now you can say for I equals to 0, I less than n, I plus plus, answer equals to answer XOR A of I. And this is it. Here you return the answer. Okay. Okay, now let us see another very similar question, but a very difficult, supposed to be difficult question. Okay, let us say that you have a similar type of array where all the numbers are repeating even number of times except two numbers, right? So initially there was exactly one number which was appearing odd number of times, right? In this case, there are two numbers which are appearing odd number of times. All the other numbers are appearing even number of times. Okay, and you have to return both the odd occurring numbers. Okay, so for example, if the array is 4, 1, 2, 3, 2, 5, 4, right? Now in this case, you can see that 4 is occurring even number of times, 1 is occurring even number of times, 2 is also occurring even number of times. But 3 and 5 are occurring odd number of times. Okay. So in this case, you have to return both these elements. Is the problem clear, guys? Now the suggestion is, can we use mapping? Yes, you can definitely use mapping. If you use mapping, what will be the time complexity? What will be the space complexity? Varun is suggesting from XOR of all the numbers, you can construct the two numbers. How? Varun, can you quickly write down your approach? Okay, now another suggestion is that we can quickly take the XOR of all the numbers. That will give us A XOR B. and using this we can construct A and B. Okay, just try for that. If can you construct two numbers out of out of their XOR result? Dipanshu, that is absolutely correct. That is in the correct direction. Okay, let us see all the approaches one by one, right? So one of the approach that some of you have sent is that sort the numbers. Okay, if I sort the numbers, what will I get? I will get all these numbers in sorted order. If all the numbers are sorted, can I say that all the numbers which are appearing even number of time will always appear together in the sorted array? Since the values are same, the pairs are always going to appear together, right? So once the array is sorted, you can quickly count the occurrences of each and every element, right? So if you start from here, you see that this is 1, and let us see how many ones are there. So once you reach to 2, you can see that there are 2 ones, so 1 is not the answer. Then you see for 2, then you do the same thing for 3, and then you can say that 3 is one of the answer, and so on, right? If you do this, what is going to be the time complexity? If you sort the arrays and then count the occurrences of each and every element, sorting, the most optimized sorting algorithm that we have studied is quick sort or merge sort, right? Both of them run in order and log n in the best case, right? So if you are sorting these numbers and then you are finding out the answer, the time complexity is going to be order and log n. The other approach that was suggested is that use a hash map. So we'll create a hash map. This hash map is going to have the array number or the value along with the frequency, right? So what we are suggesting is that you will iterate over this original array and you will maintain the frequency of all the elements in the hash map. Okay, cool. So whenever you are maintaining the frequency of all the numbers in the hash map, once all the frequencies have been calculated, now you can again reiterate over the hash map and check which is the number that is having a odd number of occurrences, right? Yes, hash map or dictionary in Python, right? The same thing. Okay, so in this case, you will be having 4, 1, 2, 3, and 5 as the keys, and the values are going to be 2, 2, 2, 1, 1. So then, once all the frequencies are calculated, you can quickly iterate over this hash map and you can figure out that these two are the numbers which are appearing odd numbers of time. If you use a hash map, what is going to be the time complexity? You are doing one iteration to calculate the frequencies, right? In one iteration, you count the number of times each number is occurring, right? So that is going to cost order n. And then once the hash map is prepared, you do another iteration over the hash map and check which are the numbers which are occurring odd number of times, right? So that is also going to be order n. So effectively, it is going to be order n. What is going to be the space complexity here? If you are using hash map, definitely you are using some extra space of order n complexity, right? So if you are using hash map, you have reduced the time complexity from log n to order n, but you have also increased the space that you are using. Okay, we have to solve this problem in order n time complexity without using any space, which means order 1 space complexity. Okay, cool. So this means that we can definitely not use a hash map, right? So what can we use? Let us go back to the previous problem. In the previous problem was also very similar, right? So if we take XOR of all the numbers, in the previous problem we were directly getting the answer. In this problem, what do we get? If you take XOR of all these numbers, right? Let us quickly take the XOR of all the numbers. We have 4, 1, 2, 3, 2, 1, 5, 4. If we take XOR of all these numbers, what do we get? 4 and 4 cancels out each other. 1 and 1 cancels out. Then you have 2 and 2 cancels out each other. So in the answer, you will be getting 3 XOR 5. Okay. What is 3 XOR 5? 3 is this, 5 is this. So you will be getting this as 0, 1 and 1. Right. So you will be getting a 6. Now, how does a 6 help you out in figuring out that the two numbers are 3 and 5? Can you construct 3 and 5 from this 6? No, right? There are multiple possibilities, because you know that in 6, this digit is a set digit. Now, a set digit can come from two combinations, right? Either you can have 1 0 here, or you can also have 0 1. Both of them are going to give you a set bit. So this is very hard to actually construct the two numbers from their XOR results, because there are actually multiple possibilities. So constructing the numbers is not a good idea. If that is not a good idea, then how is this result going to help us? Okay, let us try to analyze this 6. Okay, so we have 3 as 0 1 1. This is 3, and then we have 5, which is 1 0 1. Okay, the answer 6 is 1 1 0. Now, if I ask you that what are the set bits in this number 6 signifying? Both these set bits, what are they signifying? Is there any information which is hidden in them about the two numbers? Is there any relation between the two numbers which is hidden in this number, which is encrypted in this number? Let us go back to the basics and see that we get a set bit in XOR if and only if both the operands are different. Right? A set bit in XOR means that both the operands that were given to it, which were fed to it, are different. One of them has to be set, one of them has to be unset. We don't know which one is set, which one is unset, but we know that they both are different. Correct? Now, if I know that using this 6, I can come to a conclusion that whichever are the two numbers which are occurring odd numbers of time, they are different. They are having different values for this bit position and this bit position. Does this make sense to everyone? You can actually try to also visualize this here, right? Both of them are having different values at this bit position. Wherever the final answer is having a 0, at that position both the values are same in the two numbers. Okay, now can I use this information to solve the problem? I have got one information, which is the bit position at which the two numbers are different. Okay, so initially we had this complete array, which is 4 1 2 3 2 1 5 4. Okay, the only information that I have is I don't know which number is occurring odd number of time, but the only information that I have is that the two numbers which are occurring odd numbers of time are different in the second and third bit position. One of them is going to have a 0, one of them is going to have a 1, right? If I divide all the numbers based on any of these bit positions, if I'm separating the arrays, if I'm making a partition in the array based on the position of this number, right? Can I say that both these numbers will always fall in different sets? If I'm trying to partition the array based on the bit position which is different in both the numbers, can I say that both the numbers will fall in different sets? No, I can say, right? Why I can't say that? Because I'm making sure that I'm partitioning based on a bit which is different in both of them, right? Let us actually convert all the numbers in their binary forms, and let us try to perform the separation. So 4 is 1 0 0, then we have 0 0 1, 0 1 0, 0 1 1, then 0 1 0. So these are all the numbers, right? Now, if I am partitioning this array and I am saying that's the final, if I take the XOR of all the numbers, right? If I'm taking the XOR of the complete array A, what is the number that I'm getting? I'm getting 6, which is nothing but the XOR of the two numbers which are occurring odd numbers of time, right? And this 6 is nothing but the 6 in binary is 1 1 0. I know that the two numbers A and B are different in both of these positions. So let us select any of these bits. Okay, let us select any of these bits and partition the array into two parts. So let us select the second bit position. Okay, now we are partitioning the array based on the value of this second bit. So we'll keep all the numbers which are having a set bit on in one side, and all the values which are having an unset bit at this position one side. Okay, so let us say here we are keeping all the numbers which have got set bit at this position. Okay, so 4 has not got a set bit, 2 has got a set bit, 3 has got a set bit, then 2 again has got a set bit, and that's it, right? And for all the numbers which have got an unset bit here, we have got 4, we have got 1, then we have got 1 again, then we have got 5, and we have got 4. Right? So if I'm separating all the numbers based on the bit position which is different in the two numbers, I can make sure that both the numbers are falling in two different sets. What about the other numbers? Can I say that in this set, in this half partitions, all the numbers are appearing even number of times except the one, and in this partition also all the numbers are going to appear even number of times uh, uh, except one or just one number? Yes. What if we also have 5 in the array? We have 5 in the array, right? This we have 5 and 5 is falling here, right? If we have another 5, then we will need to have one, at least one number which is occurring odd number of times, right? Currently we have 5 and 3 which are occurring odd numbers of times. So what we have done is we are partitioning the array based on a digit which is different in both of them. If that is the case, that we are partitioning the array based on a different digit, then we can make sure that these two numbers will always fall in different sets. And now if you observe, we have reduced this to the previous problem that we have solved, right? In this part, all the numbers occur even number of times except one. In this part also all the numbers occur even number of times except one. Okay, so what we have to do? Take the XOR of all these numbers. Take the XOR of all these numbers. What will be the XOR of all these numbers? The XOR of all these numbers will give you 3. The XOR of all these numbers is going to give you 5. Is this whole thing clear to everyone? So we partition based on one singular bit rather than for each set bit. Correct, Bhavya, that is absolutely correct. We are selecting any of the set bits. So currently in this case, I have partition based on the second bit. You can also do the partition based on the other set bits, because set bit will guarantee that a set bit in a XOR result is going to guarantee that the two numbers are different at that place. If the two numbers are different at that place, they will definitely fall into different sets, and all the other numbers are occurring even number of times. So if the other numbers are having a set bit, they come with all their copies, right? So if 2 is coming here, 2 will not come alone, 2 will also bring the other 2, so all the numbers will come even number of times. Okay, how to find which bit is set? Okay, we have solved the first question that we have solved. Can you not use that thing? You know how to check whether the ith bit of a number is set or not, right? You can just loop from 0 to 32, assuming that there are 32 bits that your data type is being used to store. So you can just loop from 0 to 32. The first bit that you are finding that is set, you can do the partition based on that. Okay, so this is going to give you which bit is set. Okay, now the question is, do you need any extra space for this? Is some extra space required here? If there are n odd occurring number, then this will not work. This only works if there are two numbers which are occurring odd number of times. Okay, do we require some extra space? Let us try to see the code. Okay, so let us say that we have a XOR which we initialize from 0. Okay, and we are calculating the XOR of all the array elements in this variable. Okay, so we'll just say XOR is equal to XOR A of I. Okay, so what will this XOR hold? This XOR is going to hold the XOR of the two numbers that are occurring odd numbers of time. Okay, now what we can do is we can first find out a position. Okay, so first find out a position at which you have a set bit in this XOR. Okay, how to find out that position? To do that, if we are assuming that we are dealing with integers are stored in 32 bits, right? So we'll be running a loop. So let us say that we have a position variable which we are initializing from 0. Okay, and then we are saying that for all the values of this position, all the values that the position can take, which is going from 0 to 32, okay, we can say that check the exact same thing that we had done to check whether the ith bit is set or not. So we'll be taking XOR here and one left shifted by I bits, right? So here we can say if XOR and one left shifted by I, okay, if this whole thing is greater than 0, this means that this number XOR is having a set bit at the ith position, right? So we can just set the value of position by I, and we don't require any other set bit now. This is enough, so we can break. We just require whichever is the first set bit. Okay. Now what all we have? We have the XOR, and we also have a set bit in XOR. We have a position of one of the set bit. Okay. If two numbers we got in the same set, okay, yes, can you please use some other names? Maybe this sounds very derogatory if I use your name, but you fool, how can they fall in same set? If you are partitioning the array based on a bit position which is different in them, if you are already selecting a quality which is different in both of them, how can they fall in same set? For example, let us say that you have got a bunch of books. Some of them have got black cover, some of them have got white cover, and you are the property that you are selecting to partitioning is the color of the book. So you are saying that I will keep all the black books here, all the white books here. Can the two black and white fall in same set? No, right? They cannot. If you are selecting a property which is already different in them, right? Then they will never fall in the same set, right? So what happens till now? Till now we have the XOR, and we also know a position at which the XOR has a set bit. Okay. Now the XOR has a set bit in this position. Now the next step is that we have to divide all these numbers based on this set bit. So how can we do that? And we have to divide all these numbers without actually using some extra space, right? So now do you guys remember the problem that we had just discussed before this problem? Given an array, find the XOR of all the numbers where ith bit is set. This is the exact same problem that we have to solve inside this problem. You have to find the XOR of all these numbers where the bit at this position is set. Okay. So how can we do that? We can initialize two numbers. So basically we have to find the XORs of all the numbers where the bit is set, and parallelly we also have to find the XOR of all the numbers where this bit is not set, right? So we can say initialize, let's say num1 and num2 with 0, and then we can start the loop from I equals to 0, and then I less than n, I plus, and then we can say that if a of I, and again we are checking the exact same thing. We are just checking whether the whether this number, whether the array number has got a set bit at this position or not. So I shifted by positions. If this is greater than 0, if this is greater than 0, this means that the number has got a set bit here. So keep the XOR in num1. Else, what can we do? Else we can say num2 is equal to num2 XOR a of I. Okay. Now does this make sense? So all the questions, all the concepts that we have studied in the throughout the class have been used in this single problem, right? Let us quickly revise this problem. The problem was that you are given an array where all the numbers are appearing even number of times except 2 elements, right? So what we did was, first thing was that we took the XOR of all the numbers. Taking the XOR of all the numbers gave us the XOR of the 2 numbers that are appearing odd number of time. Okay. Once we get the XOR of all the XOR of the 2 numbers that are appearing odd number of time, this XOR gives us the information about at which bit position the 2 numbers are different. Now, if you know that in at this position where the XOR is having 1, one of the number definitely is going to have a 0, the other number will definitely have 1. They cannot have same value, right? So now partition the set, partition the whole array with respect to this position. So this number which has a 1 here will go to one side. This number which has 0 will go to the other side. And all the numbers, since are appearing even number of time, they will, whether they go to the set 1 or set 2, they will go with all their copies. So now we have reduced this to the previous problem where all the numbers were appearing even number of times except one number, right? So now we just have to calculate the XOR of the two sides. Okay. Now the question is for 3-7 it was filled. Okay, Sai, if that is your input, that is a wrong input, because if you haven't, I think you haven't understood the question correctly. The question says that all numbers appear even number of times, right? So there has to be a bunch of numbers which are appearing even number of times. Then there has to be exactly 2 numbers which are appearing odd number of times. This is the question. Okay. Now you cannot change the language of the question and expect the same approach to work, right? Ankur, thanks for correcting. This is not I. This has to be 1. 1 left shifted by position. Thanks for that. Right, because we are just checking whether the bit in this position is set bit or not. Okay. Okay, so there was a problem in the assignment which I can say has been solved by very few students. Right, so we'll discuss that problem because that is also a very important problem with respect to the interviews. Okay, the problem says that you're given an array and you have to find the pair that has got the minimum XOR. So out of all the numbers in the array, you have to find the pair of numbers which has got the minimum XOR. Did you guys attempt this problem in the assignment? So for example, if you have 1, 4, 5, 2, 3, if this is your array, you have to find the pair that has got the minimum XOR. In this case, the minimum XOR is going to be between 2 and 3, okay, which is going to be 1. So you have to find the pair that has got the minimum XOR. Okay. Okay. SK Creations is saying that maintain a map with bit count of all the numbers. Okay. Okay. Now some of you are saying that sort the array first. Okay. Why does sorting help here? What is the reason? Like all of you who have solved the problem have used sorting for solving this problem, right? But why sorting actually helps in this case? XOR of 4 and 5 is also 1, correct? So that can also be an answer, but you have to return this value. So this value remains same in both the cases, right? So answer here is going to be 1. So let us say that you have to find the minimum, or let's say that you can return any of the available answers. So any of these two will be the answer. Okay, let us not return the value, let us return the pair. So any of these two will be the answer. Minimum elements XOR is minimum. Is that the case in this case? You can have the XOR of even the maximum elements is also minimum, right? XOR of 5 and 4 is also 1. XOR of 2 and 3 is also 1. But the minimum element here is 1, and 1 is not giving the minimum XOR with any of the elements, right? Okay, now to solve this question, we need to use a very, very important property of XOR, and then we'll make some observations, okay? So a very important property of XOR that we studied in the last class, that if you are given a number A, then the XOR of A with A is going to be 0. Is everyone clear with this thing? XOR of A and A is always going to be 0. Which means that if I have got a number which is repeating in this array, can I say that the minimum XOR will always be 0? If I have an array which has, let's say, which has a pair where the numbers are repeating. So if this is the array, what should be the answer? If this is the array, answer would be 4, 4, because this will always return 0, and we cannot have a XOR which is less than 0 if all the numbers are positive, right? So if I can find a number which is repeating in the array, then the answer is always 0, right? But what if there is no such number which is repeating? Let us again try to observe why this XOR is 0. Why the XOR of a number with itself is 0? It is 0 because at all the bit places, the value of digits in both the numbers is exactly the same, right? If I have 4 XOR 4, in all the bit places, this place, since both the numbers are exactly the same, these values are also same, right? That is why we are getting 0, 0, 0 at all the bit places. Okay. Now, just use this thing, and can you say by just looking at this that if the number are closer to each other, if the number are numerically closer to each other, then chances of having a lesser XOR will be maximized. The closer the numbers, the lesser would be their XOR. For example, if I'm taking XOR of 4 with 5 and versus XOR of 4 with, let's say, 16, this pair is going to give me a lesser XOR versus this pair. Does this observation make sense to everyone? Because chances of finding same bits are going to be lesser in the are going to be more in this case versus this case. Okay, now can I also say that since I want a value which is smaller in magnitude, right, which is smaller in the value, the most significant digit always decides what is going to be the actual value, right? Because if or the most significant bit is the one that decides whether the value is going to be larger or smaller than the other value, right? For example, if I have 4, right, and I have 8, the most significant digit which is set in 8 is here. The most significant digit which is set in 4 is here. The number which has got the most significant bit set on as left as possible is always going to be a number of higher magnitude, right? Because this is the bit with the highest power of 2, right? So to actually get a minimum XOR, we want to minimize the value of the most significant bit, correct? So we always want that the first set bit from left should come as late as possible, since we want to minimize this value, right? So the first set bit should be on as right as possible in the result. So ideally, if I am given a list of number, and if I select a number out of that list, and I want to find out what is the minimum XOR of that number with any of the given number, right? So if, let's say, I'm given a list of these numbers, and I select any random number, and I want to find out what is the minimum XOR involving this number, which number is going to give me the minimum XOR with this number B. Okay, so let us say that B has got this as the binary representation. Now a number which has the exact same binary representation, which means that if I have B again in this array, then this definitely is going to give the minimum ZOR. But if B is not present, the next choice, what should be the next choice? The next choice would be that if I have a number which has just this bit as different, all the other bits should be same, right? This is the best choice that I can have if I don't have B again in the array, right? So in this case, the ZOR is going to be 1. What is the other best choice that can I have? That what is the next choice? Next choice would be that the first different bit occurs here, right? Or if that is also not present, then I would say that the first different bit should occur here, and so on. So I want the first different bit to occur as right as possible. The first different bit with this number, if I have a number which has got which is different with B, different from B, and the different bit is occurring as right as possible, then that number is going to give me the minimum ZOR, right? Out of all these numbers, whichever number is having the different bit on the rightmost side is going to give me the minimum ZOR. Does this make sense? For example, if I list down some numbers, let us say I have 1 1 1 0 0 1 0 1, then I have 1 1 0 0 0 1 0 0, and then I have 1 1 1 1 0 0 0 1, then I have, let us say, 1 0 0 0 1 1 1 1, and then I have 1 1 0 0 1 1 1 0. Okay, now out of all these numbers, which number do you think is going to give the minimum ZOR with this given number B? Let us try to analyze which number is having the different bit on as right as possible, right? So if you analyze this number, the different bit occurs here. Here we have 0 here, and in this number we have got 1, right? In this number, the second number, the different bit occurs here. You have 1 in the original number, you have 0 here. In the next number, the different bit occurs here again, right? In the next number, the different bit occurs here. In the next number, the different bit occurs at this position. Which of all these numbers is going to give the minimum ZOR with the number? The last one, correct? Because here the different bit is occurring on as right as possible, right? If you take ZOR of the first number, the result will be having the third bit in the result from left is going to be a set bit, so the magnitude will be very high. Here the fourth bit from right is going to be the this is going to be the set bit in the result, right? So again, the magnitude is going to be higher with as compared to this number. If you take a ZOR with this number, all these bits in the result are going to be 0 because all of them are exactly same as the original number. This is the first bit which is different. That is why this is going to give you a set bit. Okay, so this is the idea behind this approach, right? You have to make sure that you are taking the ZOR of a number with that number which has got the first different bit on as right as possible. Okay, now how can we do this? So intuitively this comes to the mind that since all the bits from left to right should be same, right? Should be we want the maximum similarity between the numbers. So now the closer the numbers, the more chances we are going to have in the similarities of the bits, right? The more close the numbers, the farther we'll find the different bit, correct? Okay, so Himanshu has an observation: minimum difference between two numbers will give the minimum ZOR. Is that correct? Now there can also be a contradiction to this. For example, you have numbers like 8, 10, and let's say 7. Okay, what is the minimum difference between these three numbers that we can have? We have 8, 10, and 7. 8 is 100, 10 is 1010, and 7 is 111. If you are just checking the minimum difference, then you will be selecting 8 and 7. What is the ZOR between 8 and 7? the XOR between 8 and 7 is going to be very large, right? This is going to be 15. So this observation can have some exceptions, right? But the observation that we made, earlier is that we want all the digits, we'll be checking for each and every number, and for each and every number we'll be considering the XOR, with that number which has got the first different bit as right as possible. Okay, so if you are considering the XOR with 8, you have got two prospects, right? Which of these two has got the first different bit as right, more on the right side? 7 has got a first different bit on the first bit itself, so 7 is not the contender with 8. Okay, 10 has got two similar bits, so 10 is a contender with 8. If you take XOR of 8 and 10, then you will be getting 2, right? So 8 will be giving the minimum XOR with 10. Then you will be checking what is the minimum XOR involving 10. So again, for 10 as well, 8 is going to be the prospect pair, and for 7 also 8 is going to be the prospect pair, right? And then the XOR of the minimum XOR involving 7 is going to be 15, but we will select whatever is the minimum out of all the pairs, right? Now if this thing is failing here, that the minimum difference is not giving the minimum XOR, then how is sorting helping here, right? So if you are clear with this observation, right, XOR of any two consecutive numbers after 1 and 2 always gives us 1. No, Tuhina, I just gave you an example, right? 8 and 7 are consecutive numbers and they are not giving 1. This is not 1, this is 15, right? So the observation that you are making can be correct only in those cases where you are not incrementing, you are not adding a new digit, right? So if you are switching from a number which is of the form 2 raised to power n minus 1 to 2 raised to power n or 2 raised to power x, in that case you will be getting a very large XOR value. Okay, so how to solve this problem? Now the intuition that comes to the mind is, the closer the number, the more similar bits we are going to get on the left hand side. Okay, if you sort all the numbers, if you just sort these numbers, you get 7, 8 and 10, right? The intuition is the closer the numbers, the lesser the XOR. However, we have seen an exception of this, right? But if you sort these numbers, now I can say that 8 will either give a minimum XOR with 7 or 8 will either give the minimum XOR with 10. So these two are the only numbers with which 8 can give the minimum XOR. Let us say that we had more numbers in the array. If you also had 5, 3, 12 and 15. If you have all these numbers, even then I can definitely say that the XOR that 8 is giving with 7 is always going to be smaller than the XOR that 8 gives with all these numbers. And the XOR that 8 gives with 10 is going to be smaller than the XOR which 8 is going to give with all these numbers. So 8 is always going to give the minimum XOR either with 7 or with 10. Okay, does this make sense to everyone? Because out of these two, one of them is going to have the maximum number of similar bits on the left side. Okay, that is why if you sort all the numbers, and you just check the XOR of all possible pairs, you will be getting the minimum XOR out of all the possible pairs. Because 8 can only give the minimum XOR that involving 8, the minimum XOR that which you are going to get involving 8 is going to come either from 7 or from 10. It will not come from these numbers. Why? Because these two are the closest to 8. This one is the closest on the left hand side, this one is the closest on the right hand side. And we have seen that to get the minimum XOR, we want all the digits on the left hand side similar to the given number, right? How 7 and 7 and 8 are not giving the minimums or. Try to understand this thing. How are you actually going to find the minimums or think about the brute force approach. The brute force approach would be if you don't just skip all these things which we have discussed till now. What is the brute force approach of doing this? The brute force approach is that for every number you take XOR with each and every other number, right? And you store that in a variable minimum. If you find the minimum XOR, then you store that in a variable. This is going to cost you order n square time, because for every number you are going to take the XOR with every other number, right? This is going to be an n square approach. Now what I am saying is that you don't need to take XOR of 3 with each and every other number. You can only take the XOR of 3 with two numbers, one which is closest on the left side, one which is closest on the right side, and the minimum of that two is going to be the minimum XOR that 3 can give you. Okay, so in this case, if you are looking for what is the minimum XOR involving 8, right? What is the minimum XOR involving 8? If you want to find that out, if you are doing a brute force approach, you will be checking 8 XOR 3, 8 XOR 5, 8 XOR 7, 8 XOR 10, 8 XOR 12, 8 XOR 15, each and every number, right? But I'm saying that you don't need to do all of these things. These all calculations are totally needless. Why? Because we have seen that if the number of bits are similar on the left side, right? I want to find the number which has got a different bit on as right as possible. I can say by intuition that the closest number are going to give me that. So 8 XOR 3 will always be greater than 8 XOR 7, because 7 is closer than 3, right? Similarly, I can say that 8 XOR 10 will always be minimum than 8 XOR 12. Okay, because again 10 is closer to 8 than 12. So chances of having different bit is going to be more on right side for 10 rather than 12, right? So this is the intuition behind this, that you sort the numbers and then you just check for every number, you just check with the adjacent numbers. So for 5 you will be checking with 3 and 7. For 7 you will be checking with 5 and 8. For 8 you will be checking with 7 and 10, and so on. Okay, is this clear to everyone now? Or should we also try to prove this mathematically? So let us say that we have got two values A and B. Okay, and I'm saying that A is smaller than B. Okay, if A is smaller than B, then there are some bits for which the value is same in A and B, and then this is the first bit with in which the value is different in A and B. Okay, if A is smaller than B and this is the first position where the bits are different, what can I say about the values? Can I say that A will always have 0 and B will always have 1? Yes, no, right? Because A is less than B, and this is the first bit at which A and B are different. All these are exactly the same, whatever be the value. This is the first bit where these two numbers are different, right? So I will, so we can definitely say that A is going to have a 0, B is going to have a 1. Okay. Now, if you put another value between these two, okay, if there is another value between A and B, let us call it X. So A and B are not consecutive, but A and B are just two values in the array. And now we insert a value X here, okay, and X has got a value between A and B. Okay, so I can say that A is less than X, which is less than B. This is the relation. Okay, what can we say about this bit in X? Is it going to be 0 or 1? It can be anything, right? It can be 0, it can also be 1. X, this bit can be anything, right? It can be 0, it can also be 1, right? Because these bits are same in A and B, we are not sure about what is there in these places in X, right? So X can have a 0 here, X can also have a 1 here. right? Now let us consider both the cases. Let us consider a case where X has got a 0 in this place, and the other case where X has got a 1 in this place. Okay. Now, if I take XOR of all the pairs out of these three numbers, which one do you think is going to be the lowest? Which one out of these three pairs is going to be lowest? Can I say that the XOR of A and X will always be lower than the XOR of X and B and the XOR of A and B? Yes, because A and X have got 0, 0 here. So the first different bit is going to be after this, right? Correct. So this is going to be the smallest. If X has a value 1 in this case, then can I say that X XOR B is always going to be less than A XOR X and X and A XOR B? Yes, because in this case these two are going to have the same bit at this position and rest all the bits are same, right? So they will have the first different bit on more left right side, correct? So in any case, whether X has got 0 or X has got 1, we can see that we are always finding the minimum XOR between the adjacent pairs, between the closest pairs, right? Is this clear now? So now we can say with a proof that the closest XOR or the minimum XOR occurs between the closest element. So if you have got an array, you can just sort the array and you can just check the XOR of the consecutive numbers. Okay. Should we move to the next problem now? Okay, let us now try to solve a problem which was asked in Google Code Jam. Okay. So the problem says that you are given a distributed system. This was asked in Google Code Jam 19. Okay, the problem says that you are given a distributed system where you have a master server. Okay, and this master has got multiple slaves. Are you guys familiar with the master slave architecture? If you are not, I would recommend all of you to go and read about what is master slave architecture. Okay, so you have got this system where there is a master server and there are slave servers, but the job that is given to these servers is very trivial. You are entering a binary string in the master server. Okay, a random binary string is entered in the master server, and since the master server, this is a server which cannot store the things. So what it does, it sends one bit to every slave server. Okay, so if let's say if there are 4 slave servers, okay, so if you have one master server and then you have got 4 slave servers, so then in that case you will be entering a binary string of length 4. Okay, and the master server, it distributes each and every bit to one server. So 1 goes here, 0 goes here, 1 goes here, and 1 goes here. Then after a while, master server asks all the servers to return these values so that it can return the string to the user. So S1 returns 1, S2 returns 0, S3 returns 1, S4 returns 1. Okay. Now the problem here is some of the slaves are faulty. Some of the slaves are not working properly. So let us assume that if S2 is a faulty slave, it is not working properly. In that case, S2 will not be able to return this bit. So S2 will not return anything. Okay, S2 is not getting the instructions to return, so it will not return anything. So if S2 is faulty, when master asks for the string, he will only be getting 1 1 1 because 0 is gone now. Okay. If S2 and S3 is also faulty, in that case you will only be returning 1 and 1. Okay. If S3 and S4 are good, but S1 and S2 are faulty, in that case also you will be getting 1 and 1. Okay. So any server, which server is faulty, is not going to return anything. Is the problem clear to everyone? Or is the scenario clear to everyone? You have a master server and you are just inputting a binary string of length n, where n is the number of slave servers that you have. Master server distributes each and every bit in the exact same order to all the slave servers, and then asks for the bits to create the string again. Okay. So if the slave servers are faulty, they do not return anything. Okay. You have to identify, given the number of slave servers, you have to identify which of these servers are faulty servers. Okay, you are only given the number of slave servers. Identify the faulty servers. Is the problem clear? Will we be given the final string? Yes. So what you are given is that you can input any string. You can input a string of length n. So let us say that you are given two functions, read and write. Okay. This is a function write, which takes a string, a binary string of length n, and you have got a function read, which returns a binary string. The length can be less than or equal to n. So here the length should be exactly equal to n. Here the length will be less than or equal to n based on how many servers are faulty. Let us take an example. So let us say that number of slaves is 4. Okay, and out of them, so you have got 4 slaves, and out of them, slave 4 is the faulty slave. This is not given to you. You are only given that there are 4 slaves, and these two functions are given to you. Using these two functions, you have to identify which slave is the faulty slave. Okay. So if you enter a string, you just say write 1101. If this is the string that you enter, and after this, if you call read, right? If you call read, then the string that you get is 110, because slave 4 is faulty and this one will not be returned. Okay. If again you call write 1100, in this case, if you do read, you will be getting 110, because slave 4 is faulty, so you don't get this. Okay, any number of slaves can be faulty. There is this is not given that only one slave is faulty. Any number of slaves can be faulty. It might be possible that slave 3 and slave 4 both are faulty. In that case, you won't be getting the last two bits of your string. Okay. This is multiple answer question. No, Akshay, this is not a multiple answer question. This is actually supposed to be a coding question. This in Google Code Gen, you are supposed to code this question. Okay, Deval, that is in the right direction. What is the time complexity of your approach? At least one slave will be working. It might be possible that all the slaves are faulty, although you will get to know that in the first read call itself. But it is possible that all the slaves are also faulty. If they are faulty, they never return anything. Okay, we need to return number of faulty slaves or name. No, you have to return the names, because number is definitely clear in the first call itself, right? You can just subtract the length of the output from the length of the input, right? So number is clear in the first call. You have to return the names of all the faulty slaves. Okay, Deval, that is correct. Can you optimize that? Okay, now the question is, can we compare the bits and check the missing one? Okay, let us take a bigger example. Okay, if this is if we are talking about only 4 slaves, then this looks kind of obvious, right? If there are 100 slaves, and you are sending a string of size 100, okay, and in the output, let us say you are getting a string of size 81. So this has got 100 length, okay, and in the output you are getting a string of size 81. How do you recognize which all 19 slaves are faulty? Because they can be the first 19, they can be the last 19, or they can be the 19 in between. How do you compare? You have got a string of length 100, you have got another string of length 81. How do you compare these two strings? Are you comparing this one with this one, and you are saying that the first slave is correct? It might be possible that the first slave is not correct, right? Let us take another example. Let us say that you input all 1. Okay, if the input is all 1 and you send 100 ones, and then you are returning, you are getting in return 81 ones. These are 100 ones, and then in return you are getting 81 ones. How do you find which 19 slaves are not working? Take XOR of the return string with the original string. What will that return? So Preeti, are you getting the problem in the first place? The problem is that you have to you don't have to identify the count of the faulty slaves. You have to identify the names, right? You have to tell that S1 is faulty or S4 is faulty. Now, if you are comparing and you are saying that this one is correct, which means S1 is not faulty, it might be possible that at S1 was faulty and this input has this output is from S2 or S3 or S4. Yes, an image that is in the right direction. Okay, what could be the brute force solution here? You have got n slaves, okay, and you don't know how many of them or which of all these slaves are faulty. The brute force solution is check each and every slave one by one. If you input this string, right, where you have a single bit as a set bit and then all other as unset, and then if you input this, you know that this set bit is going to the first slave. This bit should be stored in the first slave. All the other bits are 0. When you read, you just have to make sure whether there is one bit set in the output or not, right? So you write this number where you have 1 and then rest all n zeros, okay? And then you do a read. If read returns a binary string of any length which has at least one bit set, can I say that S1 is not faulty? Or if read returns a string which has got all 0, can I say that S1 is faulty? Yes, because I am sending only one set bit which should go to S1, and when I do the read, it should be returned from S1. If I'm not getting any set bit, this means that S1 definitely is faulty because there was only and only one set bit in this, right? Battery 12%. I think that is sufficient. 12% battery is okay. Okay. What if we send all 0 bits? Srinivas, you will not gain anything from that, right? If you are sending all 0 bits, there is no identifier, and then you return, then you get, let's say, 3 0 bits in return. What do you gain? You don't gain anything, right? You only know that there are 2 bits which are slaves which are faulty, but you don't know which one. But if you are sending this string, and in return, let's say you are getting three unset bits, one thing you know for sure is that S1 definitely is faulty because there has to be at least one set bit in the output if S1 is not faulty. So this, if you send this string, you can make a decision whether S1 is faulty or not. Okay. Similarly, if you send another string of the same kind, so this is just to check whether S1 is faulty or not. Similarly, to check S2, you can set the second bit and keep all the remaining bits as unset. And then this will check whether S2 is faulty or not. Because in the return, in the output that you are getting, if there is no bit which is set, then you are sure that S1 is faulty because the only set bit was sent to S2. And if it is not getting returned, then S2 definitely is faulty, right? Similarly, if you want to check S3, you can set a set bit in the third position. If you don't get the third bit as set, you can definitely say that S3 is faulty. Now, does this make sense to everyone? Correct. Yes, Suji, that is totally correct. How many queries we will have to do? What is the total number of queries if you are going to go by this approach? Or what is the time complexity? For every server, for every slave server, we are doing a different query, right? For every slave server, I'm trying a different string, which means that for every slave server, I will have to do a query So I will be doing exactly n queries. So time complexity becomes order n. Okay, correct. N is the number of slaves. Correct. Now, can we optimize this thing? Can we do this in less than n queries? Okay, now some of you have got some optimizations. Some of you are saying that let us set 2 bits one, and now you can just check whether the first is set or the last is set. Based on this, you can decide on 2 servers at once, right? This might also work. You can actually every query can give you output about 2 servers. But let's say if there are only 2 servers, S1 and S2, and if you give this as the input and you are getting 1 in the result, how do you know whether S1 is faulty or S2 is faulty? So this again is going to have some edge cases which you will have to deal, right? Okay, now guys, if let us say that some servers are faulty, right? Let us say that we have got 4 servers, or let's say we have got 5 servers. We'll make a very interesting observation here. Okay, if we have got 5 servers, out of which S2 and S4 are faulty, these 2 are the faulty servers, rest all are correct. Okay, these 2 are the faulty servers. Now if I am writing a string 11111, what is the output that I'm going to get? The output that we are going to get is S2 and S4. These 2 will be missed out. So the output that we get is 111. Okay. Then if I enter another number, let's say 10101, what is the output that we are going to get? We are going to get 111. If I add another number, if I input, let's say 10000, what is the output that we are going to get? We get 1 and then 00, right? If I enter 00111, what is the output that we get? We get 0 and then 1 and then 1. Are you able to observe one thing, that in all these input, since S2 is faulty, this whole column is missing from the output, right? The first column is present as it is, right? 1110, this column is present as it is. Second column is completely missing. Third column is again present as it is. Fourth column again is completely missing. So we have got 2 voids in the output, right? Rest everything is totally correct. First column is totally matching. Second is totally gone. Third is matching. And then fourth is gone. Fifth is also matching. Correct? Can I use this column to uniquely identify a server? Vignesh, that is also a correct approach. Using binary search will also solve this problem, right? So can we use this column which is missing to uniquely identify a server? What if I create a pattern in such a way that this column is representing a number? Okay, because this is my input and this is my output. Okay, if I can somehow make sure that this whole column is meaning something, this is giving if let's say this becomes a unique identifier, this is representing the ID of that slave, right? So for example, if I number these slaves from 0 to 4, okay, and now I just give in input, I give the input such that the first column is always going to have all 0 values. Okay. Then the second column is always going to have values in this order. The third column is going to have values like this, and the fourth column is going to have values like this, and then the fifth column is going to have values like this. Okay. If I send the input in this order, right, what will be the output? If I'm sending the input in this order and slave S3, S2 and S4 are empty, this is the first string. The output that I get is 000. Then in the next one, the output that I get is 0, 0, 1. Then the next output is 0, 1, 0. And then the next output is 0, 0, 0, right? Again, this whole column is missing from here. And this whole column is also missing from here, right? What does this number represents? What is this number in decimal? If you consider this first column as a binary string, what is the representation of this number in decimal? This is nothing but 0. What is the representation of this number in decimal? This is nothing but 1. What is the representation of this number? This is again nothing but 2. This is 3. This is 4. Okay. In the output, what are you getting? In the output, you are getting the first column, which is representing 0, which means slave 0 is totally fine, right? We had sent all these strings in a way that each and every column is making a pattern which can be used to uniquely identify all the slaves. If I'm sending all zeros in the first column, this means that this is for slave number 0, right? Then I am using the second column to uniquely identify the first slave. I am using the third column to uniquely identify the second slave. If a column is missing, I know that a number is missing. So I have 0 here, I have 2 here. This column is representing 2. I don't have 1 here, right? I don't have 3 here. I then have 4. So now I can say that the slave which is numbered as 1 and the slave which is numbered as 3, the 1 and 3, they both are faulty. Does this make sense to everyone? So we are using the bits to uniquely identify the numbers, and we are actually creating a mask of these bits, right? If two columns have same numbers, is that possible? Will two columns ever have same numbers? Can you have two numbers which have the exact same binary representation? Can you have two numbers which can have exact same binary representation? No, that is not possible, right? So no two columns are going to have same value. Okay. Now the question is, how many queries we'll have to do? If you go by this approach, how many queries are required? Just pay attention that these are not the queries. This is one query. This is the other query. This is the third query. This is the fourth query. How many queries are required? In this case, to get how many queries are required, just again observe what we are essentially doing. We are representing each and every slave in binary form, right? So the length of the query is equal to the number of slaves. But the number of queries that we are making is equal to the number of bits which are required to represent these numbers in binary, right? How many bits do we require to represent a number n in binary? How many bits are required to represent a number n in binary? Exactly log base 2 n bits. So how many queries do we need to send now? We need to send exactly log base 2n queries. Okay, if there are 1000 slaves, how many queries do we need? If there are 1000 slaves, what is the number of bits in which we can represent 1000? We can represent thousands inside 32 bits, right? So you don't need to send more than 32 queries. In the initial approach, we were sending n queries. That means for 1000 bits, you were querying it how many times? Sorry, for 1000 bits, you can actually do it in 10 digits, right? 2 raised to power 10 is your 1024. So any number less than equal to 1024 can be represented in 10 bits. So if you have got 1000 slaves, then you can do it. You can find the faulty slaves only using 10 queries. In the initial approach, you were doing 1000 queries, right? Okay. So does this thing make sense to everyone? Now there is another approach to solve the same problem, which some of you have already written in the comment section. You can also solve this using binary search. Okay, we can maybe reiterate over this when we do binary search classes, but I would recommend you guys to think about that. Okay, you can maybe have this type of a pattern where you separate ones and zero, and now you can count how many faulty slaves are present in the first half, how many faulty slaves are present in the second half, and then you can do the exact same thing in the first half, and then you can do the exact same thing in the second half, and you can again find out how many faulty slaves are there. Okay, so that is another approach using binary search. You can try to think about that approach yourself. But is this thing clear? Pseudocode, did you get the idea, Shubha? If you get the idea, you can just Google this problem. You can Google, or maybe we can post the link in the chat group, the problem where it was asked in Google Code Jam, and then you can attempt it there. So I hope you learned something in today's lecture. The last 1 hour was useful for you. If you find it useful, please do like the video. And if you want any topic to be covered, please write that in the comment section. Okay.
Hey guys, I'm Bhavya. In this video, I will discuss the very easy problem and the medium problem of bit manipulation. So let's look at the easy problem, or equals or. You are given an integer a. Find the number of ordered pairs xy such that xy is greater than equal to 0 and less than 2 raised to a, and they satisfy the following condition: x or y is equal to x or y. In other words, the bitwise OR of both these numbers is equal to the bitwise OR of these numbers. Since the answer can be large, calculate it modulo 10 raised to 9 plus 7. A is less than equal to 10 to the power 5 and greater than equal to 0. So let's look at the first sample. So the first sample is a is 0. So we have a valid pair 0 0, and when a is equal to 1, we have three valid pairs 0 0 0 1 and 1 0. So let's look at the solution approach. So first thing to notice is that x and y are a bit numbers. So for example, if a is 3, we will have a number comprising of 3 bits. That is all the numbers from 0 0 0 to 1 1 1. That is 0 to 7. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So these are the possible values of x and y. Now the condition is x or y is equal to x or y. So one thing you can notice is if these two numbers are equal, each bit in x or y and each bit in x or y should be same. So we can solve it for each bit by bit individually. So now let's find what is the condition. So if the ith bit in x is 0 and the ith bit in y is 0, so x or y will be 0 and x or y will also be 0. If it is 0 1, then x or y will be 1, x or y will also be 1. If it is 1 0, then x or y will be 1 and x or y will also be 1. But if it is 1 1, x or y will be 1 but x or y will be 0. So we can say that these are the possible values of ith bit in x and y. So here we have x, so x should be a 3-bit number, and y should be a 3-bit number if a is equal to 3. So if we treat each bit individually, what we can have is these three cases 0 0 0 1 or 1 0. So we can say that for each bit we have 3 choices. So our final answer will be 3 raised to a, because for each bit we have 3 choices. So for example, this case, we can say that we can have first bit 0 in both the cases, also first bit 0, second bit 0 in both the cases, and third bit 0 in both the cases. So this will be a valid pair, that is 0, 0 will be a valid pair. We could have other cases as well. Let's say we take 0 0 first, then we take 1 0, and then we take 0 1. So we will see that this corresponds to 2, 1, and you can see that the OR of bitwise OR of 2, 1 will be 3 and the bitwise OR of 2, 1 is also 3. So they are equal. So we can say that our final answer is 3 raised to a. Now you can calculate 3 raised to a using, let's say, binary exponentiation, or you could just loop from 1 to a and keep multiplying 3, because a is less than equal to 10 to the power 5. So you can do it either in log of a or you can do it in O of a, and either will work. So let's look at my implementation. So I have used modular exponentiation here. That is, I will calculate 3 raised to a modulo 10 raised to 9 plus 7, because 3 raised to a will be a very big number. So we need to calculate it modulo a given prime number 10 raised to 9 plus 7. So the idea of modular exponentiation is if a is even, you will calculate 3 raised to a by 2 and square it. Otherwise, if it is odd, you will calculate 3 raised to a minus 1 by 2 and you will square it. So this will give us 3 raised to a minus 1, and then finally multiply it by 3 as well. And you can do it recursively. So you will call the function for a by 2 or a minus 1 by 2 recursively, and your complexity will be log of a. So let's move to the next problem, the medium problem. Diagonally powerful matrix. Robin purchases an integer matrix A of size n cross m. He wants to make the matrix diagonally powerful matrix, but he can only use the Below operation, select any element, multiply or divide it by 2. Take floor by dividing it by 2. Matrix is called diagonally powerful matrix if all the elements starting from top or left and ending at bottom or right is powerful. Diagonal is powerful if bitwise end of the numbers or the elements in the diagonal is greater than 1. Find and return the minimum number of operations required to convert the matrix into diagonally powerful matrix. So n cross m is less than equal to 10 power 4 and aij is less than equal to 10 to 7. So the first case is 2 to 1, 10 4 1 and 11 3 2. So we will change the 1 at 1, 3 to 2. Also we will change the 1 at 2, 3 to 2 as well, and we will change the 4 at 2, 2 to 2. So we'll require 3 operations. So let's actually look at the same example and try to find out the solution approach. So let's copy the same example, 2 to 1, 10 4 1 and 11 3 2. 2 to 1, 10 4 1 and 11 3 2. So we have these diagonals. First diagonal, then this diagonal 2 1, then this diagonal 2 4 2, then 10 3 and then 11. So you want that bitwise end of each diagonal is greater than 1 and you can do some number of operations. So one thing you can notice is that each element will be present in exactly one diagonal. So we can actually solve each problem independently. That is, we are given some arrays and we need to do some operations on each element of the array so that bitwise end of the complete array is greater than 1. So we can actually solve each problem independently. So 1 2 1 2 4 2, 10 3 and 11. So for a single length array, if the element is not equal to 1, for this case, we will require 0 operations because the bitwise end of all the numbers is already greater than 1. Otherwise, if it is equal to 1, we will multiply it by some number, let's say 2, 4 or anything, so that the bitwise end is greater than 1. So we'll require 1 operation. Now for this case 2 1, currently the bitwise end is 0. So we can change this 1 to 2 and we will get the bitwise end as 2. So we'll require 1 operation here. Now for this case 2 4 2, we can divide this 4 to get 2. That is, we will divide it by 2 to get 2. So our array will be 2 2 2 and the bitwise end will be 2. So we'll require 1 operation here as well. Now for 10 3, bitwise end is, so the bitwise binary representation of 10 is 1 0 1 0 and the binary representation of 3 is 1 1. So the bitwise end is 0 0 1 1. Bitwise end is 0 0 1 0. That is 2. So it is greater than 1. So it requires 0 operations here. So the total number of operations required is equal to 3. So now since we have reduced the problem to an array, we don't need matrix. So our problem is that we are given an array. We need to divide some elements or multiply some elements by 2 such that the bitwise end is greater than 1. So we'll take some case, let's say 10 3 4 7. So we'll take this case and we will find the minimum number of operations required in this array so that the bitwise end is greater than 1. Now one thing you can notice is if the bitwise end is greater than 1, there will be at least one bit not equal to the lowest bit which is equal to 1, because if the lowest bit is equal to 1, then the bitwise end will be equal to 1, but we want it greater than 1. So there should be at least one bit which is not equal to first bit, which is set. So what we can do is we will fix that bit and then find the operations required to set that bit in at each index. So for example, if our number is 1010 and we are setting, let's say this is 0th bit, this is first bit, this is second bit, this is third bit. So let's say we are setting second bit. So what we can do is, so one thing you can observe is both the operations are actually equal into shifting right or left. So for example, if we are multiplying the number by 2, we will left shift our element. So for example, if we multiply 10 by 2, our final number will be 10100. If we divide it by 2 and then take the floor, we are actually right shifting our number. So our number will be 101. So that is, we are actually left shifting or right shifting and it is equivalent to an operation. So what we can do is we can iterate over all the bits in the number and find the number of operations required to move that bit to our final destination. So for example, if we want to move all the bits to second position, so we'll iterate over 10. We see that the first bit, 0th bit is off, so we don't have to do anything with it. The first bit is on. So we have to move the first bit to 2. So how many operations we will require? We'll simply left shift it once. So we'll require 1 operation for this case. Now here it is 0, so we'll ignore it. Now here it is 1. So how many operations will be required to move this bit to second position? So we can simply right shift and we'll get 101. So we'll require 1 operation for this case as well. So the minimum number of operations required are 1 to set the second bit on. So in the general case, if we want to move the, let's say our optimal position of placing the bit is I and the jth bit is on. So to move the jth bit to ith position, we'll require absolute of j minus I operations, because we can either left shift or right shift by 2. That is, move that bit to either to the left or to the right by 1 position in 1 operation. So let's actually take one more case. So for example, if our number is 100101. So this is 0th bit, this is first bit, second bit, third bit, fourth bit and 6th bit. And let's assume that we are moving all the numbers to third bit. That is, we are setting the third bit on in every number. So we'll iterate over this number. The 0th bit is on. How many operations will we require to move this 0th bit to third bit? We'll require 3 operations. For then this bit is again on, so we'll require one operation to move second bit to third position. So our current optimal answer is 1. And if we consider 6th bit, we will require, sorry, this is 5th bit. So if we consider 5th bit, we will require 5 minus 3, that is 2 operations to move 5th bit to third position. So our current optimal is 1. So we'll see that the number of minimum operations required will be 1. So finally our algorithm is that we will find the minimum number of operations to set ith bit for every I from 0 to 26, because 26 is the maximum number, or 25. Let's say you find some x such that 2 raised to x is greater than 10 raised to 7, so that we are sure that any bit won't be set after x. So x here comes out to be something around 25 or 26. So you can take either value. So let's actually find the answer for this case. So the bitwise representation of 10 is 1010. For 3 we have 0011. For 4 we have 0100. For 7 we have 0111. So let's say we are setting first bit on in each number. Remember that we won't consider the case where we set the 0th bit on everywhere, because in that case the bitwise end will exactly be equal to 1, but we want the bitwise end to be greater than 1. So first we'll check if how many operations will be required to set the 0th bit on. So first take this, the first bit on. So first take this case. We have 0, 1, 2, 3. So we'll require 0 operations here because the first bit is already on. Similarly, we'll require 0 operations here. Now here we see that 0, 1, 2, the second bit is on. So we'll require 2 minus 1 operations here. That is 1. Again, first bit is on. So we'll require 0 operations here. As you can see, the total sum will be 1. So that is the number of operations required to set the first bit will be 1. Now let's find the number of operations required to set the second bit. So our current minimum value is 1. So the number of operations required to set the second bit. Now here, second bit is off. So we can either move 1 to 2 or 3 to 2. So in either case, we'll require 1 operation. Now the second bit is again off. So we can move this one here or this one here. In that case, we'll require 1 operation. In this case, we'll require 2 operations. So the minimum operation is 1. Now second bit is already on here. So we'll require 0 operations here. Again, second bit is already on here. So we'll require 0 operations. So total number of operations required here will be 2. But it is greater than our optimum value. So we'll consider the case where we set the third bit on. Here the third bit is already on. So we'll require 0 operations. Here the third bit is off. So we can either move this bit here or this bit here. But we'll take minimum number of operations to move this bit here. That is, we'll require 2 operations. Now here we can move this bit here in 1 operation. Now here we can move this bit here in 1 operation. So the total number of operations required will be 4. But it is greater than our current optimum. So we have actually iterated over all the cases. You can also consider, let's say, other bits as well. But you will see that the optimal value will be 1. So we will require 1 operation so that the bitwise end is greater than 1. And finally, we will just sum up this value for each array obtained and return our answer. So let's look at the implementation to make it more clear. So we set n as n and m and answer as 0. Now we iterate from 0 to n. So the idea is, let's say this is our array. So we have this matrix 0, 1, 2 and 0, 1, 2, 3, let's say. So first we find all the elements in the diagonal. So our diagonal can either start from this elements and then move 1 step, or it can start from here and then move 1 step diagonally. So we start from 0 to n. So now we set row as 0 and column as 0. That is, we are at 0, 0. Now while r is less than n and c is less than m, we will append arc to our vector and move to and increment r by 1 and c by 1. That is, now we'll be at 1, 1. Again, we will set a11. We'll append a11 to our vector and we'll move to a22. Now we'll append a22 and we'll move to 3, 3. But notice that 3 will be outside of the, because we don't have any row 3. So it will be outside of this matrix. So we'll now consider the case where we take 1, 0. So we start from 1, 0 and now we append 1, 0 and then we move to 2, 1. So after appending 2, 1, we move to 3, 2. But 3, 2 is outside of the array, so we stop. So now we go from 2, 0. So from 2, 0, we move to 3, 1. But 3, 1 is outside of the array, so we stop. Now we consider these diagonals. So we start from 0, 1. We append 0, 1 and we move to 1, 2. Now from 1, 2, we move to 2, 3. From 2, 3, we move to 3, 4. But in that case, it will be outside of this matrix. So we'll start from 0, 2. From 0, 2, we move to 1, 3. From 1 to 3, we move to 2, 4, which is outside. So we stop. Now we start from 0, 0. From 0, 3. From 0, 3, we move to 1, 4, which is outside of this matrix. So we stop. So in this way, we actually found all the elements in the diagonal. So you can see it in the code. While r is less than n and c is less than m, we append a of r, c and increment r by 1 and c by 1. Now we add the cost of v to our answer. So we'll see how to find the cost of v as we discussed. Again, we'll start from 1 to m. That is these 3 places or m minus 1 places. Now our current row is 0 and the column is I. So while again the same thing, while r is less than m and c is less than m, we append arc and increment r by 1 and c by 1 and add cost v to our answer and we return the answer. So the only thing left is to find the cost. So we assign our cost as infinity, that is 1e9 or some big number. Now we iterate from 1 to 25, that is the bit which we want to set. So this is the current value, that actually stores the number of operations required to set the ith bit on. Now we iterate over all the elements in the vector. Now we'll find the minimum number of operations required to set the ith bit on in this element. So we iterate over all the bits. If that bit is set in our number, so kth bit is set in our number and we want to set ith bit, so we'll require absolute of I minus k operations. So we find the minimum, so that we find the minimum number of operations required to set the ith bit on in our number, and we finally add this value to our current answer. And since we want the minimum number of operations, we find the minimum over all the bits, that is minimum value, minimum number of operations to set any bit on, and we finally return this answer. So what about the time complexity? So as you can see that we will iterate over each element once, and now we have a loop of 26 square as well. So our time complexity will be 26 square into n into m, because for, let's say, what is the time complexity of this cost function? So the time complexity of this cost function is 26 square into mod of v, and now we will add it over all the vectors. So this comes out to be 26 square into sum of vector sizes, which is equal to n into m, because each element will be present in exactly one vector. So time complexity is 26 square into n into m. So I hope this was clear to you. Hey guys, I'm Bhavya. In this video, I'll describe the easy problem and the hard problem of code drift on bit manipulation. So let's look at the easy problem. Robin buys an integer matrix A of size n cross m. His mother asked him to perform the following operation exactly once, such that the bitwise XOR of the elements is maximized. Select any row or column of the matrix and decrement each element of the selected row or column by 1. Return the maximum value of bitwise XOR of elements after performing the above operation. So n cross m is 5 into 10 to the power 5 and aij is less than equal to 10 to the power 9. So for the first case, 2, 3, 4, 5, we can select second row and decrement each element. So we'll get 2, 3, 3, 4. Now XOR of elements will be 2 XOR 3 XOR 3 XOR 4. 3 XOR 3 will be 0. So 2 XOR 4 is 6. So answer is 6. Maximum value is 6. So let's look at the solution approach. So let's assume that our matrix is of size 2 cross 3. So it's a bigger matrix, 2, 1, 4 and 3, 2, 5. Now we can select either a row or a column and decrement all the elements by 1. And we can do it exactly once. That is, we have to do one operation. So what happens when we do an operation? Let's say we select first row and then do an operation. So currently our XOR was 2 XOR 1 XOR 4 XOR 3 XOR 2 XOR 5. Now when we do an operation, we want to exclude the contribution of this 2, right? Because we changed this 2 to 1. So we will change this to 1, 0 and 3 when we do an operation here. So we want to exclude the contribution of this 2, this 1 and this 4. Now how do we exclude the contribution of a XOR? We can simply XOR it again, because we know that XOR X is 0. So if we do 2 XOR 1 XOR 4 again, we will be left with 3 XOR 2 XOR 5. Now again, we know that the matrix elements are 1, 0, 3. So we can again XOR with 1, then XOR with 0 and then XOR with 3. And this will be our final value. So one thing you can notice is that you can then club these terms. So this was our initial XOR. Let's call it X. So X is our initial XOR. Now you will XOR it with each element will contribute 2. So for 2 will contribute 2 XOR 1, because we want to exclude 2 and include 1. Then this 1 will contribute 1 XOR 0, because we want to exclude 1 and include 0. And similarly 4 will contribute 4 XOR 3, because we want to exclude 4 and include 3. So if we know the initial value X, we can store the value. Let's say the value is aij, XOR aij minus 1 for all the elements of a given row or a given column, and then simply XOR it with X and find the maximum value. So let me actually describe this idea using an example, the same example. So let's find the initial value. So currently our value is 2 XOR 1 XOR 4, which is 2 XOR 1 is 3, 3 XOR 4 is 7, then 7 XOR 3 is 4, then 4 XOR 2 is 6. Now 6 is 1, 1, 0 and 5 is 1, 0, 1. So currently our XOR is 3. So X is 3. The total XOR of all the elements is 3. Now if we select this row, this will contribute 2 XOR 1, XOR 1 XOR 0, XOR 4 XOR 3. So this will be 2 XOR 1 is 3, 1 XOR 0 is 1 and 4 XOR 3 is 7. So 3 XOR 1 is 2, 7 XOR 2 is 5. So we get 5 here. Now if we consider this row, this will contribute 3 XOR 2, XOR 2 XOR 1, XOR 5 XOR 4. So this will be 3 XOR 2 is 1. Now 2 XOR 1 is 3. So 1 XOR 3 is 2. Now 5 XOR 4 is 1. 2 XOR 1 is 3. So this will be 3. So when we considered each row, we have actually taken each element exactly once. Now we will similarly do it for columns as well. So for columns, we have the contribution as 2 XOR 1, XOR 3 XOR 2. So 2 XOR 1 is 3 and 3 XOR 2 is 1. So this will be 2. Now for this column, this will contribute 1 XOR 0, XOR 2 XOR 1. So 1 XOR 0 is 1, 2 XOR 1 is 3 and 1 XOR 3 will be 2. So this will contribute again 2. Now if we consider 4, 5, so this will contribute 4 XOR 3, XOR 5 XOR 4. 4 XOR 3 is 7. 7 XOR 5 is, so 7 is 1, 1, 1 and 5 is 1, 0, 1. So 7 XOR 5 is 2. and 2 XOR 4 is 6. So this will be 6. Now to find the maximum value, these are the possible values we can XOR with 2 to 6. So there will be total n plus m values. That is, if there are n rows and m columns, so we have 2 rows and 3 columns. So we get 5 values, 2 values corresponding to row and 3 values corresponding to columns. So initially x is 3. Now we will XOR x with each of these 5 values and find the maximum value. So let's do it. Now 3 XOR 2 will be 1. When we do 3 XOR 5, we get, so 5 is 101, 3 is 11. We get 6. Now 3 XOR 2 is again 1. Then 3 XOR 3 will be 0. This 3 XOR 3 will be 0. And when we do 3 XOR 6, so 3 is 1 1 and 6 is 1 1 0. So this will give us 1 0 1, which is 5. And as you can see, the maximum value is 6. So we'll return 6 as our answer. Now what will be the time complexity? So first we find x by iterating over all the elements of the array. So that will be O of n into m. And now we find the XOR value for each row and column. So that will be 2 into n into m. N into m for row and n into m for column as well. Because for each row, we will iterate over all the elements in the row. And similarly for each column, we will iterate over all the elements in the column. So total time complexity is n into m. So let's look at the code to understand it more better. So we initialize n and m, the number of rows and number of columns, n being the number of rows and m being the number of columns. Now r of n will store the XOR value for each row and c of m will store the XOR value for each column. Now we'll iterate over all the elements. X is the total XOR value of all the elements in the matrix. So x XOR equal to aij. Then aij will contribute aij XOR aij minus 1 to ith row value, and it will contribute the same value to jth column value. Now we initialize answer as 0. So we iterate over all the rows and we find maximum of x XOR ri. And similarly we'll iterate over all the columns and we find maximum of x XOR ci and we return that answer. So in this way we can do it. So let's move to the next question, the hard problem. You are given an array A of length n. Consider that the array is one index. You need to find sum of ai and aj and ai plus aj for all pairs ij such that I is greater than equal to 1 and I is less than j and j is less than equal to n. N is 2 into 10 to the power 5 and ai is less than equal to 10 to the power 9. So for example, if a is 8, 9, we only have one pair, that is 8 and 9 and 8 plus 9. So which will be 0. Similarly for 1, 3, 3, we have 3 pairs, 1, 3, 1, 3 and 3, 3. So for 1, 3, we get 1 and 3 and 1 plus 3, which is 0. For 3, 3, we get 3 and 3 and 3 plus 3, which is 2. So the answer, sum of all the values will be 2. So let's look at the solution approach. So first, let's actually take one example. Let's say our array is 5, 2, 4, 7. So each number is 3-bit. No number will have more than 3 bits. So binary representation of 5 is 101, binary representation of 2 is 010, binary representation of 4 is 100, binary representation of 7 is 111. Now why are we writing the binary representations? Because we can actually solve this problem bit by bit individually. That is, we'll find the contribution of each bit. So our cost function is, we need to find sigma ai and aj and ai plus aj. Obviously we could do this in O of n square by iterating over all the pairs ij and finding the sum, which will be O of n square. Now the beautiful thing about bitwise operation is that we can actually iterate each bit independently. So now let's find the answer for ith bit. How much ith bit will contribute to this sum? So if we consider 0th bit, so we have 1 here, then 0 here, then 0 here, and then 1 here. Now for this to be 1, because it will only contribute if this bit is 1. So we want the ith bit to be 1, and the number of pairs is that this will be 1 for the ith bit or the xth bit. Let's call it xth bit to avoid confusion with this I. So we want the xth bit to be 1. So we iterate for over all x from 0 to the maximum number of bits. In our original problem, we have ai is less than equal to 10 to the power 9. So there will be around 30 bits because 2 raised to 30 is greater than equal to 10 to the power 9. But for the purpose of understanding, we can say that our numbers only have 3 bits, right? Because as you can see, the maximum number of bits are 3. So we will iterate over all the bits, that is our x will range from 0 to 2, will iterate from 0th bit to 2nd bit, and then find the contribution of each bit. So for example, there are p pairs where xth bit is 1, then this will contribute p into 2 raised to x to our sum. So let's actually try this in our case to understand the example more clearly. So 1001. So for the xth bit to be 1, xth bit should be 1 in ai and aj both, because if it is 0 in either of the numbers, this will contribute 0 because of the properties of AND. All the numbers should be 1. So for this case, we can only take these two numbers as a pair, because if we take any one of the numbers, it will contribute 0 because that bit is 1. So now, given these two numbers, we also have to check if ai plus aj will have xth bit set or not. Now if we are considering 0th bit, we know that ai plus aj will have ith bit on only if one of them is 0 and one of them is 1. Because if you take these two numbers, we have 101 and 111. So when we add this will be 1 plus 1 2. So this will be 1 0. So if you know how binary additions work, we will add this and we get 0 here because this will be 2 and so we'll have 1 as a carry here. So this will be 1 plus 1, 2. So we'll have 0 and 1 as a carry here. And finally we have, so the remainder is 3 and we get 1 as a carry here. And finally we put 1 here as well. You can actually see it as well that the sum of 7 plus 5 will be 12. And here also we get 12. And you can see that the ith bit is, that is x the bit is 0th bit is 0 here. So 0th bit will not contribute anything to our answer. Now consider first bit. So for first bit we have 0, 1, 0, 1. Again, we can only take these two numbers. So we'll also have to check if the numbers at this position that are 2 and 7 will have first bit set. So we have 2 plus 7 which is 9. So the binary representation of 9 is 1, 0, 0, 1. Now first bit is not set here. So also first bit will contribute 0 to our answer. But we still haven't got to algorithm yet because we have only seen that there are two numbers. So we can check two numbers easily. But what if there were multiple ones? So if all of these were ones, we will have to check NC2 pairs. So still that's not good. We will have to check NC2 pairs. So we need to find a better way to check if we can select numbers such that their sum will have x the bit set or not. So consider the second bit now. Now for the second bit we have 1, 0, 1, 1. So here we have three numbers. So we can take any 3C2 numbers, that is any pairs out of these three numbers, which is 3. So if there were, let's say, n bits on, we'll have to take NC2 pairs, which will be n order of n square. So how to find if AI plus AJ will have x the bit set or not? So let's actually take any two numbers. So we have 5 and 4. So we have 5, 2, 4 and 7. Now 5 and 4 both have second bit set. Now the binary representation of 5 is 1, 0, 1. Binary representation of 4 is 1, 0, 0. Obviously, second bit will be set in both the numbers. Now if we add them, we get 1, 0, 0, 1. So second bit is not set here. But how do we find it without adding them? So one thing you can observe is only consider the first I minus 1 bits. So for 5 and 2, we have 1, 0, 1 and 1, 0, 0. So we'll consider only this bits which lie before it. So we get 0, 1 and 0, 0. If their sum is less than 2 raised to x, if their sum is less than 2 raised to x, that is, we won't have 1 as a carry here because we definitely want 1 as a carry here. If we get 1 as a carry here, then we will have something here and then we will have 1 here and we'll give 1 carry there, right? So this bit will be set here. If their sum is greater than equal to 2 raised to x, if it is less than 2 raised to x, then we won't get any carry here. It will something like, let's say here we have 0, 1 and then we will add 1 and 1 which will get 0 and we'll have 1 carry here. So this bit will be 0. So to actually give an example, consider 4 and 7. Actually consider 5 and 7, right? So 5 is 1, 0, 1 and 7 is 1, 1, 1. So if we consider only this bits, 0th bit and first bit, so we have 1, 0, 1 here and 1, 1 here. So when we add them, their sum will be, so 1, 1, 0 and then 1 here and then 1, 1, 0 and then 1 here. So their sum will be greater than or equal to 2 square because we need to check for second bit, which is 4. So their sum is exactly 4 and that will actually set the ith bit. The idea is if we add these numbers and their sum is greater than equal to 2 raised to x, then it will definitely give 1 as a carry here. And when it gives 1 as a carry here, we will have 3 ones. So their remainder will be 1 here. So we'll have this bit on. Otherwise, if their sum is less than 2 raised to x, if their sum is less than 2 raised to x, we won't get any carry here because it will be something like, it will only take the first x bits, that is 0th bit and first bit. So if our sum is less than 2 square, that is 3. If our sum is less than 3, then only the first 2 bits, that is 0th bit and first bit will be set. Also one thing you can see that since this number, if we consider the first x bits, this will be less than 2 raised to x. This will also be less than 2 raised to x. So their sum will be less than 2 raised to x plus 1, right? If their sum is less than 2 raised to x plus 1, then it will only have x plus 1 bits. It won't have more than x plus 1 bits, right? So it is important because if their sum is greater than equal to 2 raised to x, then we will definitely have a 1 at the xth bit in their sum. So let's actually try it for the example. So what we can do actually is take the numbers modulo 2 raised to x, because when we take a number modulo 2 raised to x, we ignore all the bits from x to higher bits. So for example, for 101, if we take modulo 4, we get 01, that is 1, because 101 is 5. So we actually ignore the bits from 2 to afterwards. Now we just need to check if their sum is greater than equal to 2 raised to x. So for this case, when we have the ith bit set, how many numbers have second bit set? They are 5, 4 and 7. So we will take the remainders with 2 square, which is 4. So we get 1 here, 0 here and 3 here. Now we just need to find the number of pairs whose sum is greater than or equal to 4. And this can actually be done by 2 pointers by sorting this array. So we will sort this array, we get 0, 1 and 3. Now we take left pointer here and right pointer here. So we check our sum. The sum is less than 4. So we move our left pointer because we want to increase our sum. So we move our left pointer. Now our sum is greater than equal to 4, right? So we'll add R minus L to our answer because we know that AL plus AR is greater than our current sum, the required sum. So this will be true for all the, so we can actually change this AL to any number from AL to AR minus 1. And the sum will be greater than equal to S because the array is sorted. So we have how many numbers between L to R minus 1? We have R minus L numbers. So we'll add R minus L to our answer and then increment our, so R minus L is 1 here. So we get 1 here and then increment our left pointer. So increment our left pointer. Now left pointer and right pointer are equal, so we break. Also, you could do any other method like sorting the array and finding the upper bound or something like that, because that is actually a standard problem. Given a sorted array, find the number of pairs whose sum is greater than equal to S. That is a standard problem. So as you can see, here we get 1. That is, we have one pair whose sum is greater than equal to 4. So there is only one pair where the second bit will be set. So this will contribute 1 into 2 square, which is 4 to our answer. So the final answer is 4 because all the other bits contributed 0. So let's look at the code to make it more clear. So we assign n as a dot size. Now we assign answer as 0. We'll iterate over all the bits. That is, we'll iterate from 0 to 30 because there can be at most 30 bits. Now we use the vector in which we store the numbers. So we clear it. Now we will iterate over the array. If the ith bit is set in our element, we append j modulo 2 raised to I, because j modulo 2 raised to I will contain only the first I bits, that is bits from 0 to I minus 1. And now we'll sort our vector and then we'll find the number of pairs in this vector whose sum is greater than equal to 2 raised to I. And if there are, let's say, k pairs, we will add 2 raised to I into k to our answer. We also have to take modulo 10 raised to 9 plus 7 as well in order to avoid overflow. And finally, we'll return answer. Now the only thing left is to check the number of pairs whose sum is greater than equal to 2 raised to I. So we pass sum. Now, since the array is sorted, we pass L as 0 and write as v dot size minus 1. That is, L will point to the leftmost element and R will point to the rightmost element. Now result is the number of pairs. So while L is less than R, if VL plus VR is greater than equal to sum, we will add R minus L to our result. And if it is greater than equal to mod, we will subtract mod in order to avoid overflow. Also, we will decrement our R. Otherwise, we will increment our L. And finally, we will return our result. So I hope this was clear to you. Thank you for watching this video.
So let's get started with our today's lecture on linked list. Linked list is also a very important topic from the interview point of view. So to get comfortable with linked list, you have to attempt multiple questions because it's tricky to deal with all the pointers. Sometimes it's confusing, but once you start with it and you practice with it, it's great. Okay, you will get comfortable. So let's get started. Now, why linked list? Why have we come to linked list? So it's like we started with arrays. Let's talk about arrays. So why not we continue with arrays? So the problem with arrays was that its size is fixed, right? Size fixed, that's a problem. So if I want to insert more elements, I have to create a new array with a greater size. So that's problematic, right? What else can I do? I can basically create a dynamic array instead of that. A dynamic array, right? So in dynamic array, what happens? So if I have an array of size, let's suppose 5, now all of this is filled. And if I want to enter one more element, what happens is an array gets created double the size of this array. So an array of size 10 will get created and all of this will get copied into this newly created array, and then we can insert the element that we would want to insert, right? Now the problem with this is that, let's suppose now I don't want to enter any more elements, so this space will get wasted, right? This space will get wasted, and that's a problem, right? Wastage of space is also one of the major problems. So now we cannot do anything. The dynamic array will anyway get twice the bigger of the previous array. So that's a problem with dynamic array. So here comes the linked list now. Here comes the linked list. Okay. In linked list, what happens is we don't have to reserve any space. Okay. We don't have to reserve any space. Rather, so what happens? Let's see the logical view. So this is I am taking as the memory. These are the memory cells. Okay, so you will agree with me that in array, the elements are stored in contiguous blocks of memory, right? Elements are stored in contiguous blocks of memory. So now in case of a linked list, this is not the case. This is not the case. if let's suppose one element is stored over here, another can be stored over here. The next could have been here. Then the next could have been here. So now, if I want to connect one node with the other node, so how to do that? So for that case, the structure of linked list looks like this, that we have a data part and we have an address part. Okay, so this address part will help us to connect one node with the other node. Okay, one node with the other node. So let's look at its structure. So here I have this node, let's say the data is 5. Then I have this node, let's say the data is 3. Then I have this node, the data is, let's suppose, -2. Then I have this node, let's suppose the data is 1. So I can connect this address part of this node with the next node. Then the address part of this node with the next node. Likewise, over here, and this is empty because no node is after this. Now in a linked list, so basically I want a point from where I can start. So basically I need something to traverse the linked list, or at least have the linked list. So in that case we should have the pointer to this very first node. Okay, so that's pointed out by head. We can have a head pointer which can store the address of the very first node. Let's suppose its address is 100, then the address of this node is 250. Let's say it's lying at 300. Let's say it's at 500. So head will store the address of 100. And what do we mean by pointing this pointer out? It means that here the address is stored like 250. Then here, so basically it's like we have address 250 over here. Then we have 300 over here. Then we are storing 500 over here, and there it's nothing, empty. So this was pretty basic about linked list. Now let us see how can we declare a linked list. So in C++, we can use a structure or a class as well. So a structure can be defined as struct, then node, then so we have this data field as well as this address field. So I will, let's suppose I want to store integer type. So I'm declaring it as int, then int data. Then we have, so we will also have a pointer, that is this next pointer, right? So that's how I can declare structure of the linked list like this. And in Java, how can I do that? So I can have a class. Let's say the class name is node, then int val node next. Okay, so that's how we can do that. So now linked list is a linear data structure. Linked list is a linear data structure. That means we can only traverse the linked list in this fashion. We cannot go to any node from in between. Okay, is it clear that why a linked list is known as a linear data structure? By this we mean that next is a pointer of type struct node, because this pointer is going to point to a node, right, of type this. Therefore the type of this pointer is struct node. So that's how the structure of this the data, that's how the structure of the node look like. Okay, the first entry is of data and the second is of next pointer that points to the next node of the list. Okay, cool. Now let's talk about the advantages and disadvantages of using linked list. So the advantage of linked list is that it has a dynamic size, isn't it? Dynamic size. So if I want to insert a node, I can simply create it and attach to this node, right? Attach to the last node of the linked list like this, right? So it has a dynamic size. Then second point is that there is an ease of insertion and deletion. So if I talk about an arrays, if let's suppose I want to delete an element from here, then all of these elements I have to shift one step left, isn't it? I have to shift them one step left. So that's an extra overhead. So in linked list, we don't have to do any such thing. We just have to manipulate the pointers. We will come to that part. We will see that dry run in a while. Okay, so now let's talk about disadvantages. So first disadvantage is that there is no random access. I cannot access any node from in between. Okay, any node from in between. The second disadvantage is that we need extra memory for pointers. We need extra memory for pointers. So whenever you already know the size of your data, you already know ki, okay, I am going to store 10 elements and that's all I need. Always go for arrays. But if you are not sure that how many elements you are going to store, how much data you have, so go for linked list. The third point is that linked lists are not cache friendly. Okay, linked lists are not cache friendly. I would suggest that give it a read. And this is basically quite a big disadvantage of using linked list, due to which we prefer arrays. Okay, due to which we prefer arrays. Okay, now let's talk about that how can we insert, print, delete a node in the linked list. So let's come to a little bit of code part. So as I told you that this is how in C++ we can make a structure of the linked list. Right, let's make functions. Let's say, so void insert, that I would want to insert the node in the linked list. So I'm making this function. Then also let's make another function, void print. So how to insert a node in a linked list? So for that, first of all, we should have a global head pointer. Okay, we should have a head pointer. So let me create that. So we just need to write this for that. Now what do we have to do? So for inserting a node, first we have to create a node of type this. So how to do that? We will write node star temp is equal to new node, and then we have to set this data part. So temp data is equal to x. Okay, this x, whatever the user has supplied. Then also we have to set this next pointer. So temp ka next is equal to what? Let's set it for now as null. Okay, let's set it for now as null. Now what do? We have to check if if let's suppose head is pointing to a null, so head is null. Okay, it's pointing to nothing. So if head is null, let it be like that. If head is not null, this is the case when there already exists a node. Head is pointing to this node. So now what we'll do? If head is not null, we will set temp ka next is equal to head, right? So we have created a new node. This is our temp node. Let's say the data is 5 over here. So what we are doing, we are setting it next to the head node because head is pointing to this right now. Okay, and we also have to set head to the new head. So head is equal to temp. So basically now head will start pointing over this node. So this is how it will look like now. 5, then 4 is there, and head is pointing to this node. So this is the case when head is not null. But if head is null, so in that case, we will set head is equal to temp directly, right? So now there's this thing that since this is getting repeated in both the cases, so what we can do, we can simply remove this from here, and this is how our final code looks. Okay. So this is how we can insert a node in a linked list. Now, if suppose I want to insert one more node, I can create it. Okay, I can create it. Let this be temp. So the data is 1. Now I will set it next to head, current head, and then I will set head to this newly created node. So this is how it will look like. That we have this 1, then we have 5, then we have 4, and head is pointing to here now. So I am inserting at head. So this function is for insertion at head. Okay, this function is for insertion at head. So if you have got the logic of this, that how you are manipulating the pointers, you can very well insert any node let's say at end or in between as well. So if you, let's say, want to insert a node at end, you can go till end. And so basically this is, let's suppose, your linked list, and you want to insert a node, at end. So you can set a temp pointer over here and iterate the linked list till the next of a node is not null. So here, as you can see, the next of a node is null. So we will stop over here. Now we will make this point to the new node. Does that make sense? That how we can insert a node at end? Likewise, you can insert a node at, so how can you insert a node at somewhere, let's say at position 3rd? So this is a linked list, and you want to insert a node at, let's suppose, this position. So this is a new node that you want to insert over here. What you will do, you will start traversing from here. You will go, so k is equal to 3, that means you want to insert a node at 3rd position. You will go till 2nd position and you will manipulate the pointers. Okay, so you are over here, then you move to the next element, and now you are at k minus 2 position. So you will simply stop. What you will do, you will make this point over this. So this will point to this now, and this will point to this now. So this link will break. Does that make sense? That how we can insert a node at any position in between? So now let's talk about that how to implement this print function. So what we'll do, we will create a temporary node. So as to iterate the entire linked list. We will set this to head. Okay. Now we will simply iterate the linked list like this. So while this temp is not equal to null, we can simply see out the data. We can simply print the data of this temp node. Okay, print the data of this temp node and make the temp point to the next of temp. Okay, next of temp. And this will go on and print the entire linked list. So temp will simply start from the beginning, and so temp is here first, let's suppose. So it will print its data, then it will move forward, it will print its data, then it will move forward, it will print its data, then it will move forward. And now you can see that we will simply come out of this while loop, because now the temp is null. Okay, language should not be a constraint. You should get the logic. Okay, you should get the logic that how we are doing it. That's why I'm also taking examples that how pointers will be moved. So don't really go with the language. You can check that how these things are implemented in Java. But here, please try to understand the logic. Okay. Okay, now what do we do? So here is our main function. So I can simply call insert x, insert, let's say 5, then I call insert, let's say 4, then insert -1, then print. So this all will do the trick, right? Now all these functions can be called and our linked list will look like this. So since we are inserting at the head, so this will be 5, then this will be 4, then here we will have -1, and likewise. Okay, so guys, now let's do the final, this delete function. So let me write a pseudo code of it. Okay, I am not writing the C code for that because that's creating confusion. Let me write simple pseudo code of it. So we have this delete function. Okay, and it's taking the head. Okay, so head is already declared as a global variable, so we need not do that, right? We need not do that. So what we can do for deleting an element, we can create a node of type, whatever class or structure you are declaring. So we can set this node and make it point to head. Okay. So basically, you can see it in this diagram that how we are going to delete a head. So we will mark. So this is head. Temp is also pointing over here. So basically, we can do head is equal to head connects. So head will come over here, and then we can free this temp. So basically we will do head is equal to head ka next and free temp. Does that make sense? Okay, so now let's quickly move on to the questions. Let's do the questions now. Okay, I would like to discuss some conditions where, even if people very well know linked list, but sometimes they fail at implementing it. Okay, so the manipulation of the pointers and, while handling the linked list, it becomes tricky. So therefore, a lot of coders stumbles on that. So let us see what we can do about it. So some conditions are there that we can definitely check after writing our code, that the head, so we should check if head is null or not. Okay, as in we should check if that have we handled the case when head is null. Okay, so don't worry, as we will proceed through the questions, you will get clear of these things as well. Okay, then you should definitely check your code for a single node. What if only a single node is present in the linked list? Then you should definitely check for 2-3 nodes. Okay, so let's say only 2-3 nodes are present in your linked list. You should check if your code is working fine in that case or not. And always try to think aloud. Like, that's the suggestion for all the questions that you attempt. Think aloud, write on pen and paper, and think about all the edge cases that can be handled or that needs to be handled. So that will help you a lot. Okay, now let's discuss some questions. So here we are discussing some questions. Now we discussed about printing a linked list from the very start till the very end in iterative manner, right? In iterative manner. This is an iterative manner, isn't it? Can we do it using recursion? So basically, let's say, so this is our print function. This is our head pointer. Now what we can do, as you can see over here, this is a linked list and I want to print it using recursion. So basically I can simply print the data of this node, and now with all the rest of the nodes, I just have to do the same thing with them. So why not using the same function for them? So what I can do is I can simply print the data of this head node. So then what I can do, I can simply call this function again with the next node as the head node. So print func. Now I am basically calling the head dot next. So this is this dot representation, then this arrow representation. It's how you reference, it's how you refer to these variables. So in Java, you use this dot. So basically for in classes while you implement it, you basically use this dot, and like in structures I told you, you use this arrow function. Okay. So will this do the trick? Is it sufficient? Is it sufficient, or are we missing something out? So if your head is equal to null, then you simply have to return, right? You cannot do anything about that. So simply return from there. This is the base condition. So let me actually first state the question. The next question is that you have to print the linked list in reverse order. In reverse order. So this is your linked list. This is your head pointer. Now you have to print it like this: 2, 1, 6, 4. How can you do it? Do you have to go at the end or something? Is it like that? Or like, can you do something about it in a better way? So you can have a stack. You can have a stack. Okay. So basically you can put this node into this stack, or you can also simply put the data of this node onto the stack. So you can have a stack like this, stack in S. Then you can traverse the this linked list using a temporary pointer, let's say T. So you are here, you put this data onto this stack. Then you move ahead, put this data on top of stack, put this data on top of stack, put this data on top of stack, and now the linked list is empty. So you can simply pop everything off, right? So you'll get 2, 1, 6, 4. Simple, right? What's the time complexity of this? It's just order of n, and the space complexity is also order of n, right? It's also order of n. So you can also do this using recursion, right? So as you see over here, most people have pointed out as well that we can simply reverse their order, and that will do the trick. That now I don't have to print this node immediately. I have to go till the last and then start printing. Okay, and then start printing. So what I can do? So basically, let me simply copy this. So what I can do, I can simply bring this over here. What's the time complexity of this approach? Again, it's order of n, and the space complexity is order of n as well, because here also we will be using the call stack. Recursion uses stack. So that's ideally what we are doing here as well. So both are same basically, right? The next question is to print kth node. So what you need to do? Again, so as I told you before, that you just need to go till the, so just go till kth node and print it. That's it, right? And print it. So it's pretty simple. Let's move forward. Okay, let's move forward. Now let's say I ask you to print the kth node, from end. So what we can do, we can actually see that what's this kth node from start. So we have this node. Let's say I want to delete this third node. Okay, I want to delete this third node from end. So what's the value of this? What's this node from very start? It's nothing but n minus k. This will give us these rest of the nodes, right? This will give us these rest of the nodes, and plus 1 will give us this node. So that is, from start it's nothing but fourth node. But to delete it, you will have to reach till this node, so that you can connect this pointer over here and remove this. Does that make sense? So you can, if you simply have to print it, you can simply go till this position. But if you, let's say, have to delete it, so you have to go till k minus 1th position and connect this. Okay, so let's find the middle of the linked list now. Middle of the linked list. These are the basic questions, and if you get hold of them, you'll get pretty comfortable with linked list. So try attempting them on your own, okay? Okay, how to find the middle element of the linked list? Okay, first, the basic approach we can use is that we can find the number of nodes in the linked list and simply do the count by 2. So we can traverse till count by 2 and return the node. Does that make sense? That's how we can do it. And the second is, let's see. So we have this head pointer, then we have this mid node, and we have this end. Okay. Let's say I have 2 pointers. So this is a slow pointer and this is a fast pointer. This is moving with the speed of 2 twice, so 2 into x, and this is moving with the speed of just x. So if with this pointer, if with this fast pointer starting from the very head, I reach till end, then this pointer will reach where? Remember that it's twice the speed of this pointer. So if I am reaching with this pointer till the very end, this pointer will reach over this place and we will find the mid. Does that make sense, that why the slow and fast pointer work? So let's quickly write the code for it. So mid of linked list. So we have this head. We will set slow pointer to head. We will set fast pointer to head. Then I'll come to these conditions in afterwards. Let's write this, that the fast pointer, you know that it will go 2 steps forward. So next ka next, and slow pointer will go only one step forward. So slow ka next. Then after coming out of this while loop, we can simply return slow ka data, let's say. So in this condition, this fast pointer is reaching till end. So we will be moving till fast is not equal to null. But this is incomplete. This is incomplete because here we are jumping 2 steps forward. So we have to make sure this exists. This node exists. So we have to check if past ka next is also not null. Okay. So what's the time complexity of this? So time complexity is just order of n and space complexity is just order of 1. Now let's talk about another question, which is to reverse the linked list. So how to reverse the linked list? So we can use stack. So like I'm not going into depth of it. Let's say the nodes are 1, 2, 3, 4. Now you can basically make a stack like this, stack of node pointers, okay, stack of node pointers. Now you have to, return what? You have to return this 4, then 3, then 2, then 1. You actually have to reverse the entire linked list, okay? So you have to take node pointers so you can push them. So you keep pushing them. This is 1, then 2, then 3, then 4. Now you can simply connect them. Now you can simply remove them one by one and simply connect them. Okay, so this is one way. The time complexity of this approach is order of n and space is order of n as well. Now how can we do it using recursion? We can do it using recursion, right? In which it will look like this. So we will have a function reverse, then head, then we will call, so we have to reverse it, right? So we will call itself with the next node. Now here we will perform some operations and here we have to write the base case. Let's see what to do about that. What are the operations first of all? So we have this operation to perform. Now what do we need? So let's see it over here. This is 1, 2, 3, 4. So I am here, this is my head, and if I'm back to here after recursing, that means this is done, they all are reversed, and I am back to this after recursion. Now what do I need to do? I have to set 2 next to 1, isn't it? So in place of 2, can I write head next, and in place of 1, can I simply write head? Will this be the case after returning from recursion? So I can simply write it over here that head ka, so you can write head ka next is equal to head. And then also what you need to do? You have to make this null. You can make this null. So head ka next is equal to null. But this isn't over, right? So we have something like this now. So, but we also need the head of this. Now this is the head basically. So this will actually return us that. So what we can write over here, let's call it last is equal to. So this function will return us that. I will come to that. I will show you the dry run of this. So we will simply return last at the end. But first let us talk about the base case. So do you guys agree that first we have to check the condition for null? So if head is equal to null, and also if there is one node, so we don't have to do anything. So if head ka next is null, in that case we can simply return head, isn't it? Return head. So this is it. That's all the code. Now let us look through the dry run. So recursion uses stack. So here I have that. and I'm using two variables, that is head and last. So I'll maintain them. Now first, so this is my linked list. So I am here right now. So head is at 1, and so last is what? Whatever we will get from here. So Abhi, right now I don't have anything. Okay, right now I don't have anything. So I have called this function. Now basically this is my head. So next, head is equal to 2, and last is still nothing, because again we are calling this reverse function. Okay, so since we are calling it, now head becomes this. So next, head is equal to 3 and last is still nothing. Then moving ahead, head is equal to 4 and last is nothing. But here, as you can see, we will actually not go over here, since there is only, you can see that head is not null, but head ka next is null. That means we don't have to go over here, we can simply return the head. So now this will return, and what's the head at this? It's 4. So 4 will get returned. Okay, 4 will get returned. Now basically we are returned from this. Now we are back at 3 as the head. So answer to 3 has been returned, right? So once we have returned from here, now we will do this. So head ka next. Head is at 3. So we will set this basically. Head ka next is this. So we will set this over here. And we will make head ka next as null. Head ka next as null. Now we will get back from this, and 3 will, so again last from here is, it's 4 only. Now again we will do head ka next, that is 3 ka next point to head. Okay, and head ka next is null. So now we are done with both of them. Basically we are done with both of them. So 4 will basically return, so this will basically return 4 over here, and this is also gone. Now we are back at 1, and we will make head ka next point to it, point to head, and we will mark head ka next as null. So what do we have? This is also done. So last has had what? Last had 4, this node as the new head. Does that make sense, guys? Let me again do it quickly. Okay, let me go through it quickly. So this is my linked list. My head is here. Okay, head is here. So I am at this if condition, and my head is not null. Also, the head ka next is also not null. So I will not go into this if block. I am here. So I am calling this reverse head again. This should be head ka next. And now basically I am calling reverse and passing 2 in that. Okay, so I have to store this on stack. So head is equal to 1 and last is equal to whatever this will give me as the answer. Okay, now as so now basically I am here. Now head is not null, and also head ka next is not null. So we will go to this block. Now here head is equal to 2. Last is I don't know, right? Last I don't know. So basically we are calling reverse head ka next, that is 3. We are calling this, and we are on this now. So head is equal to 3. Last is equal to, we don't know, because now whatever we'll get from reverse of head ka next, that is 4, will be coming over here. So we are calling head ka next, that is 4. So head ka next is 4 now. We are over here. Now as you see that last is not null, but head ka next is null. It's null. So we will simply return this head. What is head? Head is 4. Return 4. Where to return it? Where are we returning it? We are returning to this last variable. So here will come the 4. Okay, here will come 4. This is done. We are done with that. So basically this we are done. Now we are back from recursion at this place. Okay. So since we are back, now it has this value of last. It will return this value over here. Okay. Now this is also done. But before that, also what it will do, it will set this. That is head ka next will point over here, and head ka next will become null. Now we are done with this and back over here. Now we have got the answer for last. Okay, over here. First of all, what we'll do, we will set head ka next over here, right over here, and we will make head ka next as null. So this will return 4 over here, and this is also done. This is also done. Now we are back from recursion over here. We will set head ka next, that is 2 ka next to 1, and mark head ka next as null. So we are back from here as well. So this will return 4 to us. So in last variable, what we'll have? Finally in last variable, what we'll have? So we will have the address of this node, the head node now. Okay, we will have the address of this head node now. Okay, the time complexity of this approach is order of n, and the space complexity is order of n. Can we do it in order of n time and space as order of 1? Using pointers, okay? Using pointers approach, iterative approach. So we have these nodes. Let's see the intuition first. Let's suppose I am at this node. Now what I can do? I can break this link and make this point over here. But now I will lose the connection from here. So I need 2 pointers at least. So that is 2 here and here. But I'll also need a third pointer, that is over here, because this is a one-way linked list, right? How will I set this to this node? There is no way. So I need 3 pointers over here. So let this be current, next, and previous. So let's see a dry run of that. Let's see how we can do this. So initially, previous and next can be null. Both previous and next are null. Initially, they are empty, and current can be set to this node. Then we can set. So if current is not empty, if current ka next is not empty, so we can set this next node over this node, so that we do not lose this contact. Now, since we have set this up, we can set this link to here. Now what we need to do? Now this is actually previous will now move here. Current will move to next. Okay? Current will move to next. Basically got this link. Now current ka next is not null. Therefore, next will now come over here. And we will set current ka next as point to. This link was set up. This link was not set up yet. Okay, this link was set up, and now we will set current ka next to over here. Okay, now we will set current ka next to over here. Then again, previous will come over here, and current will come over here. Now again, current ka next is not null. So we will set next pointer over here, and current ka next as over previous. Okay. Now again, what do we need to do? set previous over here, current over here. Now current ka next is not null. So we will set next over here so that we don't lose the next node. We don't lose the next node. So we are setting this. Now make current ka next point over here. Now previous will come over here. Next will current will come over here. Now current ka next is null, right? It's null. We will be checking that current is not null. Okay. So since current is not null, so we will set the next over here, and mark current ka next as over here. And then just like that, previous will come over here, current will come over here. And now current is null. So we don't have anything to, we don't have any node now. So this previous node is our head now. This is our head. Is the intuition clear that why we are doing this? Let's quickly write the pseudocode now. So you will set current to head, and previous next will be null. Then while current is not equal to null, what we did, next will go to current ka next, will go to previous will become current, and current will become next. Finally, we can simply return previous as the head pointer. So the time complexity of this approach is nothing but order of n, and spaces order of 1, right? So this is reversing a linked list is a very important problem in the interview. With stacks, it's easy, right? With stacks is easy, but with these pointers approach, and here we have a recursive approach, it's little tricky to understand. Okay, this was it, guys, from my side for today. I hope you guys attempt the questions provided in today's contest. So thank you very much.
So we will start with the very first bucket. So what I have decided that from each bucket, I will be doing one question. Okay. Let us do the very first question from each of the buckets. Okay. Let us start with the palindrome list. So the question says that we are given a singly linked list and we have to determine if it is a palindrome or not. If it is a palindrome, return 1, or basically if you do Boolean, it is true for 1. And if it is not a palindrome, we return a 0. So I mean, like in Boolean, false represents 0 and true represents 1. So basically we have to return true or false if we talk in parallel sense of a Boolean variable rather than an integer. Okay. And the solution that is expected is linear in time and constant in space. Okay. Let us assume that, hey, this time we are given a linked list. Okay. So suppose you were given an array 1, 2, 3, 4, 3, 2, 1. This is a palindrome, right? How can we find if it is a palindrome? We can start a pointer from the left side and similarly a pointer from the right side going towards left and a pointer from left side going towards right. At each index, we check. So for example, at the very first stage, left will be this, and right will be this. Is the pointer at left equals to the pointer at right? Yes, it is equal. So now that means it satisfies the property. We increment left and we decrement r. Is the new left and right equal? Yes, they also are equal. So we again increment L and we again decrement R. They are also equal. Then we increment L and we decrement R. This time L will be equal to R. So I mean, like L and R both will be together. Okay. So at this stage we can stop because this is a central point. Okay. So if it had been an array, we could have done something like this. Int L equals to 0 and R equals to n minus 1 while L less than R. If AL not equal to AR, return false. Else we do plus plus L minus minus R, and when we are out of the loop, we can just return true. That means that the array was sorted. But this thing doesn't work well for a linked list. Why doesn't this work well for a linked list? Because in a linked list, we don't have random access. We can't directly access this number and this number. Similarly, a singly linked list doesn't allow you to go backward side. It only allows you to go the next side. Okay. So this is why we can't use exact same approach for the linked list. Okay. But now let us see this. Let us say this was a linked list. Okay. Also reverse this linked list. What will happen if we reverse this linked list as well? Then the reverse of this linked list will also be 1, 2, 3, 4, 3, 2, 1, right? So we can see that for a palindrome, the linked list and the reverse of the linked list is equal. Okay. So I mean, like, if we are somehow able to reverse a linked list, we can find if a linked list is palindrome or not. Okay. Now the question comes, how will we reverse a linked list? Okay. Let us see how we can reverse a linked list. Okay. So linked list is something like this. 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, which is pointing to 3, which is pointing to 2, and finally this is pointing to 1. Okay. Now suppose at every iteration we are maintaining 3 pointers. This is the previous pointer. Wait a moment. This is the previous pointer. This is the now pointer, and this is the next pointer. Now, what we see that in the reverse of the linked list, now next will be what was previous element, and next. So basically, now next will be the previous element. Okay. Okay. Now let us do exact same thing. Let us try to use this approach to reverse the linked list. Okay. So now, if we somehow are able to reverse the linked list, and how to reverse the linked list we already know, then we will be able to, what we say, then we will be able to find if a linked list is palindrome or not. Okay. Now, from what index should we reverse? Actually, we should reverse only this part of the linked list, right? Because if we reverse this part of the linked list, this will change to 1, 2, 3, and whatever that comes after this doesn't matter to us. We will keep on comparing each element. So 1 is equal to 1, okay, 2 is equal to 2, and 3 is equal to 3, and we are done. Okay. So we will reverse the part of the linked list that comes after the middle element. Okay. Let us do that. So the first question comes out is, first we have to find the middle element. Okay. Then the second thing is reverse the list after the middle element. Okay. And then we have to compare corresponding elements in the first half and reverse of second half. Okay. Now let us do this step one by one. So how will we find the middle element? So I mean, like, if you have not heard of this approach, this is known as hare and tortoise approach. Okay. What a hare and tortoise approach is that we maintain 2 pointers on the linked list. Initially, the first pointer is here as well as the second pointer is here. One pointer moves faster, actually at the double speed of the second pointer. Okay. So at the next step, the first pointer will go here, the second pointer will be here. Then in the third step, first pointer will be here, second pointer will be here. Then first pointer will be here and second pointer will be here. So as soon as one of the pointers reaches the end of the linked list, that means the other pointer will be at the halved position of the linked list. Okay. So I mean, like, you can read about this after this session if you are hearing this approach for the very first time. But let us do that. So we say list node value at tortoise. I mean, you should actually not take these variable names. You should say slow, which is initially A. Then you should also say fast, which is equal to A. Okay. So while fast not equals to null and fast next not equal to null. So we move the slow pointer by one step. Slow is equal to slow next. But we move fast pointer by two steps. Fast is equal to fast next next. Okay. Now, when the fast will be null, so when the fast will be null, that will be a situation like this. Let us say this is a linked list. So in this case, initially slow will be here and fast will be here. Then fast will go here and slow will go here. Then fast will go here and slow will be here. So when the fast is null, at that time, slow is pointing to the first element of the second half of the linked list, right? Okay. But let us take a case when the linked list is of odd size, 1, 2, 3, 4, 5. In this case, initially slow is here, fast is here, then fast goes here, slow goes here, then fast goes here, and slow is here. At this point, slow is pointing to the exactly middle element, okay? And we have to reverse the second part. I'm like just after the middle element, okay? So we will say if fast not equal to null, slow is equal to slow next. Now we are sure that the element slow is pointing to the very first element of the what we say linked at the very first element of the second half of the linked list. Okay, awesome. But anyways, we will have to do wait a second. So if first not equal to null, second is equal to second next. Okay, that's it. And always we have to set this slow next equals to null. Now we reverse the two linked list. Sorry, now we reverse the linked list that starts at second. Okay, how will we do that? We say list not. So this is also a very good technique that you should use whenever you are solving a linked list problem. While solving a linked list problem, you maintain a dummy head. Okay, which is node that contains only 0. So initially, the previous will be dummy. The current will be the very first node, which is A, and next will be nothing. So we will say while now not equal to null, okay, next is equal to now next. Okay, then now next is what? Now next is the node that was the just previous node. Okay, so actually we can actually initially take previous as null. So that will also work for this. Okay, now next is equal to previous. And now what is the previous? Now previous is equal to now. Clear? Okay. So now we have done this. At the end, the previous node will represent the head of the new list because at the end, previous will point to the node 4, which is the new start of the list that comes at the second half. Okay, so now we know this. So we will say while your first pointer is at A and the second pointer is at previous, we will say while first pointer not equal to null and second pointer not equal to null, if first pointer key value is not equal to second pointer key value, return false, and we say pointer equals to first pointer next and second pointer equals to second pointer next. Finally, if we are out, that means we can return true. That means the whole list was a palindrome. Does this seem correct? Let us test it. Okay, so actually we did a time limit exceeded. So basically we entered in some kind of a loop, right? Let us see where we did wrong. Okay, so we should do this here. Otherwise, always something like this, right? Let us see if we can test it. So we are saying while if fast not equals to null, second is equal to second next, okay? And we are setting the slow next to null. Slow is the previous element here. So in this case, in the very first case, we saw that when fast was null, slow was pointed to the first element. So we also need to know actually the previous. So we also need to know the previous slow, which will be initially null. And we will say previous slow is equal to slow. Okay. So, okay, in this case, when the array size is even, initially slow will be here and fast will be here. Okay. Then slow goes here, fast goes here, slow goes here, fast goes here. In this case, previous slow ka next should be null. Okay. Else previous slow ka next should be equal to null and second is nothing but slow. Okay. Great. But in the case of odd, slow will point to the very first element. So second is equal to slow ka next. Okay, second is equal to slow ka next. And we set slow ka next equals to null. Okay, now does this look cool? This looks good. And so here we are breaking the list basically into two parts. And then let us see that if we can actually test it. First, let us test in custom input. Okay, we are not changing now to next, right? Previous is now, but now is also next. So we have to do this. Okay, and now this will work. Yep. So, but this case it should return 1, right? So in the case of 1 to 1, slow will be here and fast will be here. Then fast goes here and slow comes here. So in this case, what is the start of the next? This is 1. So we will say that we have to reverse the list that starts at second. So we have to reverse this thing, right? While now is not equal to null. Now is actually not A. We are reversing the first list. Now is second. Yep. Now this is working. Yes, and let us submit it. Are we missing an edge case? I think yes, we probably are missing the edge case where all the elements are null. One advice for any kind of linked list question, make sure that you never end up assessing a null element. That is actually a very big mistake that many people do. Okay. Always ensure that the pointer that you are assessing in a linked list is not null. So that is one of the biggest mistakes I've seen many people doing that in linked list questions. Okay. Cool. So we're done with the very first question. So here we learned two techniques. The one was the hare and tortoise approach. And the second thing was how to reverse a linked list. So basically this is a combination of two questions. Let us do a question in this pointer now. So let us say that we are doing swap list nodes in pairs, okay? Because K reverse linked list is just same as the normal linked list question, normal reverse the list question, okay? Let us say that we are solving this question that is swap list nodes in pair. Okay, so we are given a basically linked list and we have to swap 1 and 2. Then we have to swap 3 and 4. So basically 1 and 2 will become 2 and 1. Then we are done with this particular part. Now we are taking the care of the part 3 and 4. We again swap it, which becomes 4 and 3. Okay, and we are asked that, hey, we have to use only constant extra space. So basically we can't create a new linked list. But what is meant by a constant extra space question is normally that what we mean by a constant extra space in linked list is that you don't have to create a duplicate node. You have to use the nodes that were given in the initial question itself. Okay. Okay. Anyways, let us try to see how we can do this. So basically, linked list is nothing but a game of pointers. How you are able to mingle pointers is how you will win the game. So let us say that we have 1, 2, 3, and 4. Okay. So now suppose I have to reverse this linked list. I told that in the previous question as well that dummy head is a very common and helpful technique in solving any kind of linked list question. Okay. So for example, here what I will say, I will assume that there is a dummy node here, after which it is 1, after which it is 2, and 3, and 4. Okay. So now see, suppose I'm reversing the pair of 4 and 3. I at least need the pointer to 4 and also the pointer to 3. Okay, but I also need the pointer to 2. Why? Because when I have reversed these two, I have to make sure that 2 ka next points to 4. Okay, so we at least need 3 pointers. Okay, so let me first create a dummy node. Let me name this pointer. Let us say that when we were swapping 3 and 4, let me name the variable 2, the variable that stores the node 2 as the previous pair end. Okay, so let me say list node value at previous pair end. Initially, it will be dummy, right? Because this is the end of the first pair. This is our assumption. Okay, so this will be dummy. Okay, this will be equal to the current pair start. Okay, so this is current pair start. Okay, which is in the case of in the first case, this will be the node A itself. Okay, awesome. Okay, so while I will say that while the start of current pair is not null, start not equal to null. Okay, so I will say current pair second is equal to, okay, I let me also assume that current pair start ka next is also not equal to null. Is not equal to null. Okay, so current pair start ka next. So basically both the nodes of the current pair exist. Okay, if there is only one node, we don't need to do any swap, right? So I will say current pair second is equal to current pair start ka next. Okay, I also know the previous pair end. At the end of the current iteration, what will be the previous pair end? Previous pair end at the end of current iteration will be the starting node of the current pair. Because at this time, let us say this was the start and this was the end. Okay, so after this will change to 4 and 3. So basically this will be the previous pair end, so which is the current start node. Okay, okay, and we also have to make sure that current pair ka second, so basically previous pair end ka next is equal to current pair second, now has to point to 4. Okay, and current pair second ka next is current pair. So now we have made sure that 2 points to 4, 4 points to 3. Okay, and finally we have to make sure that 3 points to this. Okay, current point start, current pair start ka next should be equal to what is currently the current pair second ka next. Okay, finally change the current pair second next, and this is previous pair end. Okay, and finally I can just return dummy ka next. Okay, because dummy was just a node that we assumed. Okay, so now in this case dummy ka next will become, so the pointers will change like this, right? And 1 will now point to 3 and dummy ka next will point to 2. So dummy ka next will actually be 2, which is the start of the next list. Let us see if that is correct or not. We might have done some errors, but let us see, hopefully not. What did I do? Oh, I didn't comment here. What are we doing here? So we are saying that initially we actually made sure that dummy ka next should be equal to A. Okay, because dummy is going to point to 1, right? That I told earlier. I will like initially dummy should point to 1 and 1 should point to 2. So I didn't point the dummy to first one. Now let us test this. You lost 0. Okay. and I say first pointer previous pair end is dummy, okay, and current pair start is A, okay. While current pair start is not equal to null and current pair start next is not equal to null, okay, both are not equal to null. So then current pair second is current pair start next, okay. We change the previous pair end next to current pair second, okay. So now dummy node is starting to point to 2. Then we make sure we point 1 next equals to 3, okay. So now dummy node is pointing to 2 and 1 is pointing to 3, okay. Now we should point 2 to 1. So current pair second next, that is 2, is now going to point to 1, okay. And previous pair end will be equal to 1. That is fine. So this thing is fine. And what will be current pair start? Okay, so now we have not changed current pair start. If previous pointer end not equal to null, current pair start is equal to previous pointer next, else current pair start is equal to null. Similarly, if current pair start is not equal to null, then okay, so we don't have to do that. So we only need current pair start and we are done. So now 2834 is changed to 3428. 4874 is changed to 7448. Similarly, 4249 is changed to 4942, and we are doing well. Let us see if we have any issues. Seems fine. Great. So we got this as well. So so what thing we learned from this thing, the takeaway should be that, hey, for any linked list question, first try to find what are the pointers that you need to know to reorder the list in any way. Suppose it is swapping pair, what are the elements you need to know so that you can change their pointers to something else? That is the very first thing you need to know. And the second thing is, again, I tell you to know, is this dummy thing. This is very important in a lot of linked list questions. I will do one more question after this that will use this thing. And the third thing is, make sure that you are never assessing null. Okay, so here also I do a check of null. Make sure you are never assessing something that is null. Okay, cool. Let us do one more question. So the question is, we are given a singly linked list L0, L1, Ln minus 1 to Ln. Okay, and we have to reorder this to L0, Ln. Okay, so the very first node from the start and the very first node from the end, then the very second node from the start and the second node from the end, third node from the start, third node from the end, and so on. Okay, and we must do this in place without altering the nodes values. So what in place means is that you don't have to change their values. I mean, like, you can dangle some pointers, but that will work. Okay, you just don't have to change the node values or create a duplicate of those nodes. That is the only requirement. Okay, so one thing that I find from here is that, hey, if we somehow, let us say that this was our list. Okay, our list was 1, 2, 3, 4, 5, and 6. We have to change this to 1, 6, 2, 5, 3, and 4, right? Suppose I know the first half of the list. I also know the second half of the list, which is 4, 5, 6. Okay. Now I reverse the second part of the list. This is 6, 5, 4. Now what I do, I keep on merging this. First, this is 1. So I will put this 1. Then I put this 6. Then I put this 2. Then I put 5, and so on, right? Okay. So how can we do that is, first split the list in two halves, okay? Then reverse the second half, okay? And finally merge two lists. This is something that you do. This is something very similar to that you do in a question like merge sort, right? In merge sort, the merge step is something like this. Okay. Okay. Let us do these steps one by one. In the previous question, we had discussed an approach to split the list in two halves and reverse the second half, right? We had discussed that in the very first question for the day. Okay, so let us do that. So how did we do that? We do this question by using 2 pointers, the slow and the start. Okay, so initially the slow pointer is equal to A and the fast pointer is also equal to. Then we do while fast not equal to null and fast next not equal to null, slow is equal to slow next, and fast is equal to fast next. So now there were two cases. The first case was if fast not equal to null. When did that case happen? Let me redraw it again. That case happened when the linked list was of odd size 1, 2, 3, 4, 5. So in this case, slow will be here and fast will be here. Slow changes to this, fast changes to this, slow changes to this, fast changes to this. In this case, fast is not equal to null, right? Okay. In this case, we can reverse this whole linked list. So this will change to 1, 2 will remain as it is, and this will change to 5, 4, 3. Suppose we are able to do that, then we can do the merging, right? Or not? Yes, you can do that. So it will be equal, yes. Okay. Okay. If the size of the linked list is even, then it will be 1, 2, 3, and 4. Then slow will be here and fast will be here. Then slow goes this, fast goes this, slow goes this, and fast goes this. Then also we can reverse the linked list that starts at start. So that we could do even in the previous question. I missed this thing. So we can reverse the linked list that just starts at the slow pointer. Okay. So suppose we reverse this part of the linked list, then we are cool. Let us see how we will do that. So we have to make sure that the pointer of 2 is now the next of 2 is null, so that these two lists break off, right? Else anything can happen. So we will say list node value at previous slow is equal to null and previous slow will be equal to slow. So finally, we can say previous slow for next is null. So at this point, we have broken the list into 2 halves such that slow points to head of second half. Okay, great. Okay. So now let us reverse the linked list that starts at the slow pointer. Okay, so basically reverse this 3, 4, 5 to 5, 4, 3. So we will say list node value at previous is null, list node value at current is equal to slow, and list node value at next, this variable we will need. We will say that while current is not equal to null, that means there is still a node there. Okay. So while current is not equal to null, I will say next is equal to current ka next. Then I set current ka next is equal to previous. Finally, I change previous equals to current. And what is the next current? The next current is the node that was currently stored in the variable next. Okay, great. So now this has reversed the linked list at 345 to 543. At the end, the node 5 will be the previous node. So we can say that list node value at second head is equal to previous. Now we do have to just merge both the linked list, right? So we will say while A not equal to null, sorry, yes, for this also we will need a dummy node. Then we will need a pointer to the current index in the answer. So list node value at dummy pointer initially it will be equal to dummy. Okay, we also need a pointer, which will be initially a, and we also need the pointer to the second half, right? So this will be second head. So we say that while a pointer not equal to null and second pointer not equal to null, okay, so while both of these are not null, we first append the second thing to this. I mean, like, then we append, but we say we have to first append the node at a pointer, right? So we say dummy pointer ka next is equal to a pointer, okay? Then dummy pointer equals to dummy pointer ka next. Finally, dummy pointer ka next, okay, and a pointer is also equal to a pointer ka next. Then dummy pointer also moves to one step ahead. We change dummy pointer ka next is equal to b pointer, or the node that b pointer points to, okay? And then we say b pointer is equal to b pointer ka next. Okay, great. So now what will we be having is, suppose for a linked list of odd size, we will be having something like this: 1, 5, 2, 4. Okay, but at this time, the pointer to the second pointer will not be null, but the first pointer will be null. So we say if pointer is not equal to null, that meant that the total number of nodes were odd. So we will say dp, again we have to make sure, okay, dp next is equal to what we say, the second pointer. Okay, so dp next is the second pointer, and finally we have reached the end, so we don't need to do anything. We can so yeah, we are done. Now, but where is the answer? The answer is the dummy head ka next, right? Because dummy head ka next is storing the very first node in the answer. So we can just do return dummy pointer ka next. Sorry, dummy head ka next. Like this. Dummy ka next. Let us see if this works. What is this happening? This is returning dummy pointer ka next. What is the dummy pointer ka next? Initially, this is the first pointer, but the first pointer is null. Initially, the second pointer is also a. So the second pointer will still point to this. So second pointer will not be equal to null. So this should be correct, right? So let us see why this particular case is having issues. Okay. So in this case, we won't ever go here. So if we don't ever go here, that means that there was only one node, right? That will happen only if there was less than 2 nodes. So we can say if previous low is equal to null, we can just return the original linked list. Why? Because this thing will happen. I mean, like, previous low will be equal to null only if there are 0 nodes or 1 node. In that case, we don't need to do anything, and we can just return the original linked list itself. So now this should work. Yep. Are there any other cases that you are missing? No. Yes, and let us submit it. Great. So yes, in this thing we missed checking for null one time, and we again ended up with an issue. So that is why I was saying that never get to a situation where you are not checking for nulls. Okay. And also, again, you saw that what is the use of dummy pointer. Dummy pointer allows us to improve the code quality by not checking for nulls in the initial previous. Okay. So use this technique as well. Let us do one more question and then we will end. Let us do this list cycle question, because this also requires knowing a technique that many people might not know. So let us do this. Okay. So we are saying is told that we are given a linked list. We have to return the node where the cycle begins. Okay, the linked list might or might not have a cycle, But if there is a cycle, we have to return the first node from the start where the cycle actually started. So for example, if we start traversing this linked list like this, the node 3 is the very first node where the cycle began, right? So we have to return the node 3. Okay, great. So let us see how we will do that. So see, we once found a middle of the linked list, right? We were once able to find the middle of a linked list using the previous approach, right? If you see the hash approach has a space complexity of order of n, right? So we have to do something that has space complexity of order of 1, but time complexity of order of n. Let us do that. So we remember that, hey, we were able to find the middle of a linked list using the hare and tortoise approach. But if the linked list has a cycle, will we ever be able to find the middle? No, right? Because fast will never be equal to null. So if we start growing from 1, 2, 3, 4, then we will keep on coming back to 3, 4, 3, 4. So if we were suppose finding this thing, value at slow is A, fast is also A. We say while fast is not equal to null and fast next not equal to null. Fast is equal to fast connects and slow is equal to slow connects. Okay, but when there is a cycle in the linked list, this loop will never end. Okay, because it will again going on circle around. So let us say what will happen. Okay, suppose the loop is circling around and currently, let us say this is the case. So this is a linked list 1, 2, 3, 4. Okay. Okay. And suppose all these nodes are in a cycle. Suppose all these nodes are in a cycle. Okay. It might happen that currently fast is here and slow is here. Okay. That means in the next iteration, fast will go, what we say, at this place. And where will slow go? Slow will also come at this place. Okay. So, okay, that is the case 1. The case 2 is, let us say fast and slow are very much behind. Okay. Let us say initially the fast was here and slow was here. Okay. Then what is going to happen in the next iteration is, in the next iteration, fast is going to come here and slow is going to go here. Now this condition is again same as this condition, right? The condition that we had here. So we can say that if fast and slow pointers are in a cycle, that means they are definitely going to meet at some time. Okay. So we can say while fast not equal to null and fast connects not equal to null, okay, if fast is equal to null, this means that there is a cycle, right? This means there is a cycle. So we can break. So here we can say that if fast is not equal to null, or and fast connects not equal to null, or fast connects not equal to null. So let me say that I pool cycle is equal to false. If we enter in this loop, we say that cycle is equal to true. That means there is a cycle in this current thing. Okay. So if there is a cycle, now the question comes, how will we find the start of the cycle? But let us solve the case if there is no cycle. If there is a no cycle, we can just return null, right? Now let us see how we will find the start of the cycle. Okay. So let us say our cycle is like this. So there are nodes 1, 2, 3, 4, 5, 6, 7, and this 7 is pointing to, let us say 4. Okay. So 7 is pointing to 4. Something like this. So suppose 7 is pointing to 4. Okay, that means this is a cycle. Okay, great. So now how will we find that 4 is the start of the cycle? How will we be able to do that? Let us see. Suppose assume that this size, the size of the linked list before the start of cycle was A. Okay. And currently, both the slow and fast pointers will be traversing 4, 5, 6, 7, again 4, 5, 6, 7, and so on, right? Is that clear? Okay. So now we know that this is, so now somewhere inside this linked list will both these nodes meet. Suppose both the fast and slow meet at this particular place. Okay. And let us assume that from the node start, this distance was B. Okay. So A was the distance of start of cycle from head, and B was the distance of meeting from the current node. Distance of meeting uh, from the start of cycle. Okay. Okay. And let us say we also have a variable C, which is the start of cycle, which is the size of cycle. Okay. Okay. Now, can there be any formula between A, B, and C? Fast will not become null when there is a cycle that we have assumed. So basically, that is why at this particular position, if fast is equal to slow, we are saying that there is a cycle. Okay. So now let us try to see of one more thing. We say that, hey, this size was A. Okay. This size, suppose the nodes met at node 5. This size was B, and this size is C. Can there be a relationship between A, B, and C? Let us say in this way. Suppose the fast and slow pointer had traveled this node X times, this cycle X times when they were inside the cycle, because they will keep on circling around, right? Okay. Suppose they had traveled X times. So the total distance traveled by slow will be equal to this, which is A, plus the number of times they travels this cycle. What will be the number of times? Let us say they traveled this N times. And what is the size of this they traveled? The size of cycle is C. So plus N times C. And they met at this. Okay. So what is this distance? This is B. So this will be the distance covered by the slow node. Correct? Okay. And what will be the distance covered by fast node? The distance covered by fast node is nothing but 2 times the distance covered by slow node. But how many iterations would it have done? How many iterations would the fast pointer would have done? Suppose fast pointer did Y iterations. Okay. Slow pointer had done X iterations, and let us say fast pointer had done Y iterations. So the distance covered by the fast pointer is going to be A. So this is N, let us say this is M. Okay. So A plus M into C plus B, right? That means A plus M into C plus B is equal to 2 times A plus N into C plus B. Is that clear? Okay. From these two equations, we can find that we'll be able to find that what will be the equation that will come out to be? The equation will come out to be that, hey, what is the distance from A plus B? Okay. Okay. So if we try to expand this equation, this will become A plus M into C. So let us try to expand the right hand side first. This is equal to 2 into A plus 2 into N into C plus 2 into B. Okay. If we take B to the left side, so this will become A minus 2 into B, and also bring this A to minus 2 into A plus B, right? So, okay. So this is going to be equal to 2 into N into C minus M into C, right? Okay. So what we get from this is that this is nothing but equal to minus of, this is equal to minus A minus B, and the right hand side is equal to C into 2 into N minus M, right? Okay. But what we find from this, this means A plus B, a negative, is equal to uh, C times something. But what is C? We see that C is the size of cycle. So basically, we find that, hey, the distance from A to B. So basically, this distance is actually going to be a multiple of the size of cycle, right? So if we again start a pointer from this particular position, and we again, so basically till this time, this goes till here, the pointer that will be at this place will actually come to 4 again. Why? Because it will go from 5 to 6 to 7 to again 4. And by the time the another pointer, if we start from 1, will also reach to 4. And 4 is going to be the start of cycle. Okay? So what we can do is we can again put slow is equal to what we say A, and we say while slow is not equal to fast, this time we will move both the pointers by only one movement. Okay, so we will say slow is equal to slow connects and fast is equal to fast connects. Okay, now that means now where they have met, that is nothing but the start of the linked list, start of the cycle. So we can just return slow. So in this thing should work. What happened? Okay, so we will actually have to start with, okay, so this thing will be actually initially true, because at least we have to move fast and slow ones, because they will otherwise always be true. Right? Yes. And let us submit. Great. So we did one more question, and today our streak points are equal to 1685. Cool. So that's all for today. Make sure to complete your streak as well. Okay. Bye bye.
Let's talk about a very important topic called stacks and queues. Stacks and queues is one of the most important topic when it comes to computers programming. Recursion, for example, is based on stacks. Understanding stacks enables you to better understand how recursion works internally, and hence you can use it to optimize space of your program as well. It's extremely important for interviews. You can expect direct questions on stacks or queues. For example, if you want to find the maximum area under a histogram, you can do it using stack. The parentheses problem as well can be solved using stack. The sliding window problem can be solved using a queue. So these are important from an interview perspective. But having said that, it's also important for day-to-day activities as well. Why? You might have heard about Kafka or Redis queues. These are nothing but the data structure queue, right? At a massive distributed scale. So these are not just important in terms of an interview, these are also important in day-to-day activities as well. Hence, do not skip these topics.
Okay, so today we are going to cover stacks. So let me give you first a little introduction about stack. So first of all, the stack is very much important. It's the most favorite topic of the interviewers. Be well versed with this topic. Like first go through the basics, understand it because they're very straightforward, and then attempt as many questions as you can. There are some, standard problems that you should definitely attempt. That was the gist about stacks. Now let's get started. Cool. So stack is very much similar to the stack of objects you see around yourself. So be it stack of plates, stack of books, so stack of plates, stack of books, then stack of, let's say, bowls. So you see it and use it every day, right? So let me draw the stack of plates. So this is how a stack of plates look like. Now from this stack of plate, you can insert a plate only from this end, that is top, right? You can only insert a plate on top and you can only remove a plate from top. You cannot insert or remove a plate from in between because that will disturb all the plates, right? So you cannot do that. You can only remove and insert a plate only from top. So that's essentially the idea behind stack, that we can only insert an item from top and we can only remove an item from top. Okay, so conceptually or logically, you can think of a stack like this, where one end is open and three ends are closed. So from only this end, we are going to perform operations, that is to remove an item and to insert an item. As I was saying, that we can only insert an element from one end and remove an element from that end only, and therefore stack is known as LIFO data structure. That is the last, as you can see the stack of plates over here. So this plate which was inserted at the very end will be the first one to come out. That is last in, first out. Okay, cool. So first what we are going to do, we are going to understand stack as an abstract data structure, that is ADT, abstract data structure. What do we mean by abstract data structure? In which the implementation details are hidden, but the operations are given to us. Okay, so let me write it over here, that implementation hidden. Okay, it's not there, it's not given, but only the operations are there. Only the operations are there with which, using which we can use the stack. Okay, so for example, you can see the fan on top of you, right? So you don't know how it's working internally. All you care about its operation, as in you put down the switch and it turns on, and you put off the switch and it turns off. That's what you care about. So that's an abstract. Cool. So we are given, let us understand the basic operations that are available with stack. Okay, so there are four basic operations. The first one, I am sure you guys, if you know about stack, you must know about all these operations. So that is push function, and then second is pop, the third is top, and the fourth is empty. Okay, so the push operation actually helps us to push an element on the top of stack. So this pushes an element on top of stack. Then here we have pop. So pop removes an element from top of stack. Then we have top, so it returns the element present on top of stack. So whatever element is present on top of stack, it just simply returns it. Okay, so don't worry, we are going to see an example over here. Is empty is the function that tells us if the stack is empty. So if the stack is empty, it returns true, else it returns false. Okay, so these are the four operations, that is push, pop, top, and is empty. Push pushes an element on top of stack. Pop removes an element from top of stack. Top tells what is on top of stack, and is empty returns true if stack is empty, else it returns false. Remember that pop simply removes an element and top does not remove an element. It simply tells what is present on top of stack. Is it clear now? Okay, so basically while performing a question, you will have to use in C++, let's say you can use STL, right? In STL you have stack. So in C++, you declare a stack like this. You can use a stack like this, and on this object basically you can call all these functions. So push x, then s.pop, and so on. Likewise in Java, you have collections using which you can use stack. So while attempting a question, you don't have to implement a stack of your own until and unless told. Okay, so But in a while, we are also going to see how to implement a stack. We are going to actually implement these operations. Okay, cool. Okay, so let's actually see a dry run of these functions. So here, this is a stack, and these are the operations that I would want to perform: push 2, push 1, push -1, push 5, then pop. Pop is empty, top. So let's perform these functions, okay? So it's push 2. So what we'll do, from where we'll put it? We'll put it from here. So basically 2 will come over here. Then it's push 1. So 1 will come over here. Then -1. -1 will come over here. Then there is 5. 5 will come over here. Then we are popping. So 5 will be gone, right? 5 will be gone. So we have removed 5. Now again pop is there. So -1 will be gone. So we have removed -1. Okay. Then we are checking, is the stack empty? What will it return? What will this return? It will return false because the stack is not empty, right? The stack is not empty. Okay, so now there is top. So what will be the top function return? It will return whatever is present on top of stack. So basically top is pointing over here. So whatever is on top of stack, it will return that. So it will return 1, right? It will return 1. So that was a simple dry run of how can we use these operations. Okay, how these operations work. Now let us come to the applications of stack, which are very important. Applications of stack. So some of the applications are undo, redo. Then we have arithmetic expression, evaluation, right? Then we have recursion. So these are some of the, then we have string reversal and so on. So these are some of the applications of stack which are very important and you must know. So try to figure out that how a stack can be used in these operations. You know, that's an activity for you, that do try to search that how we can perform an undo, redo. So this is actually present in your browser, right? So whenever you go to any page, from any page and want to come back, so basically you store, for example, let me give you an example. So you are at link, let's say 1, then you go to link 2, then you go to link 3 and you want to come back to link 2. So what you can do, you can actually maintain a stack of them. So like first you are on link 1, you can put it on a stack, link 1. Then you are going to link 2. So put it on top of stack. Then you are going to link 3. Then put it on top of stack. Now you want to come back to link 2. So what you can do, you can simply remove this. And now you are back to link 2. Does that make sense? So likewise, you can also have a redo stack. Okay, so that's an activity for you, that how you can perform a redo operation. Okay, so likewise try to figure out. And we have arithmetic expression evaluation. So I think you all must be very much familiar with this. That is, you know, converting to infix to prefix or postfix, then evaluating the postfix notation. So that's where you can use stacks. Okay, and then you have recursion. Stack is a core of recursion. So you make function calls, and when you come back, so that basically those function calls get stored on top of stack. Okay, likewise string reversal. Okay, so there is another application that you may be using in your daily life. You must have seen this InShots app, right? So what happens in this, you are on this screen, okay, and so here I am actually at my feed. I am at my feed, okay, and I am watching this news. So I can only see another news if I remove it, if I remove this. So can you see that how this is an implementation of stack, right guys? Now let's talk about the implementation of stack. So Could you guys tell me how can we implement a stack? So using arrays. Second is using linked list. Okay. So how can we implement a stack using arrays? So basically, let's see. So we can have an array. So size of the array is, so array is A, and size of the array is 7. Okay, so what we can do, so let's say I want to push 2, push 3, push -1, pop, push 7, pop. Let's see how can we implement these operations using stack. Okay, so what we can do, basically we can actually enforce that one end of the stack will be there to perform all the operation. So you can imagine it like we are pushing the elements from here and removing the elements from here. So let's say I want to push 2, so 2 comes over here. Now you can also maintain a top variable which is right now pointing over here. That means what is on top of stack? 2 is on top of stack. Then we have push 3. So what we can do? We can simply increment this top variable and push 3 in here. Then push -1. So we can simply increment this top variable and push -1. Now how to pop it? How can we pop it? Top minus minus. So basically we are now at index 1 and we have, so basically -1 is gone. Okay. Then we are at, so this was done, then we are at 7. So again we can increment the value of top and 7 comes over here. Now again pop's coming. So we can come over here and this is gone. So basically that's how we can operate a stack using arrays. Okay. And now can someone tell me the problem of stacks? So problems of stack are, which are very important if let's say an interviewer asks you to implement a stack using arrays or linked list. So if I talk about arrays, then we have problems, overflow and underflow. Let's say I want to push 1, 4, 0, 5, 6. These are the items that I would want to push. So 1 comes over here, then 4 comes over here, then 0 comes, then 5 comes, then 6 comes, and now I would also want to insert, let's say, -1. So as you can see, as I move my pointer forward, there is no space because array has a fixed space, right? So I cannot insert any more element, and that leads to the condition of overflow. Okay, and it's very important. So if interviewer has asked you, he's basically maybe judging you that will you cover these cases or not. Okay, so this is the thing. So how can you handle it? So basically here you have mentioned a size, right? You can keep a check that if size, so if top is equal to the size -1, so in that case that's an overflow. You cannot insert any more elements. So that's a drawback of arrays. And to overcome that, basically you can use something known as dynamic arrays. Okay, you can use something known as dynamic arrays. Okay, now let's say I want to pop, I'm calling pop 7 times. Okay, so basically this is gone, third time, fourth time, fifth time, sixth time, and 7th time. And now I am again calling. So now what will happen? Will I be able to pop any more element? No, I will not be able to pop any more element because the stack is empty. So if I attempt to do so, that will lead to underflow condition. So how can you make it all right? Basically, you can put a check that if top, so if top is equal to, let's say, -1, then print underflow. Okay? And simply return. So that's how you can manage underflow and overflow condition. Does that make sense, guys? Underflow is when you are trying to pop an element when there doesn't exist. When you are popping an element when there is no element. So how will you be able to pop? Will you be able to pop? No, right? So that's the case of underflow. So you can manage the case of underflow by checking that if top is equal to -1, that means you have no element, so you simply print underflow and return. Cool. So let's talk about linked list. So in linked list, what you can do is, so you have nodes in linked list where this is the data part and this is the address part. So basically, the nodes of the linked list can be present anywhere in the memory, right? Like array, you don't have everything in a contiguous manner. Everything is scattered. Every node is scattered in linked list. Basically, if you have this as a memory, so if let's say one node is present over here, another node can be present over here. Okay, third node can be present over here. So basically, this address field actually links node. So basically, this will be linked to, let's say, this, then this is getting linked to this, and so on. That's how we store data in linked list. So basically, let's say you have 2 and 1 right now. Then you want to insert, you want to push, let's say 7. So how you can do? Right now, top is here. So at what position, if you, so you are actually, remember, you are actually implementing stack using linked list. Where would you want to insert this node? This is your linked list. This is what you are building. This is the temp node, current node, that you new node that you want to insert into your linked list. So where will you insert it? That we can actually put it on top of head. So now we can actually make this its next pointer point over here. So this is how our stack would look like. Now top will be over here. Okay? So you can, in case of a linked list, you can imagine a stack like this. Like this, it's growing, right? Like this is it's growing. And when you want to pop an element, so basically you can actually shift this top to the next position, and this will be, so basically you can free up this space. Okay? So that's how you can implement a stack using linked list. Now with linked list, the concept of space, a lot of space is used in linked list. Okay, so basically you are storing pointers as well, that will take a lot of space. And pros of both stack and cons is that you will be able to perform push and pop operation in just order of one time complexity. Okay, in just order of one time complexity. Okay, cool. Let's get to the question. Okay, so the first question that we have is of very much famous question and very much asked question. It's of valid parenthesis. Okay, valid parenthesis. So the question says that you are given brackets, the round brackets, okay, and you have to tell whether the parentheses are balanced or not. Let's say you are building this compiler in which you will be writing your code, right? So basically you will be you want your compiler to check, verify your code. So in that case you will definitely want how can we check if the bracket are valid or not. So how can we do that? Let's see. First of all, let me give you some examples. Let me write down the examples. Okay, so what do you say about the very first parenthesis? What do you say about the very first parenthesis? Are these set balanced? Is it balanced? Yes, it is balanced because a corresponding opening bracket has a corresponding closing bracket. So yes, it's balanced. Then if I talk about this, is it balanced? No, it's not, because this is complete. They are balanced, but here this opening parenthesis is lacking a closing parenthesis. Or you can also say that this parenthesis is lacking a closing parenthesis. So this is not balanced. This is not balanced. Likewise for this, so this is lacking an opening bracket, or you can also say that this is lacking an opening bracket. So this is also not balanced. Okay, so you have to basically tell, are the parentheses balanced or not? Let's say we want to attempt this question without stack. Can anyone think of something? Okay, so let me first actually put some observations. Let's do the question step by step. Okay, let's do the question step by step. So observations are, the first observation is that, can an opening bracket make a string invalid? As in, let's say I'm traversing the string and I find an opening bracket. So can that opening bracket make the string invalid? Well, it depends upon the future. It depends upon the future that if I have this opening bracket, maybe in future I'll find a closing bracket and that will be valid. Or let's say I don't find a corresponding closing bracket, in that case it will be invalid. So it totally depends. It totally depends if I get an opening bracket. Okay. Now if I talk about a closing bracket, so what about a closing bracket? Can a closing bracket be a problem to us if we encounter it? Well, so if till now for a closing bracket there was no opening bracket, in that case, yes, it is a problem, because even if we move any further, the string that is given to us will not be valid in any case, right? In any case. So basically, let's actually okay, let's take look at it like this. So I have something like this. So what will happen? Let it be like this. So I am at here. I will maintain what I can do. I can maintain a left and right count, which can be initialized to 0. Now I am at an opening bracket. So that means left actually tells a opening bracket and right tells the count of a closing bracket. So I found an opening bracket. This becomes 1. And so let this be the thing. Let this be the bracket. Now I am here. Now I am here. So what I can do? I can simply decrement the value of this, and that will tell us that we actually found a match for an opening bracket. We actually found a match for an opening bracket. So we can actually set this to 0. Right. Now let's say I have a string like this. What will happen? What will happen? That I am here, left and right. So basically I have left 1, then I have a closing bracket. So initially both are 0. So now this is a closing bracket. So is left greater than 0? Yes, it is. That means there is an opening bracket. So we can simply decrement it, telling that we have found a match. Now next we go to the next character. This is a closing bracket. Okay. So what's the value of left? It's 0. That means there's no opening bracket. In that case, we will simply return that it's invalid, because at this point there is no use to move any forward, because this closing bracket does not have a matching opening bracket. So we can simply return from here. Does that make sense to everyone? Okay, so whosoever is saying that can we count the number of opening bracket and the closing bracket? Guys, we cannot simply count the number of closing bracket or opening bracket. Okay, let's take an example of that. Let's say I have this as a string. So now left is equal to 2, right is equal to 2. But are they valid? Are they valid? No, they are not valid, because they are not placed in the correct order. Therefore, this is not a right approach. Is that cool? The time complexity of the approach is what? What's the time complexity of the approach? So if we have this case, here the number of opening brackets, closing brackets are 2, number of opening brackets are 2. So are they valid? No, they are not valid. So this is wrong. This way is wrong. So what's the time complexity, guys? Time complexity is just order of length of the string, because we are iterating the string just once. And what's the space complexity? Just order of 1. We have not used any space. Okay, we have not used any space. Now let me make a question little trickier. Now let's say I have brackets these and these. So this is an extension of the question. Extension hai ye question ka. Now I am saying that I have these 3 sets of parentheses. Now I have to tell, basically my string can contain these set. So I have to tell if those are valid or not. Let's take an example. Examples can be this, then we have this. So this will be given to you. Now you have to tell, are they valid or not? Now how can you do it? How can you do it? So whenever in the interview you're telling the interviewer that okay, we can use stack for this, but she or he already knows, right? You have to get to it, like how, what's the intuition? So that's is very important. Okay, some of you are saying that we can use 3 variables, so that will be wrong, because then you won't be able to actually find the order. You cannot judge the order by taking that many variables. So first of all, I am sure that you guys understand that it cannot happen by taking just the left count and the right count, because if okay, so first of all, let's take the example of this. Now here left is 1, okay, and now I find an closing bracket, but here they are not same, right? So this will not work. Having left and right is a bad idea. Now taking 3 variables. So here I have this string. So if I take 3 variables, let's say round, or let me write first bracket, second bracket, third bracket. Now here the first type. So this is type 1, type 2, type 3. First bracket का left right, इसका left right, then इसका left right. First का left is 1, okay. Third का left is 1, okay. First का right, so we have found a right bracket and this manages to be 0. Then we have third ka right, so this becomes 0. But is this valid? No, it's not valid, because the order is different. Order doesn't match. So therefore, that's a bad choice. Does that make sense? You should have a clear idea that why your approach is wrong. You should take as many, like if you are stuck, you are not able to think, take examples and try to generalize it. You guys are clear with it? Cool. So let's move forward. Now let's actually build some intuition of this. So one thing is that, let's consider these brackets. One thing is that since, okay, so this is invalid, right? This is invalid. This is also invalid, right? This is also invalid. This is valid. This is valid. They have right set of pairs. Now this is also, this is what? This is what? This is also valid. Okay. This is also, as you can see, that this is also valid. So if I talk about this string, then it's a property of the valid parenthesis that if the complete parentheses are balanced, then their sub parenthesis will also be balanced. As you can see that this is balanced, this is also balanced, this is also balanced. So we are not considering all the substrings, right? We cannot consider anything like this or something. We have to choose the right set. But what it means is that whatever the parentheses are inside it, they will be balanced anyhow. So this is its corresponding pair. Then we have this, it's correct, then it's correct, then this is there. So does that make sense? That inside of it parentheses are balanced? Now, so an opening bracket does not bother us, right? An opening bracket does not bother us because in future we may find a closing bracket for it, right? But let's suppose I am at this closing bracket. Let's suppose I am done with everything and I am at this closing bracket. Now for this closing bracket, this is an opening bracket, this is an opening bracket. Does these brackets are of any use to me? No, they are not. Can I get rid of them? Then that would be great, right? So if I can get rid of them, because they are valid in itself, right? As I told you by this property. So since they are valid, if I can get rid of them, then I can actually find out if this bracket has a matching opening bracket. Okay. So let's actually see a dry run of this using stack, because stack is the data structure that helps us find. Just look at just the past. Okay, just the past. So how and what we can do? We are at this bracket. This is our opening bracket. We'll see about it in future. So push it onto the stack. Then this is an opening bracket. We'll see about it in future. Put it on top of stack. Again an opening bracket. Put it on top of stack. This is a closing bracket. Was there an opening bracket for this? Yes. Where can I see? I can see it on top of stack. If there is a corresponding match for this closing bracket, then I can simply pop it off. Next time here, this is a closing bracket. Does this have a match? And see how nicely we have removed between whatever was presented. That is here, we have removed it. We have removed it. And now we are actually comparing this. Where can we find it? On top of stack. So yes, it has a match. Remove it. So now we are here. Now we are here. Put it. So this is our closing bracket. Yes, match found. So remove it. Remove it from top of stack. Then we have an opening bracket. Push it on top of stack. Okay. Then we have a closing bracket. Is the corresponding opening bracket present? Yes, it is present. Remove it from top of stack. Now we are at the last bracket. Is the corresponding opening bracket present? See here how we have gotten rid of all of this, right? So basically, yes, it's present. From where we can find? On top of stack. Just remove it. What's the condition we have to check for validity? That if the stack is empty, then return true, right? If the stack is empty, return true. But if the stack is not empty, so we have to return false. That tells, even after iterating the string, let's say we have completely iterated the string, even if the stack is not empty, so we will have to return false, right? Because there are still left some unmatched opening brackets. So at any time, let's say you have something like this. So at any time you don't find, so okay, let's do a dry run of this as well. So this is an opening bracket, move ahead, opening bracket, move ahead, closing bracket, but no corresponding match. Simply return from here. Simply return from here. Okay, so now let's move on to the next question. But before that, let's talk about the time complexity. The time complexity of this approach is just order of n, because we are going to each and every bracket not more than twice. How? Once while pushing it and another time while popping it. So that's only 2 into n, which makes it order of n, right? That makes it order of n. And the space complexity is order of n, because in the worst case, we may end up pushing all the brackets in the stack when, let's say, the string was something like this. In that case, you will end up pushing all the brackets in the stack. So the space complexity is order of n. Okay, so I hope that's clear, and we'll quickly move on to our next question. So intuition is that how can we, previously clear up something to get just the, so here as I talked about that step by step we made the intuition, like, sorry, I just removed it. So as I was talking about that, inside of it will also be, balance. So if we can remove it, I will just be able to look at here. That's what I want to do. So we can simply remove it, and that is possible using stack. Okay, so let's move forward quickly. Cool. So question 2, and this is very, very famous question, which is of next greater element. Okay. So question is that, let's suppose you are given an element, you are given the elements in an array. Let's suppose 10, 13, 22, 7. For each of these elements, you have to tell that what is the next greater element to its right. Just the next greater element to its right. So what's the next greater element to the right of 10? It's 13. Okay, it's 13. The next greater element for 13, it's 22. The next, is there any next greater element for 22? No, it's not. So we can put -1 over here. We can put -1 over here. Then we have 7. So next greater of 7 to right of it, it's -1. Nothing is there. Nothing is there. Okay, so let me take, this was example 1. Let me take another example as well. So we have 10, 7, 4, 2, 9, 10, 11, 3, 2. Okay, so what's the next right to the right of 10? It's 11, right? Just greater element on the right of 10. It's 11. Just greater element on the right of 7. It's 9. It's 9. Just greater element to the right of 4. 9 again. To the right of 2. 9. Just to the right of 9. It's 10. Just to the right of 10. 11. Just to the right of 11. Nothing. To the right of 3. Nothing. To the right of 2. Nothing. Okay? Okay, cool. See, if you are implementing any question, You can use STL in C++ or collections in Java. You don't have to implement push pop functions on your own. That's just for the sake of if let's say your interviewer asks you. That's it. Okay, that's it. Cool. So if the question is clear, please tell me that how can we attempt it. At least give me the brute force approach. At least give me the brute force approach. So you will agree with me that brute force is nothing. So brute force is using two loops. So you can basically, let me actually write the code for it as well. So the brute force look like that. You can have an answer variable, answer array. Then you can iterate through all the elements from 0 to n minus 1. Then for those elements, you can again iterate from. So, okay, first you can initialize your result to -1 if let's say you don't find any element. So you can do for j that goes from I plus 1 to n minus 1. You can check if a of I is, so a of I is less than a of j, then simply put answer I is equal to aj, okay, and break from here. Take a break from here because you just have to find just the larger element. You don't have to iterate any further. Okay. Now what do you have to do? Actually, this should be result, and out of this for loop, you can set answer I is equal to result. Does that make sense? This is just the brute force approach. Okay, cool. Let's go ahead. So the time complexity of this approach is order of n square, since there are two nested for loops, and the space complexity would be order of n, which we can ignore because that will be just to store the. So basically, this is just so we can actually make it order of 1 only, because we anyway have to take an answer array. Answer array we anyway have to take because that's how we are going to return the answer. So the space complexity for this we can assume to be order of 1, right? Cool. Now let's talk about the optimized approach and let's build some intuition for that. Let's see some observation. The first observation is that let's suppose the array elements are 12, 10, 9, 8, 7. Okay? 0, 1, 2, 3, 4. If let's suppose these were the elements, what is going to be the answer for them? What's going to be the answer for 12? -1. Nothing is on right. For this, -1. For this, -1, -1, -1. Does that make sense? The answer for all of them will be -1. Now let's talk about another example. Let's say we have 5, 4, 3, 2 and 10. Now can someone tell me what is going to be the answer for 5 now? For 5 it's going to be 10. For 4 it's going to be 10. 3, 10, 2, 10, 10 minus 1. Does that make sense, guys? Cool. So the thing is that as you can see, when the sequence was in decreasing order, we got -1 for them. And here we also had a sequence in decreasing order. But once we got an element which was greater than them, so this element was greater than these elements, so the answer for them became 10. The answer for them became 10. Look at it like this. So let's suppose I have a 5, 4, 3, 2, 10. So I start from here. This is 5, then this is 4, this is 3, this is 2. Now 10 came. So once the number came which was out of order and greater than them, so answer for them became 10. Okay, answer for them became 10. Let's look at one more example. We have 9, 6, 5, 4, 8. So this is 9, this is 6, this is 5, 4, then 8 came. So 8 to whichever element it is greater, it will become the answer to them. That is here. So this is 9, this is 6, this is 5, this is 4, this is 8. So 8 will become the answer for 6, 5 and 4. Okay? So basically now once we have got the answer for them, can I just ignore this and start by finding the answer for these now. Does that make sense? Does that make sense? Okay, giving you some intuition that here we are also ignoring whatever was redundant from the past. The idea here is that we have a monotonic sequence. We have a monotonic sequence over here. Monotonic sequence is when we have a decreasing or increasing sequence. So my point is that I had a decreasing sequence. Once I find an element out of order, so all the elements which are smaller to this will be the answer for them. This will be the answer for them. Okay? Now, so basically, let's say I have elements 11, 4, 3, 2, 10, 12. So I have 11, then I have 4, then I have 3, 2, 11, 4, 3, 2. Now 10 comes. Now 10 comes. So 10 is greater than these numbers. So answer for these will be 10. Answer for these will be 10. Now since we have got the answer for them, we can actually remove this. We can actually remove this, and now it will become such a sequence. It will become such a sequence. Now 12 comes. So this will come over here. Now whatever is smaller than answer, to them 12 will become the answer. So 12 will come over here and 12 will come over here. Now only. So we have got the answer for them. So we will remove it. And now we are just left with 12. We have completely iterated the array, and whatever we are left with, to them the answer will be -1. -1. Okay. So since we are ignoring whatever is redundant to us previously, and since this is a monotonic sequence, therefore stack will help us over here. So let's see the dry run using stack. So intuition was that we had to look at the just past, removing this just past. So whatever answer we had got, we will just ignore them, and now we'll start again from some monotonic sequence like we did over here, over above, right? Okay, so now let us go through the dry run using stack. Then again, if you guys will have some doubt, we will come to those. Okay, so I have 11, put it onto the stack. So 11 has been put onto the stack. Then we have 4, put it onto the stack. Then we have 3, put it on top of stack. Then we have 2, put it on top of stack. Then we have 10. Now this, you can see that this is a decreasing order. This is a decreasing order. Now we found an element out of order. So to whatever elements 10 is greater, the answer for them will become 10. So is 10 greater than 2? Yes. So we found the answer for 2. Answer for 2 is 10. Remove it. Is 10 greater than 3? Yes. We found the answer for 3. The answer for 3 becomes 10. Remove it. Now is 10 greater than 4? Yes. So we found the answer for 4. The answer for 4 becomes 10, and simply remove it. Now is 10 greater than 11? No. So simply push 10 onto the top of stack and move ahead. Now we are at 12. So on top of stack there is 10. 10 is lesser than 12. So answer for 10 will become 12, right? Answer for 10 will become 12. Now, so we are at 12. Is 12 greater than 11? Yes. So answer for 11 becomes 12. Okay? So now nothing is there. Simply insert 12 on top of stack. Now move ahead. So we are done. We are left with no more elements. So whatever is present on top of stack, the answer for them will become -1. So in this case, answer for 12 is -1. Guys, does that make sense? So Anshul says that then in this solution, we need to also store index and stack. Anshul, that's what we are going to do. We actually need to store indexes on top of stack, because we actually are trying to find the answer for the previous elements that we are done with. So let me quickly show you a dry run of how we can do this using indexes. Okay. So we are having the stack. We will place 0 over here. Then we will place 1, right? Then we will place 2. Then we will place 3. So basically still the array is in decreasing order. Now we found 10. So this 10 is greater than what is present on top of stack. So basically answer for this. So we will write it like this. We will write it like this, s dot top. Okay? Because this is the index. So a of 3 is nothing but 2. So 10 is greater than 2. Answer for this has become 10. Then likewise, answer for this will become 10. Element at index 1 is 4, which is lesser than 10. Answer for this becomes 10. Now 11 is not smaller than 10. So we will simply push the index of 10, which is 4. Then we are here. Now this is 12. 12 is greater than a of s dot top. So we will simply mark the answer of a of 4 as 12. So this is 12. Again, so as we remove it, then a of 0 is lesser than 12. Answer for a of 0, that is 11, will be 12. And now whatever is present on stack, whatever is present in stack, you will simply mark their answer as -1. So you will put -1 here. And the time complexity of this approach is order of n. Since we are putting an element and removing an element just twice, so again order of 2 into n, which is nothing but n. And space complexity in the worst case can be, when let's say the complete array is in decreasing order, it will be order of n. So does that make sense to everyone? Okay guys, so we have actually placed the link to the questions for the next questions. Okay, so hope you guys try it, and guys, this was it. I hope you enjoyed it. Cool. Please try them. See ya. Bye-bye.
Hey everyone, in this lesson we will discuss logical view or abstract view of queue data structure. Basically, when we talk about abstraction, we don't go over implementation details. We generally discuss about features and operations. In actual practice, queue is a structure in which whatever goes in first comes out first. So in general, queue is a FIFO structure. Whatever goes first, it should go out first. So if we want to construct queue as a data structure, then we need to support both insertion as well as deletion in the queue. In queue, as we need to maintain FIFO property, so both removal as well as insertion should happen from different end. It means if insertion happens in the front, then deletion should happen from the end and vice versa. Let's take an example to understand this thing. Let's say this is the snapshot of the queue at some particular time. Let's say this is the snapshot of the queue. And this is the front element of the queue, and this is the last element of the queue, or we can say as rear element of the queue. Now, so as we can see here that if we want to make an insertion, it should happen at the end of the queue, which we call as a rear or tail of the queue. Likewise, deletion should happen from the start of the queue, which we call front of the queue. As if I want to delete some element, it should be even because this element entered first into the queue. And if I want to insert some element, it should insert here. So this is the snapshot of a queue at some particular time. Okay, so what we have seen here, queue as a abstract data structure, a list or collection with the restriction that insertion can be performed at one end, that is the rear of the queue, and deletion can be performed at other end, that we can say here as the front of the queue. Let's discuss operations in the queue now. If we want to create a queue, what sort of operations that we need to support? The first operation is insertion, which we call enqueue in the terms of a queue, or we can also say it as push operation. We need to push an element into the queue. And also one other operation that we need to support, that is the dequeue, where we need to remove one element from the queue or pop an element from the queue. Now, if I want to create an interface for the queue, how it will be like? Let's discuss about that. If I want to create an interface for the queue, it will be something like I need to support these functions. The first function is enqueue, which supports insertion. And the second operation is dequeue. And here I am assuming that queue is maintaining integer elements, but it can be of any type. Okay, and the dequeue operation means delete an element from the queue, and where this return type symbolizes the element that I deleted. It solely depends upon the implementation that whether we want to return that element or not. We can keep it as void as well. That depends upon the implementation. Also, what sort of other things that we may need from the queue. That what is the element which is present at the front, or we can say it as peak. Is my queue empty or not? So these sort of operations that I may need in order to implement a queue. So what we can say that in high level terms, these sort of operations that we need to figure out in order to implement queue. And most of the languages has an inbuilt library which provides the interface, which may vary from language to language. And as a developer, we don't need to worry about the implementation details, and we can create a queue data structures with the help of available functions. As we have seen here that the operations can be enqueue, dequeue, front is empty. Now what we can say also as queue as a container which is open from both ends. As we have seen here that we are entering an element from this side and removing an element from this side. So it is actually an open container where element goes in from one end and element removes from other end. Now let's say we have this operation available in the library. Let's try to simulate queue. Okay, let's say in the starting we have an empty queue and we need to insert an element 2 into the queue. That means as we have in library, so then we can simply call enqueue function of that library and we can insert queue in our 2 in our queue. So when we insert 2, it will come from here. Fine. So now as we know that we need to maintain 2 pointers or 2 variables which keeps track of which is my front element as well as which is my rear element, so that the implementation becomes easy. But so if we have only one element in the queue, then both front and rear pointing to 2. Fine. Now let's say we are inserting one more element into the queue, that is 5, and it will go from the rear side, from this side. Now we need to update our front and rear. Let's say internally the library it's handling all those things. Now the rear reaches here and front remains here. Now let's say we have one more operation. Let's say somebody asks one more operation to insert 3 into the queue. Then the snapshot of the queue will be something like this, where the rear is pointing here and front is pointing here. Now let's say somebody asked us to dequeue an element, that means delete an element. As we know that deletion occurs from other end, from this opening of the container. So then our front got updated to 5 and the rear will be 3. So now we have done the simulation part and we have seen and the queue in a high level way actually. Now let's discuss some real world examples to understand it better. And it is generally used when there is a shared resource that's supposed to serve some request, and resource can handle one request at one time. In such scenarios, it makes more sense to queue up the request and the request that comes first serves first. Let's consider an example. Let's say we have a printer that is being shared across the network and it can print only one document at a time. When more than one request comes to it, it cannot say that I cannot serve your request. So what printer will do? It will maintain a queue of requests and serves them one by one as long as there is a request in a queue. It will keep picking up the request one by one. Let's say we have a printer and all these computers, they are requesting to the printer for the request to print a document, but the printer can only print one document at a time. So what the printer will do, it will maintain a queue and store all the requests into the queue. And what it will do now, after serving a request, it will pick an element from the front of the queue and serve that request. In this way, it will manage everything. So this is one of the real world scenario where we can use queue. This is good for the introduction part of the queue. In the next lesson, we will see how we can implement queue. Thanks.
Hey everyone, as you can see here that we have already maintained the 8-day streak and we need to maintain a streak. So in today's class, we will solve some of the questions of stack and queues. Proceed at that level. Let's solve some questions. Okay, let's solve the very first question. The question is, let's say all 3 questions of this clever stack. Okay, let's start the question. We have been given an array, and in that array, you need to find the nearest smaller element gi for every element ai in the array, such that the element has an index smaller than I. Okay, let's say we have more boundary. Gi is the element aj is greater than I. Okay, the basic question is, for each particular element in the array, we need to figure out the nearest smaller element for that particular element in the array. Okay, let's say this is our array, and for 4, as we can see that no element is less than 4 in the left side, so we have g1 is equal to -1. So for 5, as we can see that the minimum most element for 5 in the left side is 4, so our answer will be 4 for this case. Now if I can see for 2, okay, both 4 and 5 are greater than 2, so for 2 as well, I can see that there is no minimum element in the left hand side, so -1 will be for this as well. Now, okay, similarly, okay, now let's try to solve this question. Okay, how I can solve this question? Let's first think. Okay, for each element, if I do in a brute force way, what I need to do, I will just iterate over all the elements in the left hand side, and I just figured out whether there is an element which is lesser than that particular element. If I figure out that element, then I found the answer. In that way, I can proceed. Let's first copy this example. Okay, okay. Now what we can do, how we can solve this question, let's see. Okay, let's say, let's start from the end. Fine. Okay, let's say in the initially we have an element 8 only. Okay, now as I move ahead, I just found an element 10, and I know that that element is greater than that element. So I haven't find the answer for 8 as well as 10 yet. So what I can do? Okay, now I just figured out 2. Okay, one thing that is clear to me that 2 is smaller than 8 as well as 10. So, okay, so one thing for sure that I can say that 2 will be the answer for both 8 and 10. Okay, so what I can do, I can update my answers, and I just need this data point only, because I already figured out the answer for this. So I just need to maintain 2 only. Now let's say I just go into the other element. I have 5. Okay, if I found 5, when I have 2 to which I need to figure out the answer, for 2 I know that 5 won't be the answer. So I haven't found the answer for 2 as well as 5. Now I figured out 4. Now I figured out 4. I can say that, okay, 4 is lesser than 5. So for 5, 4 definitely will be the answer, for sure. But for 2, it won't be the answer. So after then, I need to store these 2 points, isn't it? So the way if I will do in that way, I will figure out the answer. So what I just think, okay, I am appending the elements, and as I'm appending the elements, I'm checking. And if I need to check the element, what I'm doing, I am just first checking for the last element, and then the second last element, and I'm doing in that way, and I'm able to solve this question. If I'm able to do in that way, then it's easy to solve. So I need some sort of data structure which helps me to maintain this information. And that data structure should be something like where I can add the element in the end, such that I can also remove the element which I just added in the end. So it should be last in, last out. And we know that stack is that data structure which provides that sort of thing. So I can use stack here and just try to solve in that way. I am able to achieve, because what I am doing, I am adding an element in the stack, and when I just found an element which is lesser, what I am doing, I am just checking with all the elements in this stack, and if I figured out an element which is greater than that element, I'm just removing it to the stack. So only I am adding an element one time into this stack, and I also am removing from this stack only one time. So that means it's kind of order of an algorithm that we just achieved. Okay, let's try to think how we can write code for this question. Okay, let's write the code. Okay, let's try think what are the constraints that we have been given. Okay, we have not been given any constraint, and the thing is, if we haven't find an answer for any element, we need to return -1 for that particular case. Okay, let me first what I can do, let me first figure out the size. Okay, let me create my answer, which is of size n, and let me have the default value as -1 for each particular element in that particular array, because we haven't found the answer, and we will follow the algorithm as I discussed here, so that we will be able to achieve our solution in order of n time. Okay, let's try to think, okay, how I can do that. We just need to iterate. In the last element, I need to move till the first element. In that way, I need a stack data structure to maintain the information, as I just discussed. Why? Okay, so now what I can do if I need to question, okay, one thing I need to be sure that, but what will be the edge case? If my stack is empty, if my stack is empty, or if I have my element which is at the top of my stack, okay, if I figured out an element, okay, which is greater than my top, then that means I haven't found the answer for both of the elements. So I need this data. So I need to push that element into my stack. If that is the case, if that is greater than, that is element is greater than or equal to my that element, so I need to push that element into my stack, isn't it? Okay, now I'm done here. So I can new. Okay, if there is other case, if the element at my top is greater than AI, if that is the case, then I need to check for how many elements I have found the answer. So let's first just check the edge case, whether my stack is empty or not. While my stack is not empty and my top element in the stack is greater than AI, in that case, what I can do, I know that answer for stack dot top will be equal to AI for sure. है ना? And I can safely remove that element because I just figured out the answer for the topmost element in this stack. Now I need not need this data in the future, so I can safely remove it. By the time this thing gets ended, I can say that okay, now I'm done. Now I can safely add a ith element because I haven't found the answer for ith element yet. And in the end, what I can do, I can return my answer. And let's check once again whether I'm doing in the right direction or not. I am maintaining my answer, and I just created an empty stack, and I'm checking if my stack is empty or if it is greater. So then I need to push that element into this because it's of no use. Otherwise, I need to check if my element is lesser. So that means for that topmost element, I just figured out the answer. So what I need to do, okay, in that way, if I just do in that fashion, I can solve. Okay, that seems like a good approach. Let me test. Okay, it's giving me correct answer. So let's submit. Oh, nice. Nice. We have solved this question. Now let's move to the next question. Okay. What will be my next question? Okay, now the next question is I need to figure out the largest rectangle in the histogram. Okay, that is my question. Let me think. Okay, let me first read the question. We have been given an array of integers a of size n, where a represents a histogram. That is, ai denotes height of ith histogram bar, and width of each bar is 1. Okay, let's say we have been given this histogram, and where the height of first bar is 2, and the height of second bar is 1, and height of third bar is 5, and fourth bar is 6, and so on. And above is histogram, and width of each bar is 1. And we have been given heights like that, and we need to figure out the largest rectangle in that histogram. Okay, let me think how we can figure out that thing. Okay, if that is the case, this will be my answer. Okay, they are saying this will be my answer, and the answer will be 5 as my height and 2 as my width. So my answer for this will be 10. Okay, so let me just copy this thing. Let's try to think how I can solve this question. Okay, so the question was, we have been given an histogram where the values are 2, 1, 5, 6, 2, 3. Okay, and we have been given histogram like that. Let me first draw the histogram on the paper and then it's more suitable. Okay, 1, 5. Okay, it will be 5 and then 6 and then 2 and then something 3. Fine. So this will be my answer in this case. So what I can think is, what can be the brute force way to solve this question? One thing is coming to my mind. I can solve it in a way that, okay, let me take all the contiguous segment to solve this question. Okay, and I can take all the contiguous segment of length 1, then length 2, and just try to find the answer for that contiguous segment. Let's say I just take this contiguous segment of first 3 element, which is 2, 1, and 5. What will be my answer for this contiguous segment? Okay, I know that the width will be equal to 3, but what will be my height in this case? Okay, I can surely say that if I want to build a rectangle, then the height will be the minimum height histogram available in that contiguous length, isn't it? So I can say that the height will be 1. If I do in that way, then I can solve this question. That is fine. Okay, so if I just take in a brute force way, so how much time it will take to me? I need to iterate over every contiguous segment, and to iterate over each contiguous segment, I need to take 2 variables L and R. So it will take order of n square time. And for each contiguous segment, I need to find the minimum most element. So the complexity will go up to n cube. So it doesn't sound me a good solution to solve this question. Can I think something else to make my algorithm better? Okay, let's think what I can do. Okay, let's think. Let's say I have an example, something like this. Okay, let's say this is my example. If I build a histogram, I have 7 here and I have 8. I have something 6. I have again 8 and I have something again like 7. Okay, if I am just considering all the contiguous segment, I will consider this segment as well, and I will consider this segment as well, I will consider this segment as well. I will definitely consider all the segments. If that is the case, that means, but I know that for all these segments, if I did in that segment, 6 is the part of that segment, then my minimum value will always be 6. Okay, can I use this idea to achieve something? Okay, why I am just iterating over all the contiguous segment? Why not that maximum contiguous segment for 6, which will give me the answer? Because in any way, other contiguous segments are waste for me. That's the waste of computation time. If somehow I just figured out for that particular 6, what will be the maximum contiguous segment if I just consider this element? So one thing I can surely say that, okay, if I just consider this element, how much elements I need to take in the right hand side, that I need to consider. Okay, I can consider 8, I can consider 7, but if I have something 5 here, I can't consider that element. Okay, this gives me the idea that what I can do, I can just take the nearest minimum element for a particular element in the right side. Fine, because such that all the elements in between will be greater than 6, and I can consider those elements for this element. And likewise, I can extend my similar approach in the left side as well. So this gives me some idea. If I do in that way, I can solve my problem. Okay, so this gives me the idea what I need to do for each element. For each element, I need to figure out the nearest minimum element in the right hand side as well as in the left hand side. Because I can surely say that this will be the maximum contiguous length for that particular element, which will give me the answers. And if I take any smaller contiguous length for that particular element, they are of no use. And in the previous question, we just solved how to figure out the nearest minimum element for any particular element. And we know that we can solve this using stack in order of n time. We just solved it. Okay, I can use that approach here as well, and I can solve this. And I can solve similar for the right hand side and for the left hand side, and I'm done. That is sounds like a good solution. Let's write the code for this now. Okay, let's write the code for this question. Now let's say this is the case. Let's first try to dry run this. Okay, now for 2, I know that the nearest minimum element for 2 in the right hand side is 1, and in the left hand side I don't have any element. Fine. And so I just end up with a contiguous segment of one element only for 2. So that means for 2 my answer will be just 2. Now if I take 1, now for 1 I can see that for 1 5 is greater, 6 is greater, 2 is greater, 3 is greater. So I can pick all the elements for 1 in the right hand side. That is good. And in the left hand side as well, I can pick all the elements. That sounds like a good thing. So I can do like that. If I do in that way, so for 1, length available will be equal to n, so which is 1 2 3 4 5 6 in this case. So my answer will be 6. Now for 5, if I do in similar way, I can see that for 5 the minimum length available 6 is greater than 5, and okay, I found element 2 which is less than 5, so I can only consider these 2 elements for 5. Now if I just think of an element in the left hand side, I can see that 1 is the minimum element for 5, so I can consider only these 2 elements for 5. So I have a length of 2 for 5. I have a length of 5, so my answer will be 10 if I take 5 as a length. Okay, now if I take 6 as a length, then my area to consider for 6 will be, I can't take this element because this is smaller than 6, and I can't even take this element. So because these 2 elements are the nearest minimum element for 6, so I just have a one length for 6. So my answer will be equal to 6 only. Okay, now I consider for 2. If I want to consider for 2, okay, 3 is greater than 2, so I can consider that element. Now if I move into the left hand side, I can see that 6 is greater than 2. Okay, nice. And 5 is also greater than 2. Nice. But 1 is smaller than 2. So the nearest minimum element in the left side for 2 will be 1. So I can consider only these 2 elements for 2. Fine. So the total elements I can consider for 2 will be these 4 elements. So my length will be 4. So my answer for this case will be 8. Now for 3, let's consider what will my length. Okay, for 3, I can say that for 3, there are no elements available in the right hand side, but let's see what are the elements available to me in the left hand side. Okay, 2 is the nearest minimum element for 3 in the left hand side. So that means I have just of length 1 for 3, and answer will be equal to 3. Okay, I have considered all the elements by using that analogy, and I can see that if I want to consider that element, so I can just get the maximum length of 5, maximum length of 2 for 5. So that means it's okay to do like that, and in the end what I can do, I can find the maximum answer out of them, which is 10. So 10 will be my answer. Nice. If I do in that way, I can figure out the answer. Nice. And I can see that 10 is the answer for this question. Nice. So let's try to write a code for this. But with the simplest code to write the solution for this will be, let's first have a size. Okay, I need 2 informations for every particular element. What will be the nearest smaller element? For that element in the right hand side, I also need the information, but with the nearest smaller element for that particular element in the left hand side. So I need both the information for any particular element. So let's say I created 2 vectors. The one of them is storing the smaller in right side. I need that information for all the elements. So I just initialize. I just need the size of n, and what should be the default value. Okay, I know that if for that element, I haven't found any element which is lesser than that element in the right hand side. So I can say that, okay, let's just say that, okay, so in that case, I may end up end of my list, so I can safely mark it as n. Okay, because that seems like a good thing. Okay, now I need one more information which is smaller in the left side. I need that information as well. Okay, if I need that information, so I need this information an element, and in similarly I know that if I move into the left side, I haven't found any element which is lesser than this particular element, so I end up with an index of -1 because something like it goes beyond 0 in the left hand side. So I can pick the default value as -1, which seems like a good thing to me. Okay, now let's fill both of these arrays. How we can fill? So this is quite simple. We need a stack for this, because what we need to do, we need to figure out the nearest most element in the right hand side as well as the left hand side. As we discussed in the previous question, we can easily do this by using stack. And let's say I created a stack. Now let's first solve it for the right side, and let's say I need to iterate. Okay, now how we can do that thing? Let's say I consider the edge case. Let's say my stack is empty, or the value available at the top of my stack is actually less than or equal to my current element. If that is the case, so I haven't found the answer for my current element yet, as well as for any element which are at this stack, because I just found an element which is greater than the element present at the top of the stack. So I need this information. So I need to push that element into the stack. So that's the only thing that I can do. So I have done, I am done here. So I can continue. Now, if that is not the case, that means what does this means that I am at the top. Okay, I need to first write the edge case. I need to iterate up till my stack is not empty, and my stack top is, if it is greater than AI, that means the ith element, it's basically lesser than the topmost element. So I can say that for the topmost element, ith element will be my answer. So as I'm moving into the right side, so I can update the answer for smaller right side, stack dot top. I can safely update it as I. Now I need not need the information for that particular element, so I can easily safely pop that element from my stack. Nice. So if I do in continue that way, I haven't figured out the answer for I yet, so I need this information. So I need to push that element into the stack. Let's say I just push that element in my stack. Fine. If I do similar way for my left side to populate this array, okay, I just need to apply the similar algorithm for this case as well. So what I can do, I just move into the left side now, and my algorithm will be something like this only. So I can just copy the same algorithm. Okay, so if that is the case, so but instead of left side, now I'm populating my left array for each element. Now, by doing these two operations, we just populated both of my arrays. We now have that information that for each particular element, what will be the nearest smaller element in the right side, as well as we have that information what will be the nearest smaller element for a particular element in the left side. We have both the information. Now, let's calculate the answer. Let's say initialize my answer as 0, because obviously my answer will be bigger than that 0, so I can update my answer for each particular element. Now, what I can do, okay, now what I can do for, let I have an element in consideration, which is element in consideration, let's say it is A of I. Now, what will be my temp answer? That temp answer is basically this answer, which symbolizes that if I take this particular element in consideration, what's the maximum area of rectangle that I can achieve? Okay, let's try to think. Maximum rectangle area that I can achieve for that particular element. Okay, for that, my length will be, height will be this, and what will be my width? I know that if I need to figure out the width, I need to find the nearest smaller element in the right side as well as in the left side. So for this, that's why I just keep the default value as -1 for left hand side and n for right hand side, so that it's easy to compute that thing. So let's say for 2, I have my nearest smaller element in the left side will be -1 and in the right side will be 1. So if I take the whole length will be equal to 3. If I take the whole length, my whole length, that is nearest right side minus of particular that element I, and I take the nearest left side, the particular element I plus 1. So this will be the total length. But in that particular length, I just include the nearest smaller element in the right side as well as for the left side. But I don't need to include these two elements, because these two elements shouldn't be included in the rectangle. So I can safely remove -2 to remove these two elements, and I can update my answer as max of my answer and temp answer. If I do in that way, I can easily achieve my answer and I safely return answer in the end. Let's see. Okay, I just initialize my array and I just keep my smaller right side as n. I just add the default value as n. For the smaller left side, I just did in the similar way. I maintain a stack. Okay, we missed one thing. Okay, what we need to do, because there are many elements, after solving it for the right hand side, for that particular elements, we haven't find any elements in the right side which are smaller than that element. So that element still remain into this stack. So I need to remove all that elements from my stack. So I need to remove, let's say I remove that algorithm from my stack. Okay, so now let's look at the complexity part of it. This is running order of n time, this is running order of n time, and also this is running in order of n time. So the overall complexity will be 3n, which I can safely say it as order of n. Okay, nice. So we just solved this question in order of n time. Nice. That sounds like good thing. Now let's test my thing first. Okay. Let's see the errors. We have an error at 51st line. Okay, I guess the error is okay. It's not nearest. It's smaller. Okay, smaller. And is there anything else? Okay. Okay, this is correct. And you need to push. Okay, now let's test it again. Okay, nice. Okay, everything seems correct to me. Let's submit my code. Let's see. Oh, nice. We solved this question. Nice. So now let's look the other question for today. We have solved both this question. Now let's look into this question. What this question is saying, that we have been given an array of integers. This is a sliding window of size b, which is moving from very left of the array to the very right. And you can see that w numbers in the window. Each time the sliding window moves rightwards by one position, and you have to find the maximum for each window. Okay, so the question is, we have been given an array, and in that given array, we have been given a window. We need to figure out the maximum element in that window, and that window is basically a sliding window. So what does it mean? Let me explain you. That let's say we have been given a window of size 3. So in the starting, let's say we consider the first 3 element of the window, and we figure out the maximum, and the maximum value for these particular 3 elements obviously will be equal to 3. As you can see that 1, 3 and -1, the maximum element for this will be 3. Nice. So now let's look at the other thing. Okay, now for if I just take the other next window for this particular case, the next window will be 3, -1 and -3. Nice. So if I take this window, and then I can see that the maximum for this window will be equal to 3. Nice. If I take the next other window, then I can say that the maximum for this window, it's equal to 5. Okay. And for this window, if I go in a similar fashion, I can see that, okay, the maximum is 5. And for other window, I can see that the maximum value is 6. If I go in that way, okay, if I take the last window, the maximum value is 7. Okay, so this is my question. How I can solve this question? Okay, let's think. Okay, let me move to here. Now, how we can solve this question? Let's see. Okay, we have been given as some array. Let's say we have been given array. Let's say we pick the random array now. 4, 7, 8, 3, 2, 5, and we have been given B as 4. Let's say this is given to us, and we need to figure out the maximum element in each window of length 4. So the first window will be 4, 7, 8, 3. So the maximum value for this window will be equal to 8. Nice. Now the next window will be this, and again the maximum value is 8. Okay, the next window is this, and the maximum value is 8 again. Okay, how I can solve this question? Let me first think. Okay, I need to consider all the windows. So the brute force way will be, I maintain a window and I just keep one start and end, which is referencing my current window, and I just figure out the maximum element in that particular window and I will get an answer. That's the thing that I can do, and I will achieve and I can solve it. But now let's look at the time complexity to solve this question. Okay, if I maintain one window, that means, what does it mean? It means if I need to find the maximum, okay, one way is what I can do. I can just find the maximum. I do the iteration from start to end, but this will lead to other order of n time, and how many updation that I need to do for start end, as there are only order of n windows. As we can see that the first window is of 4 element, then the next window of this 4, and the next window of this 4. So there are only 3 windows, and that's of order basically n. So the overall complexity will be order of n square. Can we improve this algorithm? Is there any way to improve this algorithm? Okay, the one way that we can do to improve our algorithm is, what I can do, I can maintain some sort of structure that we know, and that will tell me the maximum element within a given range. I can do something like that, and maybe that will solve my question. But if I need to maintain that structure, we already know that the segment tree provides that sort of flexibility that gives us the maximum value in a particular range. Okay, and this will solve my problem in order of n to order of log n. If you can use something like that, but even then my complexity will be n log n. Can I improve further if I want to solve this? Let's see. Maybe we can improve it further. Okay, let's say we have been given an example 4, 7, 8, 3, 2, 5. Okay, what we can do? Okay, what I can see here that, okay, let's say the window size is 3. Let's say the window size is 3 in this question. But I can say that, first of all, let me consider the first 3 elements of this window, which are 4, 7, 8. Okay, I just figured out one thing, that if I have only one element, I can store this information. Now I encountered an element which is greater than that element. If that particular element is greater than that particular element, so I can say that this element won't be the answer in any of the window. Why? Because I just found an element which is greater than this element and has a greater index as well. So that means if there is a chance that I will just need to remove an element, that will be the element of lesser index, obviously, for sure. And if I just figure out an element which is greater than this, so that's of greater use than this. So I don't need this information. So I can safely remove this information and I can keep this information only. Now, in the similar way, if I figured out 8, okay, I can remove this information as well in a similar way, and I can just store the information 8 only to solve my answer. Okay, if I do in this way, I can solve this question. Okay, let's see. Now my answer is 8 for this. Now, okay, now let's say I now come at 3. If we figure out an element which is lesser than this element, okay, but I can't say anything now. I can't say anything now because there may be a possibility, because it has a larger index, there may be a possibility that for some other window, this will be my answer. So I need to store this data as well. So that means we are coming up with some algorithm. If we are figuring out an element which is greater than any particular element, if that is the case, so we can safely remove the element which is at the end of my some data structure. And if I figure out an element which is smaller than that element, so I just need to append that element in the end. Nice. But one thing we also need to show that if we go in some other window, we need to remove the elements which are not in that window. And as I am just adding all the elements in the increasing order of index in that data structure, in some data structure, so I can just check whether the first element is of previous window or the current window. If it doesn't belong to the current window, I can safely remove that element. So okay, so one thing that I'm sure that I need, if I want to solve this question by using this algorithm, I need a data structure which will help me in adding in the end, also removing in the end, and also allows me the ability to remove from the front. Okay, and those all those operations should be as efficient as possible if I want to make my algorithm faster. So what data structure that comes to my mind? Okay, can I use stack? If I use stack, then these two operations will perform in a good way, but not this. Okay, so what sort of data structure I can use now? Okay, can I use queue? If I use queue, I can do this operation and this operation, but I need to sacrifice over here. Okay, then what other data structure that I can use? If I'm using some complex data structure, then the complexity will be log of n. And we already know that we just build a segment rather than that data structure that will already solve us our problem in order of log n. So we need some sort of data structure. Okay, one thing that comes to my mind, why don't we use the doubly linked list? In the doubly linked list, we can add, and we have both the pointers head and tail. We can just add the element, and then we can easily remove the element from the end in order of one time, and add that element in order of one time. And similarly, but we can do this thing in the front as well. If we follow this approach, we make our algorithm efficient. Nice. So in C++, we have this doubly linked list in a form of DQ. So we can use DQ in our case and we can solve this question. Nice. So now let's try to look at the example and we'll solve this question again. We have elements 4, 7, 8, 3, 2, 5. Okay, if that is true, now let's try to think. Okay, I have a window of 3 elements. Let's say I maintain a DQ where I just, if I have a first element, I just put it and I figure out the second element. If it is greater, so 4 is of no use, I can remove that element. So I can put 7, and if of no use, I can remove that element. I can put 8. Now I just end up with the window. What will my answer? It will always be the first element in the DQ, isn't it? Because the way we are just storing the data, the first element of that window will always give me the answer. So if we do in that way, we can just get the things done, man. That's cool. We can do in that way. Cool. So now if I want to consider a next window, it will be something this. Okay, now let's see what is the index of 8. Index of 8 is 2, but in the current, it belongs to the current window, so I not need to remove that element. So what I can do, I can just add 3 here because I need to add 3 because it is lesser than this element, and this element can be the answer for other windows. So I need to add 3. Now I am at, okay, I just add 3 and the answer will be again 8. And similarly, if I do it that way, I will find the answer. Now let's try to write the code for this. We figure out everything what is required, and we just figure out the algorithm to solve this question. Okay, how we will write the code? One thing is clear to you, one thing is clear to us that, okay, let's say first take the size. We need a data structure like BQ, and let's say it's BQ. Okay, now I need to iterate over my link or over my array. Okay, let's first do the parts. Let's say first cover the edge cases. If my DQ is empty, and or if I have an element in the end of my DQ which is basically greater than my current element. In that case, what we need to do? We just figured out in that case, we may need this information. So in that case, we can add this element in the end, and that will help me to solve this question. Now, if that is not the case, what we can do, we can check while, okay, my DQ is not empty, and we are getting, okay, we need to add 4 as well. What we can do, if my element in the back, they are lesser or equal to my AI, because I just found an element of greater an index and it is greater than the last element of my DQ. So that means I don't need that last element in my data structure. So I can safely remove that element. Okay, I can do in that way. So in the end, I need that ith element. So I need to add this element in the end. So I am done. But I need to remove all the elements which are not belong to my current window. As we can see that, okay, my next window will start when I becomes greater than or equal to B. So what we need to do in that case, if that is the case, okay, let me first initialize my answer as well. Okay, and so that means if I just end up with an index greater than equal to B, what does it mean? It means that we just completed our one window. So I can add the answer for that window in my answer vector, which will be the front of my DQ, as I already discussed why it is, isn't it? So it will be my front. Okay. Now what I can do, if that is the case, now what I need to do, I need to check whether the first element of my data structure is in the current window or not. So for that, first I need to check the base case if my DQ is not empty. Otherwise, it will give us the segmentation fault. And if my DQ is not empty, and we can say that the element, okay, the index of the element in the front should be, if it is, okay, if it is the first element, it's the 0th element. If I'm at the second window, then the index, if the index is 0, then I can safely remove that element. So the index will be I minus y, because if I at the next window, my I will be b and b minus b will be 0. If I'm at the next window, my I will be b plus 1. So if in the front I have the element which is having index 1, so I can safely remove that element. So if I do it that way, I can easily solve this problem. So if I do it that way, what I can do, I need to remove my element from the front. Okay, if I do in that way, I'm done. Nice. But okay, but what about the last element? What about the last element? When I'm at the last element, I haven't updated the answer for my last element. So I need to update it here. Let's say, okay, that will be, my answer will be PQ dot front. Okay, I just don't need to add the answer dot front. It will be the element for that. So I need A for that case, A for that case as well. If I do in that way, I think this should work. I need maintain DQ, I maintain vector. When I do in that way, I'm pushing my answer. I'm considering only cases. Now let's test. Oh, I need to return answer as well for sure. In that way. Okay, nice. Correct answer. Now let's submit the code. Nice, we solved this question. Now we are already ahead of our streak. We completed the 2-day streak in a really good way. Okay, nice. So this is all about today's lecture. Thank you guys.
Let's talk about trees and understand why trees are important for an engineer. Trees are used to implement other useful data structures like sets and maps. Heaps, priority queues and tries are also based on trees. In fact, Indexing in the database is also implemented using trees. The underlying data structure used in text editor, for example, is also based on, you guessed it right, trees. As an engineer, it is must to have a solid foundation on the trees. You should be able to solve all the problems related to trees. Companies like Amazon, Google, Microsoft, Adobe love asking questions on this. In fact, I will go to an extent and say that no Amazon interview is complete without solving a tree problem.
Hello everyone, in this video we are going to start study about an interesting data structure known as trees. Till now you might have heard about data structures like arrays, linked lists, stacks and so on. These data structures are linear data structures. For example, take a linked list. In linked list you have a set of nodes where each node points to the very next node. In this linked list, suppose there are 3 nodes. Let us say this node stores the data 4, this stores 1, this stores 8, and this is an end pointer. What is the start of this linked list? Correct. This node points to the start of the linked list. As you see that in a linked list, there is a logical start, there is a logical end pointer, and also there is a logical meaning of the next element. These are the properties of linear data structures. What is a data structure basically? Data structure is nothing but a way to store and organize data in a computer system. How will you choose which data structure is perfect for a particular problem? You might choose this based upon some different kinds of criteria. The first criteria might be the type of data that you are representing. The other decision might be to reduce cost or time complexity for frequent operations. Example, suppose you are given a problem that hey, we are given a set of numbers and multiple queries where you have to find if a particular number exists in the array or not. What data structure you will use? You can use an sorted array and apply binary search, or you might also use a hash map. Sometimes the choice of data structure is based upon reducing space complexity. Tree is a data structure that is most suited for hierarchical type of data. Consider the organizational hierarchy of a big corporation. There is a CEO. Under the CEO, there might be multiple presidents. Similarly, under each president, there might be multiple vice presidents, and so on. This is a type of data that is one of the most common types of data that can be represented using a tree. Why is it even called a tree, by the way? There is a very similarity between this data and an inverted tree. What are these things in the tree? Yes, these are the leaves. Similarly, in our tree data structure, the end nodes, had there been no other nodes downside it, are known as leaves. What is this in the tree? This is a root. Similarly, the top of the tree data structure is also known as the root of the tree. So basically, a tree data structure represents an inverted tree. Now, let us look at some terminology related to trees. Let me draw a formal tree for an example, and let me number the nodes in some way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The very first terminology that is related to tree is the root of the tree. The root of the tree is nothing but the node which is at the very top of the tree, or the node under which all the other nodes of the tree lie. So in this example, 1 is the root of the tree. Now let us discuss the parent-child relationship. As there is an edge from 7 to 9, 7 is known as the parent of 9. Similarly, 9 is a child of 7. Now, what is the case of 6 and 7? As 6 and 7 have the same parent tree, 6 and 7 are known as siblings. Okay. Now, the very common term that you will see when reading about tree algorithms is a leaf. A leaf is a node that has no child. So, in this example, node 8, node 5, node 6 and node 9 are leaves of the tree because they have no child of themselves. Now consider a path from the root of the tree, that is 1, to a particular node, for example 8. We see that on this path the nodes that lie are 1, 2, 4 and 8. If a node lies on the path from root to a particular node, for example 2 lies on the path from 1 to 8, 2 is an ancestor of 8. Conversely, 8 is descendant of 2. Now we studied about ancestor and descendant. Now let us see for a particular node 8 again. What is the length of the path from 1, that is root, to 8? As we do here, the length of the path from 1 to 8 is 3. The length of the path from root to a particular node is known as depth of a node. In this case, the depth of node 8 is 3. Similarly, what is the depth of node 3? As the length of path from 1, that is root, to 3 is only 1, which means depth of 3 is 1. Similar to depth, there is another term which is height. People tend to confuse between depth and height. As depth is the length of the path from root to a node, height is the length of path from node to farthest leaf in the subtree rooted at node. Let us take the example of node 3. In node 3, what is the subtree rooted at node 3? Correct. This is the subtree that is rooted at node 3. What is the farthest leaf from 3? As you can see that the farthest leaf from 3 is the node 9. So, what is the length of the path from 3 to 9? It is 3, 7, 9. So, the length of path is 2, which means height of node 3 is 2. So, make sure you understand the difference between height and depth clearly and don't confuse between those. This was the definition of height of a particular node. Now, what is the height of the tree? Height of the tree is nothing but the height of root node. So, in the example above, what is the height of the root node? Clearly, the longest leaf from the root 1 is 8 or 9. What is the length of the path from 1 to 8? As we saw earlier, it is 3. Thus, the height of tree in the above example is 3. Great. So, we have till now discussed some of the terminologies related to trees. Let us discuss a few properties of the trees as well. The very first property of a tree is that a tree with n nodes has n minus 1 edges. Why do you think that is the case? Let us go back to the tree that we draw above. We see that for all the nodes other than the root node, there is an edge pointing to the node. For example, for the case of node 2, there is one edge that is pointing to the 2. Similarly, for node 4, also there is only one edge pointing to the node 4. Similarly, for node 5 and all other nodes. So we see that there is one edge from to any node other than the root. So for n nodes, all nodes other than root have an edge pointing to them. This means there are n minus 1 edges. Based upon the properties of the trees, different types of trees are also defined. So, for example, if all the nodes of a tree have less than or equal to 2 children, this means the tree is a binary tree. Extending this thing, if all the nodes of the tree have less than or equal to n children, implies that the tree is an n-ary tree. Let us take an example. Do you think this particular tree is a binary tree? No, this tree is not a binary tree because we see one node has 3 children. Implies that not binary. Do you think this is a ternary tree? Ternary is also known as 3-ary. We see that this node has 3 children, this node has 1, and all other nodes have 0 child. As we see that all the nodes in the tree have less than or equal to 3 children, this means that this is a ternary tree. Similarly, there are many other properties of the trees of different kinds of trees. For example, there is a binary search tree. We will discuss this in depth in a future video, but as an overview, a binary search tree has a property that all nodes in left subtree of a node have values less than the node value, and all nodes in right subtree have values greater than the node value. Now let us move to some of the applications of this tree data structure. A tree data structure is a very important data structure and is used in many real-life applications. As we discussed earlier, that tree data structure is the by default data structure for hierarchical type of data. So it is used in applications that resemble hierarchical data. Example, the file system of your computer. How is a file system like? There is a parent directory, or which is also known as the root directory. Inside this root directory, you might have multiple other directories and files. For example, this is a directory D1, D2. This might be a file F1. Similarly, there might be another directory D3. Each of those directories can in turn have other directories under them or files. For example, suppose D1 has one more directory inside it and 2 files. A file cannot have anything inside it, so file in a file system will be a leaf node. There might be a directory, for example in this case D2, that might not have anything inside it, which can be an empty directory. I hope it is clear as to why tree data structure is one of the best data structures to represent your file system. The second application of tree data structure is by different types of trees that exist. For example, there is a tree known as trie. Trie is a data structure that is very good to represent dictionary. It allows us to search if a word of length m exists in the dictionary in order of m time. We will study trie in depth in one of our future videos. Similarly, as I talked briefly before, there is a type of tree known as binary search tree. Binary search tree allows us to find if a data exists in the tree in order of height of the tree. That is why you will see that height of the tree is very important factor in analyzing the complexity of tree algorithms, and we will study it in depth also in future videos. One last application of tree that is commonly used is in routing protocols and internet. Are you guys aware of a DNS? A DNS is represented like a tree. Suppose you have to find the address of www.google.com. A DNS server is organized like a tree. There is a root domain dot inside under which there is a .com, under which there will be a .google, under which there will be www. Similarly, suppose it had to represent facebook.com as well. To represent facebook.com, the root domain will remain the same, .com will also remain the same, but there will be another Facebook here. Great. I hope it is clear as to how a DNS server might now be resolving your queries.
Myself Robin, and we'll solve some of the simple questions of tree today. Let's solve some basic questions today. Let's start with the simplest question with the binary trees. Now we have been given a binary tree and we need to figure out whether that given tree is height balanced or not. Okay, what is the definition of height balanced binary tree? It is defined as a binary tree in which the depth of two subtrees of every node never differ by more than one. Okay, I need to return 0 or 1 for this problem. I need to return 0 if my tree is not balanced, and I need to return 1 if the given binary tree is balanced. This is the input that is being given to me, and I need to figure out whether the given binary tree is balanced or not. Okay, as we can see that the height of the left subtree here is just 1, as well as the height of right subtree is also equal to 1. It means that, okay, the difference between the heights for the left and right subtree, it's equal to 0. Okay, if it is 0, that means it is less than 1. So the answer for this case, it should be true. Okay, fine, nice. Now if I just visualize this input, in this input, as we can see that in the left side we have 2 nodes, but in the right side we don't have any node. It means that, okay, the height in the left subtree, it's equal to 2, but the height of the right subtree is 0. So if I take a difference, then the difference for this as a rule, it's equal to 2 minus 0, which is 2. And as it is greater than 1, so that means I need to return false or 0 in this case. Okay, now we got the question. Okay, now let's try to visualize how we can solve this question. Okay, the question is, we have been given a binary tree. Let's say this is the binary tree that is being given to us. And we need to figure out whether that given binary tree is balanced or not. Okay, the simplest thing is kind of a really simple question, that what we can do in this case, I need to first check if that given binary tree is balanced or not. That means that first of all, the left subtree also should be balanced, as well as right subtree also should be balanced. That should be true. If both the things are true, and if I just calculate the height of the left subtree as well as the height of the right subtree, if I figure out height of both the subtrees, then the difference should be less than equal to. If these 3 cases are true, that means I can say that, okay, that given tree is height balanced. Okay, now if I need to do that, in order to solve for my complete tree, whether that complete tree is height balanced or not, what I need to do, I need to check for my left subtree whether my left subtree is height balanced or not, or as well as my right subtree is height balanced or not. And again, when I just reached at my left subtree, and again I will check whether the left child of left subtree, the left subtree of the left subtree, it's balanced or not. Similarly, I will check for the right side, and for here as well, I will check for both the sides. So it seems to me kind of a recursive approach in which the way I can solve this question, if I build some sort of recursion. Okay, I need also some sort of information which will help me to evaluate the height in the left side as well as in the right side. Simplest approach that is coming to my mind is, what I can do, I can make a function, pass the root, and check whether the left side is balanced or not, or also check whether the right side is balanced or not, and somehow evaluate the height for the left side and evaluate the height for the right side as well, and then just check the difference. And if this gives true, and height is less than equal to 1, in that case I will return true. In other case I will return false. If I just apply that algorithm, that will give me the answer. But now let's try to analyze the complexity of it. Okay, I'm doing some sort of one traversal over the tree, which will cover my recursion part, and also I'm evaluating the heights. Okay, if I will evaluate the height, that means if I am at some node, I need to traverse each level if I want to figure out the height of the given tree. Okay, again, that can go up to order of n. And at each step, I am just figuring out the height. So the complexity in if I solve by this algorithm will be order of n square. Okay, can I do better? Okay, if I want to do better, that means I want to somehow pre-store the height information. Okay, so one approach that is coming to my mind that what we can do, first evaluate the height of every node. Okay, but then it will take off an extra space. Okay, though, so two solutions comes to us. One of them gives us solves our question in order of n time, order of n square time, and order of one space. And the other solution solves our question in order of n time and order of n space. Can we think of something better? Okay, such that we can solve this question in order of n time and order of one space. Okay, let's try to think first. Okay, the point is just we need to check one thing only, and that thing is basically the difference between the heights of left and right subtrees. Okay, and if I check this information at each level and at for each node, and each node just give me the answer, the difference less than equal to 2, then I am damn sure that that given tree is height balanced. So what's one thing that is coming to my mind, that forget about this thing, just try to solve in such a way I can just figure out the heights, because I know that if I want to figure out the height of a tree, it will be I need to figure out the height of my left subtree as well as I need to figure out the height of my right subtree. So if that is the case, and the height of this will be, because anyways if I want to calculate the height of a tree, I want to evaluate the height of the left and right subtrees. So the whole recursion part, it can also be covered here. So one thing that I can do, I just evaluate the height of every node, because if I want to evaluate the height of every node, I am checking this condition. I'm doing this thing. So, and I can check whether the difference is less than equal to 1. If it is, that means I'm done. That means, okay, if it is greater than 1, that means I just found a node such that that node is not height balanced. If a particular subtree of a given tree is not height balanced, that means I can't say that the whole tree is height balanced. That means the whole tree is also not height balanced. Fine. So I can, the one thing that is coming to my mind, that what I can do, I can keep a one global variable which just track this information. And if I just solve in that way, I'm done. Sounds like a good solution. Okay, let's try to solve this now. So the way I think is, so let's first make a global variable is complete tree balanced, and I can initialize the value here for this global variable. It's complete tree height balanced, and I should initialize it with true. Okay, now what I can do, I can calculate the heights for each node, because I know that while I'm calculating the height, I can check the overall height balancing thing. Let's calculate the heights. Let's say first for A, and it should return me integer value. So let's calculate height for a given tree node. This is the case. Now if A, let's try to handle the edge case. If we don't have A, then I need to return 0. Otherwise, the left subtree height, if I need to evaluate, then I need to calculate left height. Again, that function with the left node. If I want to evaluate right subtree height, same function with the right side. I need to follow this procedure, and now I can check this thing. If the difference between left subtree height and right subtree height is less than equal is greater than 1, that means I'm done. I just found a node, or I found a subtree in more specific sense, that is not balanced. So I can change my global variable is complete tree height balance or not to value false. Nice. If I do in that way, I can surely achieve something, and I need to return the height of that given tree, which will be equal to max of left subtree height or right subtree height plus 1. Nice. If I just solve in that case, and I can return that global variable, because if it is true, I need to return integer. I just need to check if it's complete tree height balanced. I need to return 1, else I need to return 0. That is it. Let me check. I just created a global variable is complete tree height balanced. Okay, now I'm checking the height, calculating the height. The left subtree height is I'm calling the same recursive function again. And for calculating the right subtree height, again I'm calling the same recursive function again. Now I am checking whether if the difference between the left subtree height and right subtree height is greater than 1, then means I am just updating my variable. Otherwise, I'm returning the max of left subtree height and plus 1, adding 1 to it, and I'm initializing it with true, and I'm calculating my height, and I'm done. Nice. Let's submit my code. Nice. Oh, we've already got 261 points. Nice. Let's solve some other question. Okay, he said you took some basic question. Okay, let's try to solve some good question. Let's pick this one. Okay, I don't know, but this, okay. Okay, given the in-order traversal of a Cartesian tree, and we need to construct the tree. Okay, what is Cartesian tree basically? Cartesian tree, it's basically a heap ordered binary tree where the root is greater than all the elements in the subtree. Okay, you may assume that duplicates do not exist in the tree. Okay, nice. So the thing is, we have been given a Cartesian tree, and he cleared me the definition of Cartesian tree as Cartesian tree is basically a heap ordered binary tree. Okay, if it is heap, that means whether the root contain the maximum value of the given tree, or it will contain the minimum of the given tree, and it says that the root is greater than all the elements in the subtree. That means root maintains the information that is the maximum value of that given tree. So I need to construct a tree, or I have been given in order traversal of the tree. Okay, if somebody, or if most of you who don't know about Cartesian tree, let me briefly tell what the Cartesian tree is and all those things. Cartesian tree, it's basically the concept Cartesian tree comes because the thing is, it's a kind of BST plus heap, or in some sense we can also call this tree as tree. And the way we have the definition that we have been given a Cartesian tree in that form. That is we have been given the in order part of it, because we know that if the given tree is BST, we can, if we have been given some order, with some specific in order. Let's say that in order is 1 2 3 4. We can construct so many binary search trees. One of the binary search tree that we can construct is simply 1 2 3 4, because in that given binary search tree, the in order is 1 2 3 4, and with the same in order we can construct so many binary search trees. The point is, so the way Cartesian tree comes, it just gives us the unique binary search tree. and that uniqueness comes because of that heap part. Because in that case, why that heap thing helps me, because the way heap we design the tree now, such that the root contains the maximum value and it also maintains the in order part. That's the basic property of BST. Okay, let's say we have been given a tree 1, 2, 3, 4. Let's say the maximum value is 4. So I can say that, okay, the 4 should come as a root, and the elements, let's say the elements before, after 4 are, let's say the elements are 3.7, 2.8, something like that. And that is the in order. I know that that is the maximum value. That means that, and I need to maintain in order as well. So it means that all the nodes which are less, which is having a index less than 4, that means all these nodes should come into the left subtree. Why? Because I need to maintain in order. I know that the in order of a BST is left, root, right. If that is the case, that I know that the in order is left, root, right, it means that, okay, first I need to evaluate left and then root and then right. So I can say that all the nodes after this node will definitely go into the right side, and all the nodes before this node will definitely go into the left side. So we have been given the in order of a tree, and the heap is kind of a max heap. We need to construct that tree. That is our question. The question is quite simple. Okay, let's try to first construct a tree. This question is also not too complex. The point is, we have been given the in order of the given tree in the form of an array. Okay, and I need to construct the tree. Fine. Okay, in this question as well, I can just somehow apply some sort of recursive approach, and in that recursive approach, what I can do, first of all, I have been given a complete vector. What I can do, I just figure out the maximum value in it. I just figured out let's say I just figured out the maximum value in it, maximum value in that complete vector, and I just make it as root. And now what I can do, I can just now recursively call for the left side as well as recursively call for the right side. And now what I can do, I can just construct this as a tree as well, and I can mark the left child for this root as the root of the left subtree, and I mark the right child of that node as the root of the right subtree. If I just solve in that way, then I can solve this question. Now first, before jumping into the code, let's first try to analyze the complexity for this question. Okay, first what I am doing, I am just calculating the maximum value. At each instance, I am calculating the maximum value. Okay, I am calculating the maximum value, which is of kind of order n. And I am calculating the maximum value at each step. Let's say I have a function which gives the root, so it has a node, which gives me the root of the tree when it takes a given array. Now what I need to do, first I need to find the maximum element in that given array. And then I need to call the recursive function again. Let's say the index I just got after calculating the maximum value from that given array, it's let's say I. So I need to call the function from the left side to the I minus 1, and that same function again with the I plus 1 to right, because this should go into the right side and this will go into the left side. And what I can do, I can mark the left as this and right as this, and I can return this. Now the complexity is the order of n, just because I am traversing over each of the nodes, over each element of the array, and also I am figuring out the maximum value in that array as well. So the overall complexity for this solution, it will go up to order of n square. Okay, so we just figured out the solution which is of order n square. Now the point is, can we solve it in a better way? That is the point. Can we solve it in a better way? One thing we just figured out that what we are doing, we are just concerned about the maximum value. Okay, and somehow I know that if that is the maximum value, and so all the nodes here comes to the left side of it. Okay, let's say I have a sequence. Let's see the sequence. Let's see the example. Let's say we have a given sequence as 5, 4, 8, 3, 1. Okay, if we have that given sequence, what we can do now? As we can see now that we have a 5, and if we just found an element which is lesser than this element, so I can safely say that as 5 is greater than 4, that means the 4 should go to the right side of it for sure. Okay, now if I figured out 8, now can I say anything if I figured out 8? Now I know that, okay, if I have some elements, let's now try to construct something such that we can able to solve our question in less complexity or better complexity. Now let's try to think what we can do to solve our question in a better complexity. Okay, the thing is, let's say I have 5, nice, then I come across 4. If I come across 4, I know that 4 is less than 5. That means what I need to do, I need to make it as a right child of 5 for sure. Let's say I just do that operations as well. Let's say I just keep it as right child. Now, okay, do I need the information of 4 ahead? Will it help me in any further processing? Okay, I don't know. Let's see. Let's say I just found a value 8. If I found a value, let's say now 3. After 4, let's say I found a value 3. Now what I can do? Okay, if I found a value 3 and I know that 3 is less than 4 and 3 has a greater index, that means 3 will go into the right side of it. Okay, so I just figured out a solution. If we have been given an in order in such way, then I just need to map as a kind of right child of that particular node. Okay, if that is the case, then I'm happy. If so, that means I'm just keeping the information, and the time I'm getting the value which is less than the particular value, in that case, I just need to mark it as a right child. Fine. If that is not the case, let's say I'm just getting a value which is greater than this value. Let's say I'm getting a value which is 4.8. Now, so that means what should be my structure now if this information is given? If this information is given, then I know that, okay, let's say we have 5. I know that all the elements, these are less than these, the elements I am storing here, it's kind of in reverse sorted order. So if it is greater than 3, nice. So that means all these nodes should go into the left subtree of this, because I need to maintain a heap kind of information. So this particular node should be the root for these two nodes for sure. So what I can do now, the overall structure at the end, it will be something like 5, then the right child 4.8 will come, and in the left subtree I will have 4, and I know that structure. So what I need to do now, what I am just doing now, if I am getting a value which is, let's say I am iterating over the array, if I am getting a value which is less than that particular element, then I am just making that node as a right child of it and just push that something. And if I am getting a value which is greater than this thing, then I just pop all the elements which is in this stack or some data structure, because I just said stack because it is following that property. Why? Because what we are doing, we are adding the elements in the end as well as we are removing the elements from the end. And if we follow the same procedure, somehow we will able to achieve our solution, isn't it? Does it sound good to everyone? The way I am approaching or the way I am dealing this problem, if I want to achieve it in a better complexity. So the point is, if we follow the same way, we can now the complexity. Now let's try to think about the complexity. If we just try to solve in that way, the thing is, what we are doing, we are just inserting an element in the stack. If that element is lesser than the topmost element of the stack, and I'm marking it as right child of the topmost element, fine. Otherwise, if the given element that I just encountered, it's greater than the topmost element of the stack, then what I need to do, I just need to pop out some of the elements from my stack. Let's say I just popped out these two elements in that case. So the last element which I popped out, I need to keep track of that information about the last element. And I need to make the left child of that particular node as that particular element. And now the topmost element which is present in this stack, I should make that particular node as the right child of that particular node as 4.8, because in the end my structure should be something like this, isn't it? If my structure is something like this, only then I can say that that is maintaining some sort of heap information as well as maintaining in order as well. So if I will solve in that way, I can solve my question from order of n square to order of n. Nice. And we know that we can't solve better than this complexity. This is the best complexity that we can achieve for this particular question. Now let's try to solve this question. So as I just told you, we need a stack to maintain all this information. Let's say I created an empty stack, and okay, now let's iterate over my entire array. Let's first keep n as size. Now what I can do, as I know that, okay, let's first check the big edge cases. Let's say if my stack is empty. If my stack is empty, that means I don't have any elements in my current stack. That means that the particular element should be the root. Or if that is the case, or okay, let's first create a root. So that means in that case, let's say my root will be new tree node, and I have been provided a constructor in which I can just pass the value of integer and it will create a node. So I just need that value, which is a of I. Nice. And kind of I'm done. Okay, now I figured out the root, and it's better to maintain a stack of tree node. So I can push into my stack, the value of root. Fine. Now the point is, now the case is something like I have an element in this stack, but the current element that I figured out, it is less than the topmost element of this stack. The topmost element of this stack, and I need to just concern about the value of that particular element. So because I am adding the basically nodes into this stack. Now if I just do in that way, in that case, what I need to do, first of all, let me create a new node. Okay, with the value AI, and mark the right child of the topmost element of the stack as that given node, and I can push that given node into the stack. Fine. Okay, even if that is not the case, that in other case, the other case is I have a value, that means AI is greater than the topmost value of this stack. Then in that case, I need to pop out some elements, and I need to just concerned about the edge case as well. If my stack is not empty and the value at the top, it's basically less than AI, we are happy because we don't have given any duplicates in the tree. So we can do in that way. We shouldn't have to handle the duplicacy case here. So we are good with that. Now, if that is the case, then what I just told you, then I need to keep track of the last element which gets popped out, because that last element will be the left child of that particular element of AI, isn't it? So if that is the case, then I can make last, and I can update my last as Toto, and I can remove I can keep it as null. Okay, now what I can do, I just figured out the last element. So let's first create a new tree node for that particular element. With the value of AI. Now what I can do, the value for that particular node, the left child of that particular node will be my last, and the right child for the topmost element. If let's first check whether we have a topmost element in the stack, or there might be a case that my stack gets empty. So I need to check that thing. If my stack is not empty, then but I need to check whether I need to mark the rightmost child for the top as the given one. If I just do in that way, I will somehow solve this question. Looks like a good approach to me. And I need to return true. Let's again check the way we think and the way we applied the algorithm. Are they both matching or not? Or have we missed any case or not? Let's first check. Okay, what we do in the starting, we just created a stack and which contains all the nodes. Nice. And we just take our n, which is the size of my array. Nice. I just iterating over my array and I'm just checking whether my stack is empty. Because I know that stack will be empty, only in that case, I need to push now that element as well. Sorry. I just forgot that thing. Okay. Because if that stack is empty, that means this is the first node, kind of. So that means I need to make it as a, okay. Oh, sorry. I just need to push. Okay. So that means I can't say that it will be my root. The root must be the topmost element in this stack, for sure. But yeah, I need to construct a node here and I just need to add the node if stack is empty, because I can't do anything else. And the other case will be if we have our value, it is less than the topmost value, then we are sure that in that case, we need to mark it as our right child for that particular element. So we are doing this thing. So it seems right to me. Now the other case will be if AI is less, if it's not less than, it will be greater. So that means it should be the root of some of the nodes. So I'm just checking out all the nodes. So for that, what I'm doing, I'm just checking up till when I have that given value, it's greater than to the topmost value. So I'm just maintaining my last node because it is required. And what I am doing, I am just creating one new node, and just what I am doing, and just mark the left child for that particular node as a last. Nice. If I do in that way, it seems like a good thing. Now let me test. Okay. Oh, sorry. Nice. Let's submit this code. Oh, okay. What's wrong? Let's try to see. Have we done anything wrong here? We have been given the tree as 231. If we have been given tree as 231, first what we can do, what we are inserting 2 here, and it shouldn't be that. It will be the first element. It shouldn't be the last element of this stack. Okay, so I need to maintain the last information. Let's say it as null. Because the way we are maintaining our stack, it's in reverse sorted order. If it is in reverse sorted order, what does it mean? That means the maximum value should come in the front of my stack. And I am popping the element in that a way that if we have a maximum element, it won't be go out of my stack, and it will always be appear in the starting of my stack. So I need to update as this, and I need to pop. If I do in that way, then it should work. So, sorry. Why now? I'm updating my last here. Okay, not stacking. Sorry, I'm doing some silly mistakes today. Let's check. Nice, we solved this question. It took us some time, but we solved this question in order of n time. That's good. That's good for us. Okay, let's solve one more question today. Let's solve this question. I don't know what's this. Okay, the question is, we have been given two binary trees and we need to check whether they are equal or not. Okay, two binary trees are considered equal if they are structurally identical and the nodes have the same value. Okay, I need to return 0 or 1 depending upon this. Okay, let's say I have been given this tree and this tree. I just need to check whether both of the trees are equal or not. It's kind of a very simple problem, but I need to check if the both of the trees are equal. That means there the node itself will be equal, as well as the left subtree and right subtree, all of them, both left subtree and right subtree also should be equal. If all those things are fine, then I can safely say that the both of the trees are identical. To solve this question, it shouldn't take much time. Then what I can just first concerned about the edge case, and you can see that this question, this simple question, it's been asked in Amazon as well. So, but the point is, are we handling all the edge cases? Are we come up with a good solution at one go or not? So, what are the edge cases? What will be the edge cases in this question? The basic edge case for this question will be kind of, let's check whether we have been given both the nodes as empty or not. If we have both as empty, both the trees as empty tree, then I can safely return 1. Because I know that in that case, both of the tree are identical. If any of them, if both are not kind of empty, one of them is empty, that means both the trees are not identical. And in that case, I need to return 0. So this will be kind of one more edge case. Now I end up with both the trees such that both the trees has some elements. Now in that case, the idea is very simple, but I need to check whether the basically value for both of them are equal or not. And it is equal, and I say that is the left subtree for both the nodes, are they equal or not? Oh, sorry. I need to concern about the left subtree only. And also we need to check whether the right subtree for both the nodes, are they equal or not? If all these three conditions met, then only I can say that both the given tree is identical. Otherwise, both the given trees are not identical. If I just solve in that way, I am done. Sounds like a simple solution to me. Okay. Oh, sorry. Today I'm doing a lot of silly mistakes. Nice. Let's submit our code now. Nice. We got a really good point. गोयल दोनों नॉन नल होने से ट्रू कैसे कह सकते हैं? I didn't say that, Goel. But I just said to you that basically, if both of them are null, only then we are saying that as true. Because in that case, both of the trees are empty. If both of them are non-null, then I am checking. Then I'm checking all the three conditions. Where the first condition is whether the value of the nodes are equal or not. If both the trees needs to be identical, okay, fine.
Hey guys, in this video, we are going to talk about the problems of code drift day 1. The topics are binary trees and tries. So let's get started. The first problem is BST sum. The problem description states that the cost of an array ARR is the sum of all the values in the left subtree of the binary search tree formed by inserting the elements of ARR in the order they appear in it. Find the sum of the cost of all the permutations of length A. Since the answer can be large, we need to return it modulo 10 raised to power 9 plus 7. A permutation of length n is an array consisting of n distinct integers from 1 to n in arbitrary order. The problem constraints are n can vary from 1 to 10 raised to power 5. Now let us discuss the problem with an example. Now let us look at this example. We are given A as 3. That means we have an array of length 3 which have elements from 1 to 3, right? So all the elements are 1, 2 and 3. Now the permutations we can make out of these 3 elements are this one, this one, this one, this one, this one, this one. These are all the valid permutations we can make. Okay. Now we need to create binary search trees out of all these permutations. So let's do that now. So the first binary search tree will be, first we have 1 as the element, then we'll insert 1 here, then we'll have 2. For 2 we know 2 is greater than 1, so it will come to the right of 1. Then for 3 we know that 3 is greater than 2, so it will go like this. From 1 3 is greater than 1, so it will be on right of 1. From 2 it is greater than 2, so it will be on right of 2. So 3 will be here. Okay. Now let's talk about second binary search tree. In second binary search tree we have 1 3 2. So first we need to insert 1. After that 3 is greater than 1, so 3 will come on right. Then after that we can see that we have element 2 as the last element, so we need to insert 2 here. Now from 1 I know that 2 is greater than 1, so it must be on the right of 1. Okay. From 3 I know that 2 is less than 3, so it must be on left side of 3, so 2 should be here. So in that way we can create binary search trees. For the third one it will look like 2 1 3. Similarly, in this fashion we can create all these 6 binary search trees. Now the answer to our problem is sum of all the values on the left subtree of each and every binary search tree, right? So the left subtree of first binary search tree, it has nothing on the left, right? So we don't have to add anything to the answer from this subtree. Now again for second one we don't have anything on the left, so we don't have to add anything here again. Now for third binary search tree we can see that we have one value here, so we need to add 1 to the answer. Let's say our answer variable is stored here and currently it is 1 because of this, right? After that fourth binary search tree have 1 in its left subtree, so I am going to add 1 here as well, so the value will become 2 here. Now for the fifth binary search tree I can see that we have 3 on the left subtree, 2 and 1, that is 3, right? Similarly here as well I can see that we have 3 on the left subtree, so I need to add 6 to the answer, so our total answer will be 8. So that is our final answer in this case. Now let us talk about the solution to this problem. Let's say we are given any binary search tree which is rooted at some integer a, right? Now all the values which are less than a should be on the left subtree of this a. Okay, let's say all those values are x, so all these values should be less than a, right? Similarly, what will have on the right subtree? All the values which are greater than a, right? Now from this observation the conclusion that we can draw out is that all the values which are less than a should be present on the left subtree of a, right? So if we have any binary search tree that starts with a and it is some permutation, then I need to add all the values from 1 to a minus 1 to the answer, because all these values will lie on the left subtree of our current binary search tree, right? And as we know, the root of binary search tree is the first element of the array, right? So for each permutation basically I need to add 1 to a minus 1 to the answer, sum of all these values to the answer. Now again let us look at this example and try to solve it using the observation we just made. So for the first element I need to add 1 to 1 minus 1, that is 0, to our answer. Since this range is invalid we don't need to add anything. For this again we don't need to add anything. For this one I need to add 1 to 1, or basically 1 to the answer. For this again I need to add 1 to the answer. For this I need to add all the values between 1 and 2. So I need to add basically 2 plus 1, 3 to the answer. For this one again I need to add 3 to the answer. So the answer of all these permutations will be 3 plus 3 plus 1 plus 1, and that is 8 again, right? So basically what we can observe here, if I know the root of some array, then I can calculate the answer for this array with a simple formula, right? What I need to do, I need to sum all the values from 1 to a minus 1 if that range is valid. Now the next thing that we need to notice is we are given all the elements from 1 to a, which is a permutation. Then let's say I fix the first element to x, then I have to choose rest of the a minus 1 elements, right? So that I can do in a minus 1 factorial ways, right? So if I fix my x, I know that I can choose the rest of the elements in a minus 1 factorial ways. So that basically gives us the contribution of this element to the answer. Now for any element x, the sum of all the values from 1 to x minus 1, it will be x into x minus 1 by 2, and I'll multiply it with a minus 1 factorial, because I can have this permutation a minus 1 factorial times with x as the root element, right? Now let us talk about the code. So our formula was we need to iterate from 1 to a, and for each number x we are using this formula x into x minus 1 by 2, and we are multiplying it with a minus 1 factorial, right? So that is basically what we are doing here. But since we need the answer modulo some number, in this case 10 raised to power 9 plus 7, So instead of dividing by 2, I have already pre-calculated a mod in 2. It is basically the mod inverse of the current number. So instead of dividing by 2, I am basically multiplying by inverse of 2, or 2 raised to power minus 1. Now 2 raised to power minus 1 modulo 10 raised to power 9 plus 7 is stored in this number, right? So now whenever I need to divide, I'll just multiply by this mod in 2. And each time we also need a minus 1 factorial. So we are pre-computing a minus 1 here. Okay, so after pre-computing, what we'll do, we'll run a for loop from 1 to a, and we'll use our formula I into I minus 1. This is divided by 2, right? So that's why we are multiplying with the inverse of 2. And then we are multiplying that value with factorial a minus 1, and then we are taking the mod. And after that, we are just adding it to the answer, and then we are returning the answer. So it's quite straightforward. Now let us move on to the second problem. The second problem that we're going to talk about is max base pair, and the prerequisite to this problem is tries. You should know how the tries data structure work. So I'd highly recommend you to learn about tries first. Now the problem description is, you are given an integer array A. There's a function f for two integers x and y with another variable b base, right? Now for calculating the functional value, first convert x and y in base b, and then the ith bit of f x y b will be xi plus yi mod b. You have to return the maximum functional value possible for any pair of elements of array A in base B. Please note that you can take two elements for pair from the same index. Note, array elements are in base 10, and you have to return your answer also in base 10, calculated value from equation in base B. And the problem constraints are, A can vary from 1 to 10 raised to power 6, and each element of the array can vary from 2 to 10 raised to power 6, and the bases can vary from 2 to 9. Now let's talk about this problem with an example. Let's say we are given this example here. We are given an array of length 10, and we are given the base as 3. That means we need to first convert all these elements to base 3. So let's do that first. Now here I have converted each and every element to its base 3 representation. I need to find a pair whose sum is maximum base 3, right? And the sum that we are talking about it, let's say we are given two numbers. Let's say I choose this one 12 and 101. Then how do I need to sum them? I'll write them here 1 2 and 101. So what I'll do, I'll add these two, it will give me 3. I'll add these two, it will give me 1. I'll add this, it will give me 1. Now for each digit I need to again do a modulo by 3. So for 3, if I'll do it modulo 3, it will become 0. 1 modulo 3 will be 1, and 1 modulo 3 will be again 1. So the answer for adding 12 and 101 in this manner I am getting is 110. So that's how we need to add when we are talking about two pairs. Now we need to maximize the answer, right? In this example, we can see that if we take these two pairs, that is 100 and 101, and if I repeat the same procedure that I did here, that is 1 plus 0, that is 1, 0 plus 0 will be 0, 1 plus 1 will be 2. Now doing modulo by 3, it will remain 1, it will remain 0, it will remain 2. So I'll get 201 here. So for this specific case, 201 is the best we can do. Okay, so that's what we need to calculate for any array given to us. And if I convert 201 back to integer, it will be 19. So for this specific case, the answer to our problem is 19. So in this way we need to solve this problem. Now let us talk about the solution to this problem with the same example. So basically I have taken that same example. These elements here, they represent the value of 1 to 10 in base 3, right? So we have b equal to 3 here. So what we can do, basically we need to find any pair which can maximize our sum, right? So the first thing that I'll try to maximize is the most significant bit, right? Let's say we are given some number here, 2, 1 and 6. Now if I'll add 1 here, then I'll get 217. But if in the same number I am adding 1 here, I'll get 316, which is way bigger than 217. So basically the whole concept is, first off we'll try to maximize the most significant bit, and then we'll move on to maximize the second most significant bit, and in this manner we'll go from left to right. Now that we know we need to go from MSB to LSB, let's say we are at some number right now. Let's say it is 101. Let's say we are at last number right now. Then what I'll do, I'll try to find any number which can maximize it. Okay, so what is the maximum I can get at the most significant bit right now? The maximum value that I can make at most significant bit is b minus 1, right? That's what I can make. Currently we have 1 here. Then what is the value x that I will add to this most significant bit so that I can make b minus 1, right? That means I need to add b minus 1 minus 1. Okay, that is x, right? So the first thing that I'll try to search for is, do I have any number which is equivalent to b minus 1 minus 1, or basically b minus 2. Okay, so in our case b is 3, so 3 minus 2 is 1. Do I have any number in the third place which is 1? If we look closely into the array, we can see that we have one candidate here. Okay, the third digit of this number is 1, right? So we have just one candidate here, so we'll put 100 here. Why didn't we go further? Because we have only one candidate, right? But let's say we don't have one candidate now. Okay, let's take one more example here. Let's say we are given these 4 values which are in base 3 already, and we need to get the maximum pair I can have for each and every value, right? So let's say I want to maximize this 100. I want to find some pair that can maximize it. So what I'll do, I'll write 100 here. Then I'll go from the most significant bit. Okay, so what is the best I can make out of it? That is b minus 1 or 2. b minus 1 is equal to 2 here. Now what is the number I need to add to 1 which will make it 2? So obviously that number is 1, right? So I'll search for the candidates which have 1 on third place. The first candidate will be this one, second will be this one, third will be this one. All three satisfies the condition, right? Now let's move on to the second most significant bit, or this one. Now the second most significant bit is 0. Now again I'll do the same procedure. I'll try to maximize this 0. So what is the maximum I can get at this position? It is again 2, right? So I'll do the same calculation here. What is the value I can add to x that will make it 2? So I'll see that x equal to 2. So I'll try to find among all the candidates that I have selected, do we have any candidate which have 2 at its second place? So I'll see that I don't have any candidates, right? None of them have 2 at second place. Okay, fair enough. That means we cannot make our second digit equal to 2. Now since I cannot make 2, I'll try to make 1 at first digit, right? So what is the value I'll add to 0 so that I can make 1? So that is 1 obviously. Now I'll try to search for a number which has 1 at its second digit. Okay, now out of these 3 candidates I can see that this one and this one has 1 in its second position, right? Now this candidate is also neglected. So now we have 2 candidates which is maximizing my value currently, right? Since we have 2 candidates, let's move on to the last digit. Now again I'll try to maximize my last digit. In order to maximize it, the best I can do is I'll try to make it 2 first. In order to make it 2, I'll try to find the number which have its last digit as 2, right? Now if I look at my candidates, these 2, I don't have any of those values, so I cannot make 2. Now I'll try to make 1. Now again I'll check which one of these have 1. So I'll see that my last candidate has 1, right? That means this guy can actually maximize my sum while I'm talking about this 100 value. So in this manner we can solve this problem real quickly. But there is a catch. We need to find these candidates each time, right? For each digit we need to iterate over all these candidates. But we can do it faster by using prefix trees or tries. So let's do that now. So basically if we are given some array, what we'll do, we'll iterate from left to right, and let's say we are currently at this element, ith element. Then what we'll do, we'll try to build a try over all the previous elements, and I'll try to maximize my current element using the try I have built on the previous element. Now let us try to build try over these 3 values first. Let's say this is the root node of our try. Then the child at each level a try can have is b. Why? Because we can have values at any position between 0 to b minus 1. I'm going to insert this element first. So it has 1. So let's say this is 1. Then again 1. Then let's say this is again 1. Then 0. Let's say this is 0. Okay. Then I'm going to insert this value. Then it will be like 1. Here 1. Then again 1. Now another 1. Right. Now let's try to add this value. It is 1, then it's a 0, then it's a 1, right? Now this is the try structure that I have built right here. Let's say currently I'm at this value, then I need to find the optimal pair for it, right? So this is my value right now. So I'll start from MSB, that is 1. Now I will try to make it 2 first. Okay, so I'll search for a 1, and in our try we'll see that we have a node which corresponds to 1. So we'll iterate on that, we'll go there, we'll say okay, we are here now. Now from this node we'll try to check the second digit. Okay, what is our second digit? This is our second digit. We say that we need 2 here. Okay, so from this node I'll try to search for 2, and from this we can clearly see that we don't have any node which corresponds to 2, right? We have just 2 nodes. The first one corresponds to 1, the second one corresponds to 0. Okay, so we cannot make it 2. So now I'll try to make it 1. Now we can see that we have 1 here, so I'll go there. Okay, we can make 1. Okay, now that we are here, now I'll iterate on the last digit. So what is the best I can get at last digit? I'll try to make it 2. So I'll search for 2 here. I won't find any 2's, right? We have only 2 nodes, 0 and 1. So again, I cannot make 2 here as well. So I'll try to search for 1. Now we'll see that we have 1 here. So it will go in this direction. So what is the value that I got? I got 1, 1, 1. So again, I got the same pair 1, 1, 1, right? So in this manner, with the help of try data structure, we can do it efficiently. Now that we got the optimal pair for this element, so we can do it for each and every element of the array by iterating over elements from left to right. So that's how we can solve this problem. For better understanding, let's look at the pseudocode now. Now let us talk about the pseudocode. So let's start off with the solution function. So here is the solution function. We are given an array A and a base B, right? So basically, first we are converting each and every element of the array into its corresponding base B form, and then we are pushing that number to a vector named VEC. After that, we are creating a try node, which is basically the root node, and we are inserting one element. Why so? Because in order to get a pair, we at least need one element already inserted in try, right? After that, basically we are iterating from 1 to n minus 1 here, and what we are doing, we are searching for the best element before the current element which can pair up with our current element. So as we have done already it in an example, for 100 this function will return 111. Okay, after that we are combining that and using another vector. So if we combine these two, I'll get 1 plus 0 1, 1 plus 1 2, and doing it modulo 3, I'll again get 1 1 2, right? So that's what is going to get stored inside this answer vector. After that, I am getting the current answer by converting this digit back to decimal or base 10. Okay, and after that I am checking if this answer is the best answer, then I'll just insert it into the global answer variable, right? And after doing all these things, I am inserting our current element into the try data structure. Okay, so in this fashion we can get the answer, and whatever we get at the end, that will be the maximum optimal answer we can get. Okay, after that we are returning the answer. Now let us quickly see what these functions do. This first function, it converts a number to its base B form and returns a vector. Okay, and this function right here, it basically converts the given vector back to its base 10 decimal representation. Okay, and after that we have the standard try node, and then we have an insert function. In order to understand these functions of tries, you need to understand how actually tries work. And in this function, we are basically iterating over the try and trying to find the best we can get for our current element. Okay, and this combine, the last function is this combine function. This basically do this operation. It basically adds up both of those vectors and then do the modulo thing. Okay, and then it returns the answer, which is again a vector. So that's pretty much it. And if you enjoyed the video, please hit the like button and do subscribe. Thank you for watching.